Testing 1, 2. Yep.
Oh, I guess I need to join Zoom actually, she said. So.
Let's see, I think we should go ahead and get started. It's 8:30. Thanks everyone for coming to day 3 of our ISS conference today. We are going to begin with our first talk. So just real quick in terms of logistics, for people who are actually in the room, don't forget there are mics on either side of the room, sort of down the middle of each. Well, not really, but kind of on the left side here and the right side over there. So just remember, there are 2 different mics if you want to come up for questions. For people who are online, you have a virtual link to Slido, so please post your questions there if you have any. And I think that should do it for that. We're going to go ahead and get started with Damian Rouson, who is going to give us a talk on cloud microphysics training and aerosol inference with the Fiats Deep Learning Library. So I'll hand it over to you.
Thank you.
There you go.
Okay, as mentioned, I'm Damian Rouson. I'm here from Berkeley Lab. I lead the Computer Languages and Systems Software Group. And I first want to acknowledge my many colleagues and collaborators who've contributed to this work, both through work on the deep learning library that I'll talk about, Fiats, as well as the compiler that we're using, LLVM Flang, and ICAR, which is a code that's developed here at NCAR, primarily by Ethan Gutman. And our work has been sponsored by the Department of Energy, and we've used resources from the National Energy Research Scientific Computing Center, NERSC, Perlmutter supercomputer. So quick overview, this is a pretty short talk, so I'll have some introductory materials and then talk about our methodology, results, conclusions, future work. For the introduction, we'll do a little bit of deep background and then motivation and the objectives of this specific project. So deep background, taking you to the beginning. This is the first Fortran manual in 1956. Fortran was developed by a team at IBM led by John Backus. And my understanding is that over time, Backus began to kind of move away from Fortran. I think was somewhat disenchanted with the direction of the language. I don't know all the reasons for that, but I do know that in 1977, he won the Turing Award. And in his lecture, he was talking about a functional style of programming, which is something that has actually influenced our work quite a bit. And you'll see it come out in the design of the deep learning library, Fiats. Another thing that sort of influenced my work, believe it or not, is the food author, Michael Pollan. Many of you might know he wrote, or actually he's a journalist who did deep investigative journalism on the food industry, so that's why he wrote books about food. And in his 3rd book, he tried to summarize his philosophy that he'd come up with from everything he'd studied about the food supply in America, which is not a pretty thing in many regards. But his philosophy was eat food, not too much, mostly plants. And so the first part of it seems obvious. What else would you eat but food? But he has a special definition of food, which is that if what you're eating would not have been recognized by your great-great-great-grandparents as food, then it's not food. So Doritos are not food, Twinkies are not food, that sort of thing. And the rest of what he's saying here is probably straightforward. So in 2021, I gave a keynote at the International Fortran Conference, and a keynote is a good time to sort of take the view from a top to null, think about what your philosophy is. And so I came up with write software, not too much, mostly pure functions. And much like he had a special definition of food, I'm going to say that if you're just writing code, then I won't call it software. What you want is a lot of the things that you've been hearing about in this conference so far, including from my colleague Kate Rasmussen, who presented our unit testing framework yesterday. You want things like a test suite. You want those to run in continuous integration setup on Git. Well, first of all, you want to Git repository for your software, automated documentation. This is kind of all the scaffolding that really makes something what I'm going to call software. The not too much part is that I am obsessive about writing compact code. So you'll see at least some ways that comes out. And the mostly pure functions part we'll kind of maybe talk about it as we go, but this is sort of what he was getting at with the functional programming style. In a sense, it kind of makes the programming more like math. When you write y equals f of x, you have certain things in mind, like the function f isn't going to change the value of x. It's actually just using x, so it shouldn't be changing its value. That's something that's not so true for if f were a subroutine or function in your program necessarily. So pure functions are more like the functions in math. So first I'll describe a functional programming pattern that we use a lot. I heard one computer scientist say that patterns are the things that you forgot to put in your language. So Fortran isn't, strictly speaking, a functional programming language. There are languages that are completely designed around the ideas of functional programming, but we do have a few features that are either inspired by functional programming or that we can at least maybe sort of hijack for our functional programming purposes. So I'll talk about those. And then those of you familiar with deep learning, I guess these days everybody hears about AI and machine learning. Inference is basically the forward pass on a neural network. I'm sorry, yes, and then training is when you do that forward pass as well as a backward pass called back propagation to train the network and adjust the weights. So we'll be talking about how we achieve parallelism on the inference and how we at least hope to achieve it on the training once we have the compiler support that we want. So the functional programming pattern, since Fortran 95, so Kate yesterday talked about a code example where she could go from 37 lines down to 2 lines just by really effective use of the language, specifically the intrinsic procedures in the language. A lot of times I find that because I'm, kind of known for my work in Fortran, I mentioned yesterday that I have Fortran on my license plate, people oftentimes want to hear about what's the next thing, what's coming. And a lot of times I want to try and get people to look back and make better use of the features that have been in the language for a long time. The pure keyword has been there since Fortran 95, 30 years ago. So how many of you were writing code 30 years ago? One hand. Okay, me too. So in other words, then for the rest of you, this feature has been in the language for as long as you've been coding or longer, but it's very rarely used. And again, another retrospective from Kate's talk, we do some things to try to support you with that, like our assert library helps you to write pure procedures, but be able to get diagnostics out of it. I emphasize pure functions because I think they over subroutines, because I think they really clarify the data dependencies in your code. And so the basic idea is that a pure function can't have side effects. Basically, you just map from inputs to outputs using only local data. So you don't reference module variables, for example. In Fortran, you actually are allowed to do that, but I would recommend not. And there's now something beyond pure called simple in Fortran 2023, which actually prevents you from even doing that. You're not even allowed to reference a module variable. You're not allowed to do most I/O, so no write, print, read. However, as Kate mentioned yesterday, you can use error stop, and we use that to great effect. And so you also can't just call a regular stop. Pure procedures are referentially transparent, so if you give them the same argument, they should give you the same result. That then leads to certain optimization opportunities. If the compiler can see that you're calling the procedure more than once with the same arguments, it knows it can just substitute the result after the first time. It doesn't have to repeat it. In fact, with the G-Fortran library, with the G-Fortran compiler, I know that even if you don't mark a procedure pure, it will try to detect if you could have marked it pure, and it will mark it implicitly as pure because of the optimization opportunities that affords. And one of the really important ones being that if you're going to call a procedure inside do concurrent, which we'll talk about in a minute, it has to be pure. Also, functional programming emphasizes defining immutable state, so things that you can't change. And so we sort of hijack the associate statement for that. If you associate a name with an expression, and one simple example of an expression is just a function invocation, then that entity cannot be changed within the associate block. It's not actually true if you associate it with just a variable, but so we typically don't do that. So as I mentioned, this procedure affords optimization opportunities, and most importantly, I think for the current era where GPUs dominate, is the ability to call a procedure inside do concurrent. So this is what it looks like to do inference with Inference Engine. So you define a neural network object. It contains all of the parameters for the neural network, the weights and the biases and activation functions and what have you. And then you invoke a type-bound procedure called infer on that object. You pass in this case, also an object, which is a tensor. In this case, it's actually a 3D array of objects because this is inspired by a code like ICAR, where we want to do inference at every point on a 3D grid at every time step. So that's a lot of inference, so I'll call it large batch inference. And the traditional way to write something like that would be to do 3 nested loops. Now, loops are inherently serial. When you're writing a loop, you're telling the compiler, do these iterations in this order. That could be very important if you're doing something like time stepping. You wouldn't want it to compute next year before it computes tomorrow, right? So then the traditional way that we do things is that we come back and tell the compiler, oops, I lied. I didn't really mean that I want you to do them in that order. I want you to do them all in parallel, which is why we have OpenMP directives. And I didn't really need to write 3 nested loops. I want you to collapse those loops. So it's something that we put into the OpenMP directive. As of Fortran 2008, so again, going reasonably far back, you could write instead do concurrent. And now you don't have to lie to the compiler first and then come back and tell it something different. And so there's no implied ordering between the iterations of this loop. And there are additional annotations that you can put on do concurrent that we'll see in just a moment to explain data dependencies. But the basic idea is you can collapse this into something more compact. So that's the not too much part of the philosophy that I stated earlier. Given that I'm obsessive about writing compact code, what I really would like to be able to do is at the bottom here, Kate talked about elemental procedures. If you write a procedure that's elemental, then you get to write the procedure as if its arguments are all scalars. But at compile time, if the compiler sees that you're actually passing in an array, because we know that inputs here is a 3D array, it will simply apply that procedure to every element of the array and then give you an array result back. So really, you can do all that in one line. Unfortunately, the compilers won't parallelize it automatically. Eventually, we should be able to get them to parallelize it with something like OpenMP Workshare. Right now, that form works. It gives us the right result, but it doesn't parallel. It doesn't give us any performance benefit. Okay, so results. So this is kind of interesting when I talk about results in the context of this talk in this conference. I'm actually talking about the code. I gave a talk at a conference many moons ago. This is back around 2003, where I refer to it as my coming out party because I've always really loved writing the code. And it was the first time I gave a talk where I actually just stood up and talked about the code and not the actual numerical results. So results here is going to be more about like how we do the coding or what's in the code. This is the Git repository for Fiats. In the upper right there, we have a few maybe shell scripts for installing things, but basically it's almost 100% Fortran all the way down. We don't make any calls into PyTorch or TensorFlow, for example. We do all the deep learning in Fortran, partly because, as I mentioned, the name of my group is Computer Language and System Software. So part of our goal is to try using new language features in novel ways and to see what this old language can do in this new emerging domain. So towards the end of functional programming, most of the procedures, essentially any procedure that we can, is pure in Fiats. So those are some of the things that distinguish it. And for this talk, I'm going to center around a couple of applications that are in our demonstration directory, our demo directory. We've got one that computes statistics on your tensors, one that trains the cloud microphysics model using data from ICAR, and one that does inference for aerosols for the energy exascale Earth system model, E3SM. And the actual results that I'll show for parallel performance will come from this examples directory. So an example, concurrent inferences. So this is what the aerosol example. We had a pre-trained neural network that came from Zhe, who's also at Berkeley Lab in a different group. And some of the parameters of the network here, it's got 3 hidden layers, 80 inputs, 31 outputs. And she trained this on data from E3SM. And this is just showing the close correspondence on the right between a first principles ordinary differential equation solver that's in E3SM and a machine learning emulation of that same result for the aerosols. So you can see that there's a very close relationship between the two. And so then just using so here I'm comparing the scaling on Perlmutter, it's a supercomputer at NERSC. And ideally, if you run on 100 cores, you'd like to see a speed up of 100 if you could. Of course, you can't get quite to that ideal when you get to large numbers of cores. What I want to do here is focus on comparing the do concurrent automatic parallelization by the compiler. And by the way, what the compiler is doing is basically translating into OpenMP. Compare that to writing my own OpenMP, and we can see that results are almost identical, certainly out to, say, 16 cores, and then quite close all the way out to the number of cores on the machine. So a couple of things that we do that are unique in this code that you don't tend to see it in a lot of codes. One is that we use derived type parameters. When Xia Bei was working with me, she wanted to do double precision inference, which is kind of unusual. Most people, a lot of times with deep learning, you're going lower in precision. And so I spent about a week prototyping how to use kind parameters on derived types so that I could support her, and then another week getting it all to work and refactoring the entire library. And she was kind of shocked that it took me 2 weeks to change the precision for her. But the basic idea is by using derived type parameters, which is a Fortran 2003 feature, which I, to that point, had never used in my career. But what I liked about it is the fact that I could set the precision in the declaration of an object. Okay, so that way I don't have to have multiple types, multiple derived types for multiple precisions. I don't have to recompile. I can use the same derived type and have it be single precision in one place, double precision in another place. And I think that's a really nice feature. Another really unique feature that is very rarely used in the wild. In fact, I've looked at like 5 other deep learning libraries that service Fortran. 3 of them are interfaces to either PyTorch or TensorFlow, and then 2 others besides ours are Fortran all the way down. And I did not find this keyword non-overwritable in any of the other libraries. This again is a Fortran 2003 feature. And what this is doing for us is that by telling the compiler that a procedure is non-overwritable, we're saying that if a child type extends this type, and we do use type extension here, I'm not showing it, if a child type extends this type, they cannot provide their own version of that procedure. That's really important because it turns off what compiler developers call dynamic dispatch, which is where the compiler has to basically figure out at runtime, or the code has to figure out at runtime what procedure is actually going to be called, the one on the parent or the one on the child. And what's really important about that is that by turning off dynamic dispatch, it gives us the ability to execute this on the GPU once the compilers can fully support our code. So LLVM Flang does have the ability to offload some code to GPUs. It can't quite handle it for our code yet, but we're working closely with the compiler developers to get there. I think I'll make this the last slide.
You're at time. Yeah. Yeah.
I'll make this the last slide before my conclusions. Just wanted to mention in the training, a very new feature, Fortran 2023 gives you the ability to do reductions on do concurrent. So that's what's in that line 909 there. I know this is pretty small, but the point here is just that there's a sum reduction on a variable that's being used in the loop. If we were to drop back to Fortran 2018, where we didn't have the reduce clause, that single statement would expand to whatever it is, let's say 7 statements that we have there. If we were to drop all the way back to Fortran 2008, where we couldn't say anything about the locality of a variable, then it would expand to, let's say around 10 statements. So really important to look, and that's one of the first 2023 features that most compilers are supporting. It's in the Intel compiler, the Cray compiler, and it's also in the LLVM Flang as well. And it either is, or I think in the next version of G-Fortran, it'll be there as well, G-Fortran 15. Okay, so I'll stop there. We don't have time to go into any of the more pretty pictures and results, but we talked about the important thing for this conference, which is the code. And so in conclusion, Fiats is leveraging Fortran 2023 support for functional programming, as well as loop parallelism. We're seeing that the automatic parallelization exhibits strong scaling that matches the OpenMP. And I'll just leave the future work there since we're out of time.
Okay, thank you. So we probably will have time for one question, if there's any, just so we can stay more or less on. Yeah. Well, actually, let's congratulate our presenter for completing their talk. Great talk, thank you. And just in the spirit of keeping on track time-wise, are there any questions in the audience? Anything anyone wants to jump in real quick with something? I've been told that snacks will be withheld if we aren't on time. No, please. No, I'm just kidding. Come on up.
Yeah, Damian, great talk. I was just curious in terms of Fortran functional. Does Fortran support higher order functions, or is it something that's been discussed at all? Or yeah.
Well, I guess you can tell I haven't programmed in a functional programming language because I don't even know the definition of that. So you'll have to tell me.
Well, it's just like a function can take in a function as an argument and then output a function as its output.
It's a very interesting question. You can certainly take in a function as an argument, and we do make use of that in some places. Well, namely in the testing framework, Julian. and output a function. My guess, so kind of, yes, like you can return, say, a procedure pointer.
Okay, yeah.
I just don't know enough about what a higher order function really means to know if that satisfies your question.
Okay, cool. Yeah, I can look it up later. Yeah, great.
Sure.
Thank you.
Okay. Oh, one more. Yep.
Quick question. So 1 year back, I evaluated G Fortran versus Intel Fortran. Intel Fortran has moved to LLVM-based compilers, and I see a lot of performance difference between G Fortran and Intel Fortran. Like sometimes it's an order of 7. So where is the gap? Why the GNU is lagging behind, or do you have a participation of different vendors?
That's a really interesting question. I don't know a lot about compiler optimizations. We kind of do a lot of work, like we sit as close to the compiler team as you can be without actually being like in the internals of the compiler. We write a lot of tests and file a lot of bug reports, but I don't know a lot about compiler optimization. Certainly, I would expect that most vendors' compiler would perform best on their hardware. So the Intel compiler would give you better performance, particularly on Intel CPUs. And I just will throw in one related caveat. Yesterday, I was extolling the virtues of LLVM playing and saying it's the most feature complete and robust compiler that I use. The one thing I forgot to mention is that it doesn't always produce high performing code. We've seen, so particularly in the training of neural networks, I'm embarrassed to even say this, we've seen code when compiled by Flang 20 times slower than the same code with G4tran. So, there's still work to be done on optimization in Flang in particular, but yeah, so there's a wide range of performance you can get depending on which compiler.
Is there any common portal or some kind of recommendations which you can point us so that like we know we are not doing wrong at our part? It's like something like the environment variable or something which we are missing. So is there any?
Well, the main thing I would point you towards is TAO, the Tuning and Analysis Utilities. It's a parallel performance toolkit that's developed at the University of Oregon. I've gotten great results out of that where it will, like you can use a profiler like gprof, for example, at least on serial code, and it'll tell you things like which procedure is using the most time. TAO will tell you which line is using the most time in your code. So that's where I'd point you for performance insights.
Okay, thank you so much. And for those people who want to ask questions of our speaker during the breaks and throughout the rest of the conference, you will be here to answer those questions. So thank you so much. And we are now going to go to our next presenter, who is going to be presenting virtually, as well as the presenter after. And so we're going to go directly to Daniel Abdi, who is going to give us a talk on developing a data-driven emulator for the high-resolution rapid refresh model, and this will be on the screen and presenting virtually. Thank you.
Hi, everyone. Today I'll be presenting about our efforts to develop an emulator for the high-resolution rapid refresh model at the NOAA Global Systems Laboratory. My collaborators are Isidora Yankov, Paul Madden Vanderlei, Gerard, Jeff, and Jacob. Okay, so to start with, here I'm showing the HRRR grid subsample to significantly. So the HRRR grid is about 1100 grid points by 1800. So it's very hard for to train a neural network using that high resolution model with the latest GPUs that we have. It's currently H180 GB. So we couldn't do the whole 3 kilometer resolution HRRR grid. So we had to subsample it into a 6 kilometer grid to do the whole domain. Initially, when we started with the project, we were looking at smaller domains shown here, like in the red rectangle and the square domain, the green square domain. So we were limited by the hardware. So we started with the small models, but eventually ended up doing the whole corners domain, but at a reduced resolution of 6 kilometers. So here, so I've already mentioned about the domains, and the data we use to train the emulator spans 3 years from 2021 to 2024. That's the HRRR version 4. And we had developed 2 global models initially, so we didn't need to rewrite, to write the models from scratch. So we just adopted the global models for regional application. We had a GraphCast model trained on UFS replay data, and we modified that to work for regional domain by just changing the spherical domain into a rectangular domain. And this model uses graph neural networks, which GraphCast uses. And the other one is developed in-house. It's based on the ResNet model. It's a CNN-based model, and we call it ResHer. So these are our two models, GraphHer and ResHer. We also wanted to explore two different approaches, which is deterministic, which is commonly used for global modeling, and there's also a generative approach where you can generate ensemble members instead of one single prediction. So for this work, we used the denoising diffusion implicit model, DDIM for short, and I'll show results for that later. And we also trained for multiple lead times at the same time. So the HRRR spans about 48 hours. So we had to train also for 6 hours and roll out the 6 hour for longer lead times. The variables we consider are 6 atmospheric variables at 12 pressure levels and 2 surface variables, composite reflectivity and 2 meter temperature. We are particularly interested in composite reflectivity, which is typically a proxy for precipitation. It is a rough outline of the ResHer architecture. At the top row, you see like the different inputs it accepts. HRRR takes about 74 channels. These are the variables that I mentioned. And we also optionally can feed in GFS data as well. And for the diffusion model, we need to feed in a perturbed HRRR channels, which adds about another 74 channels. We have additional static variables and lead time and diffusion step. These are directly fed into each block, and this is quite important for the diffusion model to be stable. And we have encoder, processor, and decoder models. This is typical of many data-driven models. For the GraphHer, I already mentioned it's a graph neural network bit. It's based on the well-known GraphPath model. It's a collaborative work with NSL and PSSL. Here in the figure, I'm showing two different types of grids we considered. The one on the left is used by the WOFcast from which we started our work, and the one on the right is an optional grid graph architecture used by the neural lab from the European data-driven models. Okay, here is an initial result on the smaller domain, on the Western domain that I showed earlier. So the green dots show the GraphHer result. The red ones are ResHer, and the blue ones are the HRRR forecast at 1 hour. So this is a performance diagram, probability of detection of the vertical velocity for a given threshold. The detection threshold is about 1 hectopascal per second. And from this graph, we can tell that GraphHer is outperforming the HRRR forecast because it's closer to the diagonal. So this is how you should interpret a POD diagram. The closer to the diagonal, the better. And ResHer is also performing well, but it's more spread. And this will become obvious on the power spectral plots I'll show later. So next, I'll show you about our results on the whole CONUS domain using diffusion model. A little bit of introduction to diffusion model. So this in the figure, you can see that initially the picture of the cat is being gradually noised. Like it could be 1,000 steps, it could be 200 steps. We use 200 steps for this work. So you noise it first until you reach like it's pure noise, which is XT here. And the purpose of the neural network is to denoise your picture, start from pure noise and denoise it gradually until you get a purely denoised image. So this is the essence of diffusion model. And why do we need to do this? We need to generate different multiple ensemble members, which is which you can do by starting from different Gaussian noise. So if you just change the noise, you get potentially different ensemble member. But I should caution you that like generating 10 ensemble members and the additional 50 steps that would be required for diffusion model adds about 500 times more expensive. So even though this is still like 2 orders of magnitude faster than traditional physics-based models, it's quite expensive compared to deterministic models. So we have different options to generate different ensemble members. We can either change the initial condition, we can change the initial Gaussian noise, and also like during each denoise step, you can use you can add some noise. So we have 3 options, but we just for this work we changed only the initial noise. So here I'm showing at the top row a deterministic forecast by Razer for 1 hour lead time, and at the bottom just 1 out of 5 ensemble members. And you can clearly see that like the second column is showing the predictions. The diffusion model produces sharper forecast compared to the deterministic model. So this is the value of diffusion models, and this will be more and more, the deterministic models become more and more blurred with longer lead times. For 3 hours, you can see it's more blurred now. Diffusion model remains sharper. This is our result for Grapher and Razer comparing just the deterministic models. You can see at the bottom some root mean square errors, and Grapher generally outperforms Razer for almost all variables except RefC, and we're still trying to diagnose why that is, but Grapher is generally a better model if you look at root mean square errors. Showing the power spectra here, the green is showing the result for Razer, and you can see that it dampens the high frequencies a lot. The red line is showing the Grapher, so it's a better model in that regard. It's sharper. But if you look at the diffusion model, the single member diffusion model is more or less overlapped on the HRRR analysis, which is our target. So it's not diffuse, it's very sharp. So the spectral plot makes that very obvious. And for longer lead times, the story is the same. The only difference is that the Grapher is now more blurred. So this is expected with deterministic models. Here I'm showing 2-meter temperature. So all other variables, we call them like smooth variables. You do not see any difference in the power spectral plots. So that's why like deterministic models are very successful in global model, but for precipitation forecasting, they have, they have those challenges. So this becomes very clear from the power spectra. Here I'm showing like fractional skill score. This is used to evaluate the skill of precipitation for models. So the orange line, the yellow line is showing for light rain, blue is light to medium, and green is medium rainfall. So we see a very good skill at light rain, and also even light to medium up to 4 hours lead time. It does well. But for medium rainfall, we expect that the deterministic models do not perform here, and there's almost no skill there. And figure on the right is showing for different pooling window sizes. That's how FS is computed. You consider neighboring points within a certain kilometer radius, and so for light rain we see like good skill even like at 6 kilometer resolution, which is the resolution that we trained the model for. Next, I'll talk about ensembles. So for ensemble forecasting, we use a diffusion model and just changed the initial Gaussian noise. We haven't, we didn't use any changes in the initial conditions, which is traditionally what's done for physics-based models. And we generated 10 ensemble members, and I'm just showing here like two of them here. So if I look at this picture, I cannot tell whether there is some spread or not between the different ensemble members, which is critical for ensemble calibration. Here I'm showing the spread error ratio, and this comes about 0.6. So this is very acceptable value, and that's also like what HRRR ensemble HRRE has. Like the spread error ratio for HRRE for the physics-based model is also 0.6. So we were quite happy with this result. But it's still under dispersive. The ideal value for this spread area ratio is about 1. So it has, if it's 1, then it's a good ensemble. But the physics-based model is also has an ensemble spread error ratio of 0.6, so we're happy with that. The next thing is, how do we average the different ensembles? We can either take the ensemble mean, which is what's done traditionally, but for precipitation forecast, there is a way of computing an equivalent mean called a probability matched mean that gives better results and also tends to preserve the peak values as well. So the ensemble PMM is the one we are going to move forward with, and I will also be showing the ensemble max, just to see what the difference with the other averaging techniques is. So if you look at the ensemble mean at 1 hour lead and 6 hour lead, at 6 hour lead it becomes more blurred. You can see like here it's more blurred. Ensemble max, it preserves the peak values, but it's covering wide area because the values are coming from different ensemble members. So this is also bad, but you can see like what's doing here. Ensemble PMM, you don't see a lot of spread. It's still but you see like more peak values compared to ensemble mean. So that's why it's better. And so for precipitation particularly, ensemble PMM is the way to go. If you look at the power spectra, this is my last slide. The ensemble PMM is the light blue. The ensemble mean is green. They are both, dampen the high frequencies, but ensemble PMM is clearly better. And if you just take like a single ensemble member, its power spectra is more or less aligned with the HRRR analysis. Yeah, so that's my presentation. Thank you.
Okay, let's give our presenter a round of applause. Thank you so much, Daniel. That was a great talk. Are there any questions in the audience? Anyone want to jump up to either of the mics and ask a question? Or online. Are there any Slido questions? I'm not sure. Any Slido? Any questions? I guess maybe I've got a quick question. On one of the slides, let's see if you could go. Are your slides still presentable by any chance?
Can you see my slides?
I
guess I have to share.
That's okay. That's okay. I guess one of the questions that I had was, yeah, if you go back maybe 2 slides, I noticed something, and this is not an area that I'm super familiar with, but I'm curious about. Keep going. Yeah, the ensemble mean. Yeah, you're right there. Okay. So what I was, sort of looking at this, there seems to be some sort of dip, between this 9 and 12-hour lead time. Was there any? What is the explanation for that? It seems like things got kind of good around the 8-hour lead time, and then dipped a bit. What's the explanation for that, or if there is any?
Yeah, so the general trend for the spread error ratio is it will increase with lead time because the ensemble members become more and more spread, and particularly for data-driven models, that's the case. So you expect the spread error ratio to increase in general. So at the 6-hour mark, you see a huge jump. That's because the way we trained our model. So the model is trained to predict 1 to 6 hours lead time directly. So you don't do any rollouts. But from 6 hours to, for example, to get to 12 hours, I unroll once the 6-hour model and get to 12 hours. To get to 7, I use the 6-hour model and then the 1-hour model. So rollouts come at the 6-hour mark. So that's why you see a huge jump in the error because you're doing rollouts. I'm not sure why it falls like from 8 hours to 9 hours. I don't really know, but the general trend should be like it should increase.
Okay, great. Thank you.
Yeah.
I think that puts us right at 9:10. So if there are no more questions in the audience, going once, twice. Okay, thank you so much, Daniel, for your presentation. We appreciate it. And I suppose that if there are any lingering questions, folks in the audience who would like to ask can shoot an email and fill your inbox with profound questions about your talk. Thank you so much.
Thank you.
Okay, our next presenter is Daniel Hahn, who is going to talk about µWMS, cloud-based microservice web map service. So thank you, and the mic is yours.
How does this work? This
I think that maybe if you okay, is that working now or okay?
oh. Yeah, okay. Yeah,
All right, thank you.
thanks. All right. Hi, my name is David Hahn. Good morning. Thanks for being here. I work in the National Center for Atmospheric Research, Research Applications Laboratory, and I'm happy to be presenting this project that my colleague, Patty McCarthy, and I have worked on. This has been something I've wanted to do for a very long time. About 6 or 7 years, I started proposing this. We finally found a way to make it happen. So we're calling this the µWMS service. Basically, it's a web map service and it's cloud-based and has a microservice architecture. So it's serverless. So the goals behind this project are to have boundless web map service capacity for your applications. We see this with user applications a lot. It's hard to predict activity. We see spikes in traffic and we see periods where there's no use of the system at all. So we're using these serverless technologies on Amazon Web Services to only pay for the compute resources that we're actually using. And so it can scale up very rapidly to handle spikes in traffic. So that's the goal of the project. So I just want to take a couple minutes to define what a few things are if you're not familiar with it. So a web map service is a major component that's used in data visualization and application development. It's a standard protocol from the Open Geospatial Consortium, and it allows a way to request map tiles of data over HTTP, so you can display those in your web applications or other desktop applications that can access the network. It's a major component we've used a lot in developing visualization applications. And one of the benefits of this versus pre-generating the tiles is that the user can actually change the color scales, the color ranges, projections of the map tiles on the fly, and they get rendered as the user requests them and sends them back. So if you see this image on the bottom, this is just showing a pressure level from Hurricane Milton last October. And this image is made up of many tiles that get pieced together. Each tile is one request to the web map service. And it has parameters in the request, like which map projection you're using, which color palette you want to use, min-max values for the data layer. So that's what a web map service is. And serverless is a little bit of a newer term, so I wanted to take a minute to define that as well. So if you see each of these 4 columns here, these are different service levels. So on-premises means you're not using the cloud at all. You have to manage everything yourself. So then we have infrastructure as a service, platform as a service, and software as a service. So the boxes in blue are what you have to manage in each service level. So as an example, EC2 would fall under infrastructure as a service, where you're asking the cloud service provider for one server. they give you the server with the hardware that you request, number of CPUs, memory, disk space, and then you're responsible for managing the operating system, the runtimes on it, and your data and your applications. Platform as a service is what I like to think of as the serverless level. So in this case, the cloud service provider is also managing the operating system and the runtimes for you. So some examples of this would be API gateway, Lambda, DynamoDB, S3. So they're managing all the servers, the runtimes. For Lambda, you tell them you want Python 3.13 to run your function, and they give it to you when you need to run your code. You don't have to worry about what server it's running on or where, or having to reboot the server ever, or managing the operating system. So, and then software as a service is just an application that you're using. So you're not responsible for anything. So that'd be like Google Docs, and you're just using the application online. So platform as a service is what we tried to stick to for this. So we add those two together, the WebMap service and the serverless architecture, and we get our project, the µWMS service. So here's just like a very rudimentary design of how the system is working. The web application is loaded on the browser on the laptop. That comes down through CloudFront, which actually isn't shown here. But we're using an open layers client to develop our map application. So in that application, there's a WebMap service layer, and it has a URL pointing to our API gateway endpoint. So when that gets called, the request goes to API gateway. The request gets forwarded to the Lambda function. The Amazon Web Services is going to find a server for us to run on when we need it, and we don't really care where it's running or how. We just tell it we need Python 3.13 and give it our code and libraries, and it runs. So part of the request for WMS is like a geographical bounding box. So and the field name and the time. So all of those parameters get passed on to the Lambda function from API gateway. And we're using S3 and ZAR to store our model data. And so based on those parameters that the browser gave, the Lambda function is going to determine which file it needs to read and which data fields, which vertical level. And it reads it, renders an image in the projection specified, passes it back to API gateway, and then that goes back to the web browser client and gets added as a tile on the display. So there were a few challenges in developing this. Well, one of the biggest challenges we had was that we're trying to rely heavily on existing code libraries. It's not have to rewrite our own projections and data storage and all that. So this is the quite large list of dependencies we ended up with. I think pandas by itself is about 150 megabytes, and everything in bold was more than 5 megabytes. So the challenge here is that we ended up with 346 megabytes total in our dependency package, and Lambda has a limit of 250 megabytes. So we had to shed about 150 megabytes of weight there. It turns out that a lot of these libraries come with examples and test cases and data. So we started going through and deleting all of that so we could reduce the size. So we set up a unit test and just kept running it. Once it passed, we would delete things and run it again. If it failed, we put it back. And if it succeeded, we kept deleting more things until we got below our limit. So it's kind of a trial and error there. So one of the claims that Amazon says is we can scale this up very rapidly. So we did some load testing here. I used the JMeter application to help with the load testing. So We set up a test in there with 1,000 users, which is actually just 1,000 HTTP requests. They call it users is the term they use. And doing 10 iterations of that. So that gave us 10,000 requests total for the load test. So here are the results of that. So with the cold Lambda function, it takes a little bit longer. What that means is your code is not deployed yet to a Python environment, so it takes some extra time to do that. It has to copy your libraries and code to a Python environment to run it. So that's ends up being a little bit slower than if you're calling warm Lambda functions, which is a Lambda function that's already run before in their environment, and it times out after 15 minutes, I think. It gets removed from the Lambda environment for other users to work on it. So for the cold Lambda tests, 10,000 requests took about 53 seconds, request rate of 188 requests per second, and we had 0 failures. So we got 200 response codes from everything, and the response body was exactly what we expected to get back. For the warm Lambda case, we expected that to run faster, and it did run quite a bit faster. So 24 seconds for 10,000 requests, and that was a rate of about 416 requests per second. Again, we had 0 errors back from it. And then I wanted to compare this with other systems that we've used in the past. So I pointed my load test at an application we have running for a different project. It's on this hardware that's specified down there. So it's a single server running on our site. And the same test took about 3 minutes and 3 seconds. And so that's a rate of processing 54 requests per second. But we also had over a 40% failure rate. So it was either 400 or 500 error response codes. And the response body was just an error message saying they couldn't be handled. So that gives you a comparison of WebMap server or the µWMS service to other methods we've used currently. And then the other benefit we're trying to get from this is a cost savings. So I just took a screenshot of the cost explorer in AWS. We'd already used up our free tier for the month, so this is actual costs. So in doing this load testing, we made a total of 59,607 Git map requests. And this is, I ran it numerous times, so that's how many we ended up with on this day. So you can see the cost breakdown. Lambda cost us almost 80 cents to handle 60,000 requests. API gateway cost us 24 cents to handle 60,000 requests. So that day was a total of $1.11. I didn't include S3 in here. That's going to have mostly just our data storage costs. So depends how much data you're storing as to what that's going to be. But then you can also see on subsequent days, we didn't get charged anything because nobody was using the system. So we handled 60,000 requests for $1.11 when we needed to handle a traffic spike, and we didn't get charged anything on other days. So it's one of the other benefits we're trying to capture from using cloud services. So the current status of the project is we've implemented the Git map requests. If you're not very familiar with WMS, this might not make sense to you, but we have not yet implemented the Git capabilities. So we still have some work to do to make it comply with the WMS standard. We're discussing making this open source. We have a prototype deployed right now, and we're looking for people with projects who might be interested in using this. So if you are, you can contact me. after the presentation. Okay, so now for the fun part, let's try to crash the server with everyone here. We don't actually have a server, so we'll see how it goes. So if anyone's willing to help test out, I'm going to put up a URL in a second so you can load the page. Here on the left side is basically what you should expect to see. It doesn't do a whole lot other than show like one level of pressure data. This is from Hurricane Milton in October. And while people are playing with this and testing it, I can take questions as well. And then maybe after the questions, you can see a show of hands of who had errors. So I kind of debated whether to do this or not, but I figure it'll either work well and look good, or we'll get a data set to help us improve it. So, and so here's the URL. And if you type it, you have to type the www or you won't get the app. So.
Okay, thank you. Let's give our presenter a round of applause. Thanks a lot. And either we're going to crash your server or crash your wallet. It's going to be. So let's go. Are there any questions on either side for start? Question? Anybody got any questions?
Yeah, I mean, I can take a guess, but just curious, what was the failure mode for the Xeon local server? Was it just running out of memory or?
If I can remember, yeah, I don't recall. I think it was maybe like a too many requests
Okay, so
type
just
of deal.
just flooded.
Yeah. It didn't run out of memory because I didn't have, that's what I was expecting, because that application got announced at AMS last January to a room of 30 to 40 people, and the server immediately crashed because it ran out of memory and I had to restart Tomcat. But yeah, so I was expecting it out of memory, but it was different this time. I forget what it was.
Motivation for this work.
Yeah.
Great work. It didn't crash for me.
What?
So when I didn't crash for me, so
No?
I loaded
Okay.
just fine. Question: the use cases we have lots more dependencies than the list that you showed there, and we're talking about gigabytes of installed packages, not just megabytes. So do you have any other advice than infrastructure as a service like EC2 for that use case?
Well, Lambda lets you use a Docker image now. So I'm not sure what the size limit is on that. I was trying to avoid that because I was worried about performance with it. So if you're able to use Docker and you want to use Lambda, you could still do that.
Okay.
And then if you're going to use EC2, you would probably have to set up an elastic load balancer and then have a server pool that gets scaled automatically. Those don't start up nearly as quickly. They can take several minutes to start up rather than seconds, like Lambda does.
Okay, so then the Docker image seems to be an idea to explore. Okay,
Yeah.
thank you.
Sure.
Great talk, David. What's the scope of the data types of files that you want to plot in this visualization? Is it just model data or any other types of data too?
Yeah, so right now we're focusing on gridded data that we've converted from NetCDF. So right now our only test data set is from WRF. So we converted a full set of the output. This app is only showing the pressure field, the lowest level, with really no configuration options on it. But so we can show the whole model from that. We're also, the code is written so that we could also add a web feature service request to this. So you can request point line polygon data from a different database, but that's not implemented yet, but it could fit into the same architecture.
Great, thanks
Basically
again.
gridded data for now. Yeah.
I think we've got time for maybe one more question. Anybody? Oh, online question. Yes. Let's see. We've got So can everyone see that question? It's, since you're looking for projects, what are the project requirements needed to use the service?
Okay, probably the main requirement is that you're willing to work with a prototype system. May not be as robust as other options out there. Yeah, I think the question about what types of data we can handle with gridded data, you need to be using gridded data, so. I don't know, yeah, I don't have too many requirements for it other than you're willing to work with a prototype system. And maybe work with us and help give us feedback on what can be improved and.
Okay, great. So let's give our speaker another round of applause. Thank you so much. We're going to go to the last talk of this session. All right, we're going to introduce our speaker, Joshna Kurra, who will be talking about toward generating experiment-specific notebooks in Fabric.
Okay. All right. Good morning. My name is Joshna. I'm a master's student from the University of Kentucky studying data science. I've been a part of
Could
the.
you come a little closer to the mic, please? Thank you.
Is that better? Okay. I've been a part of the UK Fabric team for a bit over a year now, working as a student researcher. And today I'm going to be presenting some interesting Gen AI work that we've been doing. For time purposes, I'm gonna get right into it and skip the agenda. Fabric is an international infrastructure that allows researchers to conduct experiments in an environment that closely emulates the real systems that drive distributed applications today. Its primary capability is to provide users with deep in-network programmability with nodes that are connected with dedicated optical links. There are 35 globally distributed sites, 4 international sites, and all of these are able to integrate with facilities and networks that researchers and scientists already use, such as HPC centers, campus labs, cloud testbeds, and the internet. Each of these routers offer traditional compute and storage, but also advanced resources such as GPUs, FPGAs, and programmable NICs. Here are some example use cases of Fabric. It's been used by researchers for experiments in various areas such as edge computing, in-network caching, smart data distribution. And this is some basic terminology that will be helpful to know as we go through this talk. To run experiments on Fabric, you have to first create a slice, which is a collection of logically related resources. And within these slices, you can reserve nodes, which are the virtual machines that you actually run your experiment on. Here's an example topology. This whole setup would be considered one slice, and the nodes in there are the virtual machines, which you can connect with network services. And this is a hello world equivalent of how experiments can be run on Fabric. The program is written on Jupyter notebooks, which are then run on a Jupyter Hub server. You can note here that the first thing that they do is import Fabric testbed extensions and the FabLab manager, which is likely the first thing that you would want to do in any Fabric notebook. And then you go on to run your experiment and reserve the nodes or resources that you need per your experiment requirements. So we think that Fabric can be a great asset for experimentation in various fields, but we acknowledge that there are some challenges in using Fabric. When you're a new user, there is quite a steep learning curve. You're forced to familiarize yourself with the FabLab API before you're able to run any experiments because it is necessary to program on the testbed, even for basic things like reserving and managing your resources. Yes, we have several Jupyter example notebooks and also hundreds of forum posts that you can browse with previous users' questions. But there are so many of these resources that it can quickly become overwhelming and quite difficult to find what you're looking for. And in such a case as this, when we don't know how to write the code needed, there is a popular solution these days, ChatGPT, or more generally, code generation tools. But the problem with using such generalized tools is that one, they're not trained specifically for coding questions, and two, they're not likely to know enough about Fabric to give you accurate and relevant results. So our solution is to create a specialized code generation tool for Fabric users that is more knowledgeable about Fabric and is specifically trained for coding questions. We hope this will make onboarding easier for new users and also allow them to primarily focus on their experiments as opposed to learning and understanding the FabLab API. LLMs and RAG are the basis of our solution. Large language models are very large deep learning models that are generally used to recognize and generate human readable text. Retrieval augmented generation, or RAG, allows these LLMs to reference an external knowledge base and take information from the knowledge base to augment with their inherent ability to produce a more accurate and relevant result for the user query. The knowledge base in RAG is usually a vector store that has anything that you want your application to be especially knowledgeable about. There are three main steps in creating this: loading, splitting, and embedding. When creating the vector store for Fabric, we tried loading various things: the Jupyter example notebooks we have, or the teaching materials notebooks we have, and even a combination of these. More recently, we realized that there was quite a bit of outdated information in our examples from previous releases. So we tried cleaning up the input data, and we've seen quite a bit of improvement in the results after doing that. The next step would be splitting, and there's several options when it comes to this. Some of the things that we tried was splitting by markdown. What that means is every time you see a markdown cell in a notebook, until you see the next markdown, all of that is considered one chunk. We also tried splitting by notebook. So that means a whole notebook is passed in as one chunk. And the advantage of this is that it preserves the context of the notebook. And this has been the one that has given us the best results so far. Finally, the split notebooks or documents are embedded into the vector store. We also tried various models in this process to see which one might best suit our needs. One of the first models we tried was Code Llama. Initially, we didn't see a lot of success with this, which is what made us pivot to OpenAI's GPT Mini 4, because this is the OpenAI is kind of considered like the industry standard in some sense. As expected, the performance was quite good, but we really wanted to try and stick with open source models, and OpenAI's models are of course not open source. You have to pay per query and make an API call, so we tried to find more models that are open source and experimented with them. And these are some of the things that we tried, like CodeStrawl, Mistral, CodeGemma, DeepSeek Coder. And initially these were not comparable to the results given by OpenAI, but over time, especially in the recent months, we've seen quite a bit of improvement, almost to the point where they're either the same level of accuracy and performance as OpenAI or even better. And we think that some of this is because of the improvements that have been made in our application, like the input data. But this is also kind of a testament to how fast improving these LLM models are. We also tried experimenting with prompt engineering techniques. Prompt engineering is an attempt to guide your LLM application to output the result that you want. You can do this by phrasing your questions a certain way, or by giving some background information. So one of the examples of giving background information would be defining a system prompt. For example, our system prompt instructs the model to always use FabLab Manager or always generate Python code. So it's like a set of instructions or background info that you give to the application to follow for all user queries. The other end of this is just trial and error. So for instance, over time, we've realized that including the phrase using FabLab Manager explicitly in the user query makes the model perform better. So now we ensure to append this to every user query before we pass it into the model. Finally, we also tried tuning several model parameters of these LLMs. One of the first ones was temperature. This is like a dial that you can turn up and down to define the model's creativity. A higher temperature makes it more creative, a lower one makes it more predictable. For Fabric, we found that mid to low temperatures work well because we want the model to take the retrieved information and kind of customize it per the user query, but not entirely alter it. More recently, we've actually been running our tests with a temperature of 0 because this kind of gives us somewhat stable results from one run to another. We also tried messing around with the context window of these models. So models with a larger context window are generally able to take in and digest more information, which means they can fully utilize the retrieved information from the knowledge base, whereas models with a smaller context window aren't the best at doing that. But the smaller context window models are faster to run, so it's just a little bit of a trade-off. And finally, we also experimented with how many documents we're retrieving from the knowledge base or the top K. This is kind of tied into the context window because you can imagine that a model with a smaller context window won't do so great with a lot of documents being retrieved. But regardless of the context window, we found that having a lot of documents being retrieved kind of confuses the model. So it's good to experiment and find a nice medium. And for Fabric, that's been about 2 documents. Before we move on to the results, here are the tools that we used in building this. LangChain is an open source framework for building LLM applications. It's kind of a one-stop shop for all of this. Chroma is the application database that we used. It's a specialized database for LLM applications. And Ollama is the tool that allows us to pull open source models and run them locally on our servers. Here's a reminder of the terminology that we discussed earlier as we move on to the results. So before I walk through the results, just some things that will help you understand it better. On the right-hand side, you have, it's the model that I used for that slide, and also if I included RAG or if I didn't include RAG. And on the other side, whichever side that is, that's the actual query that I typed in. And the image itself is the generated code, whereas everything that's circled in black is incorrect code that was generated by the model. For this presentation, I tried 3 different queries: easy, medium, hard, 3 different difficulty levels. So let's get started with the easy one, where I ask, how can I check what slices I have? And you can see the majority of the code is incorrect. This import statement is wrong. That won't work on Fabric. And also the get slices function does not exist on Fabric and is completely hallucinated. This is when I did it without RAG. But when I included RAG, you can see with the same model and same query, the results are perfectly accurate. The import statement is correct. List slices does exist on Fabric. And it even gives me some bonus information of alternate ways that I can find a specific slice. Moving on to the medium difficulty one, where I ask, how can I look up when my slices expire and extend them by 20 days? So the whole thing is circled in black, which means the whole thing is incorrect. The import statement is wrong. And the authenticate, get all slices, and the extend slice function don't exist on Fabric. Those are all hallucinated as well. And this is without RAG. And when I include RAG, you can see that majority of the code here is correct. The get slice function is correct, and the lease end function will also give you the expiration date, and renew will actually extend the slice. The thing that's circled in wrong is that the line itself isn't wrong. It's that it uses the date time module, but the generated code fails to import the date time module from Python. But all the Fabric stuff is correct here. Finally, this is the hard query. How can I create a slice with 2 nodes connected with L3 network using basic NICs and do CPU pinning and NUMA tuning and launch iPerf tests between them? That's complicated. It has a lot of moving parts, but that's kind of what we were trying to test. And you can see here when I run it without RAG, there are several mistakes in the code. The import statement is once again wrong, and when it tries to add the L3 network, it uses the connect nodes function that does not exist on Fabric. Neither do the functions it uses for CPU pinning and NUMA tuning. But when I include RAG, you can see even with a query of this difficulty level, everything is perfectly accurate. This is almost an exact replica of what is demonstrated in the example notebook on how to do this task. So you can see that with RAG, there is quite a bit of improvement in the results with queries of various difficulty levels. Before I conclude, I hope this talk encourages you to make your own code generation tool in your domain or project if it seems applicable. It's really not, I want to say it's not rocket science. Like, I think there's enough resources out there that we can do it, and I think it will make their life easier for a lot of your users. So to conclude, we have 3 big takeaways here. As demonstrated by the results, RAG definitely improves the accuracy and relevancy of the output. Secondly, what you store in your vector store is extremely important. Keeping that data clean and up to date will make a huge difference in how good your results are. Finally, just like with any other LLM application, it's hard to ensure consistency between one run to another. I can run it one day, get perfect results, and the next day, not so much. So that kind of uncertainty will be there, but we're excited to work more on this and see how far we can go. And finally, a special thanks to Kamal Tareja, who's part of the Fabric software development team. She helped us quite a bit in evaluating the generated code. And also to the ISS conference for giving me the travel and registration support that made it possible for me to be here. Thank you, and I'll take any questions.
Okay, let's give our speaker a great talk, and I'd like to say, are there any questions? And thank you also for using open source LLMs. I think, we should support the multitude of projects that are out there to make sure that OpenAI changes their name to Closed AI. So we have a question here.
Yeah, thank you so much for the great talk. That was really informative. I was wondering, how big is the existing knowledge base? Do you have any metrics on that?
So I have a number of documents, and it is about 120 to 150 documents. And I think the goal, honestly, is to even cut down from that, because I just think that there's information that we can clean up, because certain notebooks, they have things that are redundant that are already present in other notebooks. So we're hoping to cut down a little bit more. Yeah.
Awesome, thank you.
Yeah.
Great talk, Joshna.
you.
I'm curious how you decided to follow this route of using LLMs to provide a better experience for the user and be able to answer their questions instead of developing this really comprehensive and thorough documentation base. At what point did you decide to go okay, if we keep going down frequently asked questions of this, we're just gonna get so many answers here rather than going towards the AI approach?
Okay, so just to clarify, are you asking why kind of we chose to focus on this tool versus just kind of solidifying our documentation or making it more comprehensive? Okay, yeah, I think that, so the idea is that we do have documentation that's actually quite helpful, but it's just that as the scope of the project grows, there's so much more documentation being added that when a user wants something specific, it's not very easy for them to find it. Even during the search results, I feel like the things that show up, there's so many of them that it's not very easy to find. And that's why we kind of pivoted to doing this, where it's a little bit more of a automatic, it's like a quick and dirty kind of way. So that's kind of how I think the project started. Yeah, and we do want to take not just the notebook examples, but also the documentation and make it part of the database or the vector store that we're using. Yeah.
Thank you.
Yeah. Oh, and I want to say that I do have like a sort of we do have a sort of initial user interface running. So if anybody wants to type in queries and test it out during the break, I'd be happy to do that. Yeah.
Thanks for the talk. Maybe I missed this early on, but so for the 3 tests that you did, the easy, sort of easy, medium, and hard, I think on the hard test you had said that with the RAG, it produced a solution that was very similar to a solution that was in one of the notebooks. Did you do any testing that involved something that really wasn't covered well by the notebooks, but could be inferred by the knowledge that was taught by the notebooks?
That's a very good question. I think that's one of the drawbacks of what we've done so far, because we haven't really come up with any questions that aren't part of the notebooks. The questions are kind of what we did in phrasing these questions was look at the notebooks, find the task that we want, and then phrase it like entirely differently than what the notebook phrases it as. So that's kind of what we were trying to, at least a little bit of a variance. But it's just that there's only so many things that we can predict. The users might have a lot of different questions, and we are hoping that like once this is like a little bit up and running, we can take their questions as feedback and kind of improve this. Because I feel like I try to come up with a lot of questions, but it's just I run out of like what to come up with because I joined Fabric, I worked on the teaching materials for a little bit and then jumped right into this. So I feel like I just don't have enough experience to know what questions that users might have. Yeah.
Yeah, well, you'll get a good training data set from them.
Yeah.
Thanks.
So you just said if like open to public user sending in the question. So how do you save those questions?
Oh, there's something called Gradio in Python that allows us to make like a user interface for LLM applications. And my advisor, Mami Hayashida, she wrote some code that will kind of save the stuff that users type in like each time the server is up and running.
Okay. So for like for all those generated like from your service, do you like feedback to your?
Not yet. I think that's something that would be helpful, kind of like a chatbot. This isn't quite a chatbot yet. It's like one question, one answer, and then repeat sort of. But I think that would be a good next step. Yeah.
Okay, thank you.
Okay, we are at time. Thank you so much. And let's give our presenter another round of applause. And okay, I think we're at break. We've got 20 minutes, 30 minutes, and snacks and other goodies, I think. And we'll see you back at 10:20 in this room. Thank you.
Yeah, it's a joint, release. Yep.
Oh, oh. Oh, so so we will restart our session now. I'm Haiyin Xu. I'm gonna moderate of this session. And the first speaker gonna be Brad Klotz from NCAR EOL lab. He will talk about the internet workflow design for simulated airborne phased radar data. Welcome you.
All right, thank you. And good morning, everyone. Happy to be here to talk about APAR. So as the title suggests, I'm going to be focusing on kind of our workflow design for our simulating APAR data. I'd also like to acknowledge the co-authors on this work, spanning across labs in EOL, M-Cubed, and we also have partnerships with RAL and Sizzle, as well as university partnerships with Colorado State University and Stony Brook University. So, go. Just to give you a quick outline of what I'll be talking about today, I would be remiss to not describe what APAR is before going into why we're trying to simulate its data. Talk about some of the motivation and both from the science and engineering frontiers related to APAR, and then get into some of the workflow diagnostics for simulating our APAR data. This then allows us to connect to different applications and look into different metrics related to quality control, visualization, or analysis with the simulated data. So I want to first draw your attention to these pictures on the bottom of the slide here. These are some different what we would call high impact weather scenarios. These are severe weather events such as like a squall line or a supercell that might generate a tornado, tropical cyclones, even something like an atmospheric river that can cause substantial flooding along the US West Coast are all types of systems that we want to study with APAR. So APAR is going to be the first airborne C-band dual Doppler, dual polarization phased array radar, which is important because it allows us to link different atmospheric processes together from kinematics, microphysics, and thermodynamics within a storm environment. We also have the ability to use this data to link into forecast models through data assimilation. So that is a future objective with APAR once it becomes an operational instrument, allowing us to improve upon forecasts and predictions of these weather systems. I would also like to mention that this is a large interagency partnership that we have across NSF, NOAA, as I mentioned, university partnerships that we have in place in the program. So in terms of the design and the operation of APAR, you can see in these images, we have these panels on the sides, the top, and the cargo door of the NSF NCAR C-130 aircraft. This is the intended full operation of a full APAR system. The reason that we need this on an airplane is that we can fly long duration missions over remote regions, including the ocean, that have not really been observed before with a dual polarization, dual Doppler radar. The phased array technology allows us to access advanced engineering, where we will end up producing what are called airborne electronically scanned arrays, or AESAs. These are the panels that you see in the pictures that allow us to not only have agile scanning capability with this technology, but also have more control over our beam forming and reduce uncertainties in our measurements. You also notice in these pictures that we're producing vertical scans and three-dimensional coordinate system around the aircraft, as well as generating horizontal scans out towards the side. So this is important for understanding the full structure of these weather systems to get a full coverage for the winds and precipitation fields. So we can look at this in terms of existing radars that are on board, such as NOAA's tail Doppler radars that they use for hurricane reconnaissance. And those highlighted in this blue rectangle here. For a hurricane, we're able to diagnose the reflectivity as well as the three-dimensional winds from the dual Doppler analysis. We can look at this in horizontal or vertical space. With the addition of APAR, we can then take the next step in terms of combining that with the microphysics. Here, I'm overlaying the actual particle discrimination, looking at what types of hydrometeors we're able to look at based on the dual polarization capability, and link that back to the kinematic processes. We also have the ability to, with the top panel, would have the ability to get direct measurements of vertical velocity, which has never been available on an airborne platform radar before. In terms of the engineering design, this is kind of an overview of what the panel looks like. It's designed of these subarray panels that allow us to combine elements to produce a coherent beam that allows for the digital beam forming and agile scanning. I won't go into a lot of the details here, but essentially this requires a significant effort both in the structural, thermal, and aircraft design implementation on the C-130. So as you can see, this is a complex instrument that requires a lot of collaboration across scientific, hardware development, and software engineering teams. It's currently under development. This is not an operational instrument yet, but this is why we're talking about simulation here. So these different teams have various ways of simulating different aspects of their data sets. So the goal of this presentation is to kind of show how we might link all of them together through a coherent workflow. And, I think of this kind of like pieces of a puzzle, where we have scientific data generation from high impact weather events. We can access radar front end tools to understand design implications and calibration, the radar back end tools that are available to us that control how the radar scans, its data collection and archival, and also the links to the visualization applications. So several of the main simulators that we have in place right now. The first one is what we call AOSPRI. This is the APAR Observing Simulation, Processing, and Research Environment. It is a public repository on NCAR's GitHub page. The purpose of this tool is essentially to take numerical weather model output and generate radar moments, dual polarization variables from that output as the aircraft flies through the storm environment. We also, as part of the engineering support, we have what's called the ACES simulator. This allows us to test IQ time series, beamforming, and waveform implementation. And this is more of kind of the ASA evaluation simulator. And we also link back to this open software environment called LROSE. It was spoken about on Monday to look at different data QC analyses and visualization for our simulation. So this is kind of an overview of what our workflow looks like for Osprey, and then also linking back to some of the interconnected tools at the bottom. Now, don't worry about this. There's a lot of information on this slide. I'm going to go specifically in each of these three components. So as I mentioned before, Osprey is intended to kind of be the basis for where we go with our linked applications, where we have the pre-processing stage, which allows us to kind of set up the scene and provide initial parameters to run our simulations. And then in the moment processing phase, which is that middle box, is where we're actually computing the radar moments from the model output. Within that computation, we do have the ability to run parallel computing using OpenMP. This is essentially done by breaking our flight into different segments and processing in parallel to speed up the process of generating our simulated data. And then linking tie-ins to different applications such as quality control, the LROSE environment, or the ASA simulator, as I mentioned before. So getting into some more specifics about our workflow, the pre-processing stage is actually very important because this determines, what type of weather system we want to explore or the flight paths we want to investigate the storm with. So just to give you an idea, we have this animation is showing a WRF simulation, an atmospheric river event from 2021. We can use this information as our starting point to investigate different aspects of this type of event. We also have a flight planning GUI that is pretty versatile in terms of how a user can access and produce flight plans for the simulator. This is based on, it can go as far as a person wants to manually pick all their points, or there's actually a machine learning based methodology that allows more automated approach to defining the best flight path around the weather system of interest. We also have the ability to impose different scan types or parameters that we want to test as part of the simulator. We can link, expect to be able to link specific beam patterns and waveforms as part of upgrades to this system. So once we have gone through the pre-processing stage, we can now move on to kind of the meat of the code. This is actually written mostly in Fortran, and we have the ability to take that information from the pre-processing stage and then integrate that through the workflow. So if we focus on this first part where we take the model output, this of course is as a gridded data output, we want to convert that into radar space. So in order to do that, we have to determine the aircraft time and position, and then create a radar volume space and interpolate those model variables to a radar grid. This is first accomplished by converting to an aircraft-centric reference grid, which is this left figure here on the bottom, and then going a step further and converting to Earth relative polar coordinate system. We then, once we have that those model parameters in radar space, we can then pass that to our radar moment simulator. This is a tool that was developed by our colleagues at Stony Brook University. It's called the Cloud Resolving Radar Simulator, or CRSIM. And it allows us to generate both standard and dual polarization moments to pass that on to further analysis. In this figure on the bottom, we're working with Stony Brook now to generate more specific applications for APAR in terms of CRSIM. This is just giving an example of how we might replicate signals based on land or ocean surface and the artifacts associated with them. The last part of this I wanted to highlight is we are saving these output in CF radial format file, which is a version of NetCDF. So now I want to move on to some of the connected applications that we have access to through this workflow. focusing first on some of the quality control procedures. There are built-in applications, which are actually, some of these are embedded within the LROS environment. This particular one, the calibration, allows us to look at some of the engineering components that might be connected to the simulator. We have the ability to, once we have different artifacts, say from ground or ocean surface clutter, we can use tools to remove those data. An important application is wind de-aliasing. This allows us to unfold velocity data from the Doppler measurements. And then we also are making use of new tools. Isaac Schlussi from CSU gave a talk on Monday about Ronin. So we're working closely with CSU on some of those new tools for analysis. I wanted to talk briefly too about the ASA simulator and how we're connecting to that application. I'm not going to go through the detailed workflow here, but essentially what the way this works is we take the output from Osprey and pass it into the ASA simulator. Here, if you see under the box that says ASA Sim CPU, that's where we load in that data. And then it's passed to a GPU system that assembles the various pulses that then we can generate specific waveforms that the ASA might produce, and then back out the different radar moments and compare that back to what we would generate from Osprey. This is a good way to evaluate performance of the ASA and how it might handle different types of waveforms and compare it back to kind of an ideal situation. Other types of radar analysis. One tool that we're making use of is this cool tool called Samurai, also developed by our colleagues at CSU. We're also working closely with Sizzle on improvements for efficiency with that code base. And essentially, Samurai allows us to look at the three-dimensional wind field and structure analysis of storms. So here I'm just showing an example of the three-dimensional radar reflectivity and streamlines from a supercell case. So Samurai is important for us to diagnose the three-dimensional structure of the winds associated with severe weather events. Again, this is another application looking at the vorticity mesovortex related to the supercell as it's going through tornado genesis. Other applications include quantitative precipitation estimates that we can now use the data from Osprey to help understand how APAR could improve upon existing algorithms for diagnosing flood potential. And then, as I mentioned before, the particle identification is a really important application for our dual polarization analysis, which can inform on new information about drop size distributions in storms, as well as microphysics. Even going a step further, we can even diagnose ice water or liquid water content, which would be more relatable to model forecasting. The last item I wanted to talk about was visualization. There are multitudes of tools out there. We have available Hawkeye as something that we make use of in order to output data. This is just a screenshot from the documentation from Hawkeye, but it allows us to view the output in a radar-centric coordinate system. There are also engineering applications that we can link back to the ASA simulator to look at time series performance and power spectra, and also different user-defined applications that we can link into the workflow, such as analysis for flight planning and kind of animations of how the storms are evolving over time. So just in summary and some future development, so in order for us to understand some of APAR's performance capabilities, we have these simulation tools that we link as part of a large workflow. I mentioned walking through the Osprey code, as well as the ability to test different waveforms and beam patterns in the ASA simulator. We have ability to look at different radar analyses and visualization tools within this workflow. And then just in terms of things that we want to improve upon for the future, of course, our efficiency and usage of parallel computing could be improved to help speed up some of the processing associated with the moment computation. We want to improve our linkages to some of existing tools, but also open up opportunities to link to other open source tools that might be of use to the simulation workflow. And then also, we're kind of starting this development of a true system digital twin that encompasses all aspects of APAR, especially looking at some of the engineering components and then linking back to the weather simulations. So I think that's it. If there's any questions, I'd be happy to take them.
Thank you, Brad. Any questions? So I have a question. So can you point out which part of this process is happened on the airplane?
So from that box that was the workflow, that was the middle box. It's the computation of the here, let me go back.
The moment one?
I guess what's exactly, you're asking about where on the airplane we are actually computing?
Yeah, yeah.
So I guess I would talk about it in this context is that starting with that bottom box on the left side under the model transformation, that's pretty much where we would start with observations from the aircraft as the radar is taking observations in radar space. From there, we can then compute the moments. So this isn't, because we're starting with model output, we have to first do the conversion into that radar space, and then we can kind of replicate how APAR would collect its data as flying in and around the severe weather of interest.
Okay, yeah, got it. Thank you. More question? Is there any question on the Slido? Okay, so thank you. So our next speaker will be Dazhong Xia. He will present here. Okay. I didn't see you. So he will talk about a small tool for medium data, browser-based data exploration, and export down click chip.
All right. Cool. Yeah. Hi, my name is Dazhong. I'm a member at Catalyst Cooperative. We're a little worker-owned co-op that deals a lot with US energy and environmental data. And I'm here to talk about a tool that we use to sort of make our data actually accessible to people in the public. So let's get started. Okay, so I'll set the stage, talk about a little bit about us as Catalyst, and then about our data, and also about our users and what they need. So yeah, I've mentioned we work with energy data. We mostly work with data that energy utilities sort of report to the federal government, and then the federal government then republishes. That's represented by this mess on the left because it can often be very hard to work with. And so what we do then is we sort of clean it up, normalize it, and then we republish it as one database that is openly licensed. So then other people out in the world, so regulators, policymakers, advocates, researchers, people like that, can turn them into actual like good decisions about what to do with our real energy system, which is cool. It's nice to have your computer work have an impact in the real world. Well, all this real world impact doesn't really happen unless the people doing it can actually navigate and understand your data, which was easy at first. When we started making this data set, there was not a ton of data. It's relatively easy to look at 3 tables and figure out which one is the most relevant to you. However, the downside to having 3 tables is you don't have a lot of coverage. So as you sort of start to get more and more data about this very complicated system that we have, it starts to become a lot harder to navigate. Now we have like 250 tables-ish. There's 3,000 different data columns. it's just kind of hard for a person to grapple with it, even though the scale of the data is still pretty manageable for a computer. So we decided we wanted to, make it a little easier for our users. And so we talked to them and found out that they have three main sort of needs or questions when they're dealing with our data, which are, the first one is when you show up to the data set, your first question is, do you have the data I need? This can be pretty hard to figure out, especially when you have a ton of tables. They're all about things that seem like they could be relevant, and they're all sort of related. And so this problem, we'll talk a lot more about these later. I'm just going to give it a shorthand name here, which is search. And then the next question is once you've found, a handful of data sets that seem promising, you need to actually figure out, like, is this really what I expect, or was I fooled in the first step? And so you have to answer questions like, what time frame does it cover? What geography does it cover? Are there any weird outliers? Is it missing exactly the data that I need? Wow, how inconvenient. And so that sort of question we sort of can lump under exploration. And then the third need is once you figured out, yes, I found the data, how do I work with it? How do I get it into my system with my tools that I actually know how to use? And so we'll just call this last step export. So we've got those three user needs, but we also have one fourth need that comes from us as Catalyst, which is that we want it to be cheap. We don't want to spend a ton of money operating this thing. We're a tiny organization and we can't really have a person dedicated to ops. And also we don't have a ton of money, so we can't just pour money into a cloud service. I'm sure many of you are also familiar with funding uncertainty. So, we're trying to keep things cheap here. So we have this sort of set of pretty reasonable demands, I think. And we figured, okay, there's probably some off-the-shelf thing that can make all this work for us. So we went and looked for them. But it was sort of like putting a square peg in a round hole. Turns out that there are a bunch of open source tools out there, but a lot of them are designed for like internal corporate use. And so often that's like much bigger data than we need. Or it's like, so it becomes complicated to run and hard to operate. And then some others have restrictions on how you can use it. And so it's like, it's not designed for public access. Or there's also some tools that worked in all the right ways, except you couldn't export things. So we ended up building our own tool, which is a tale as old as time. Here's what it looks like. On the left, you can see we have like a search bar, and search results are sort of grayed out the description so you don't have to be distracted. On the right side, there's a table display that sort of shows you what the data looks like. You can do some sort of rudimentary filtering and sorting for the exploration piece. And then on the top right, there's that export button that just pops out a CSV for you. So we've got those things. So we've met the user needs. And then also, in terms of expense, the infrastructure to run this thing costs about 30 to 40 bucks a month, as far as I can tell. And the code base was only about 1,000 lines of code. So I hope it will continue to be cheap to maintain going forward. But no one knows anything about the future, so we'll see. So the rest of this talk is just going to be about how it works. We're going to start with some sort of like high level stuff, 5 concepts that underlie everything, and then we'll just go into the details and give you a whole list of tools. There's a bunch of links that will be in the last slide, so you don't have to like frantically Google everything that I'm talking about. All right, so we already talked about the user needs up top, but I'll just go over them again. We've got the search, we've got the explore, and we've got the export. And in the bottom left, on the bottom side, there's like 2 supporting concepts that underlie everything else. The one on the bottom left is a little tag, and that represents like data descriptions. You sort of just have to describe your data before people can actually use it. And then on the bottom right, again, with the dollar bill is cheap infrastructure. You got to run your code somewhere, and so we'll talk about that as well. We'll start with the supporting roles, then go into the user needs. Okay, data description. This one is first because it is the most important. You gotta describe your data, otherwise people can't actually understand what's in it. And when you describe your data, there's basically 3 core things you need to talk about. First one is you gotta describe the whole table. Just figure out like what is in this thing. And the next one is where can you find this table? How do I actually get access to this table? Is it at some URL? Is there some crazy FTP situation? Just figure it out. And then the last thing is that you want to have sort of more like detailed descriptions of each individual column so that people understand what the data inside your table actually means. There's one other thing we need to think about, which is making this whole sort of metadata situation machine readable. The whole point of, well, not the whole point of describing your data, but one very helpful thing about describing your data is that you can then build tools that use those descriptions, but you can't do that if your tools can't understand your descriptions. So those are the 4 critical pieces of data description. Unfortunately, there's no like one weird trick. It's just hard work. There's like, you have a lot of information in your head and you're just trying to get it out into the world. There's no, at least no current shortcut for like just taking stuff and spitting it out like that. So you're just gonna have to do a bunch of work and you're probably gonna have to keep maintaining it. Sorry. And yeah, I'll just show you sort of like what we use for our data descriptions. We follow a format called the frictionless data standard. It's one of a handful of different standards for this kind of stuff. We've used it for the past couple of years. No real complaints, and I think that's about as high praise as you can give for a standard. So, you know, yeah, go use frictionless. There'll be a link at the end. And so here's what it looks like. It's a JSON blob. There's fields. The name and description field describe the table name and what the table is about. Then there's a path field that shows you where to get the data. And then there's a schema field, which then includes information about each individual column. So pretty straightforward. Yeah, you can go find the documentation online. So that's everything about data description that there is to know. Let's talk about the infrastructure. So this is a diagram of what basically our old data portal looks like. And it's a pretty standard like web application thing. So on the left, you've got the cloud, you've got a bucket that stores all your data, you've got a server, which is that blinky box in the middle that handles sort of the actual client requests. And on the right side, you have the user blissfully off the cloud, and they're using their laptop to access your data. And so here they make these small requests towards the server, and then the server then says, all right, let me get the big data out of the bucket and then send the data to the laptop. That's represented by the big fat arrows. Totally works, but costs a bunch of money to have that fat arrow across the cloud boundary. Cloud providers love to charge you these cloud egress fees. You know, it's a couple cents per gigabyte, starts to add up pretty quick. This sort of architecture also is a little tricky when you have a lot of users, or if there's one user who is just automatically scraping your data relentlessly, because your server is doing a lot of work and pushing a lot of data out there. So that can cause your server to go down. It's happened to us sometimes. Yeah. So this is pretty annoying. And fortunately, there is one weird trick here. So I'll show you what it is, which is you actually have the user talk directly to the cloud bucket and then also to your server, but your server is only sort of exchanging little tiny messages and it doesn't matter. The astute viewer will observe that there's still a fat arrow crossing the cloud boundary and there's still the money flying away on top of it. So does this really help with anything? And the answer is sort of. This actually opens up a couple different options to reduce your costs. The first one is you can make the arrow skinnier by just shipping less data. We store our data in Parquet, which means that it's a file format that supports partial reads. And so if your file format supports partial reads and your hosting provider supports partial reads, then when you have 20 years of data and your user only wants 1 year, they only grab the 1 year of data from the bucket, thus reducing your costs by 95%. Wow. The other thing you can do is you can just sort of get rid of these costs. Sometimes you can just do them for free. And I'll show you how in the next 2 slides, or the next 1 slide. These are 2 options that we use to host our data. We host our stuff on AWS. Yes, AWS does cost money. However, there is a open data sponsorship program that they run that is not super well advertised. But if you apply, you get in, they pay for your egress, they pay for your storage. It's great. Definitely highly recommend that. The other tool that we use to host our data is Zenodo, which is like a scientific data hosting service run by CERN out in Switzerland. They let you just put your data up there for free. They don't charge you any money. There are certain limits to how much you can do and how many files you can put in one sort of record. But as long as you can find a way to work around that, or if you can just work within it, it'll also work great. Yeah, so that's enough about infrastructure. Let's get into the actual, user-facing stuff. So let's talk about search. This is a picture of what search looks like. User sends a query to your server. Server thinks about it, looks at the metadata that is hosted on the cloud bucket and says, okay, I know which data descriptions are most relevant to you, and sends the data descriptions back to the laptop. Crucially, you don't send the actual data. That's too big and slow. So you send the little descriptors back, and then the piece of software that determines relevancy is a search engine. There are tons of search engines out there. Most of them are designed for like millions of documents, and we're only looking through like a couple hundred tables. So we just picked the most lightweight one we could. It's called Whoosh Reloaded. It's super fast to set up, took like an afternoon. Nice and easy. All right, so we have the data on the laptop, or we have the metadata on the laptop, time to actually explore it. So that means you need to get the data from the cloud into your browser, and then from the browser into your user's eyeballs. To get data from the cloud into the browser, we use DuckDB. DuckDB is this like hip and happening new database tool that has lots of fancy features. One of them that is very important is reading remote files, and then the other one that is important is running in the browser. That's exactly what we need. Super easy choice. Just use DuckDB. To get from the browser to the eyeballs is a little trickier. We tried a bunch of different tools. There's a million different visualization tools out there. We ended up with AGGrid. It's just a super common, straightforward table library. In this process, we tried out a bunch of tools that are like, we were tempted to like make a whole analysis framework and let people do all sorts of crazy insights on our web app. And then that was really hard. And also people wanted to use their own tools. So we settled on something that was like more streamlined and then allowed for just straight up export. Which brings me to export. People want to use the data in their own tools, and that means we need to give it to them in a format they can use. That format is CSV. We took a user survey of our users. They all love CSV. It's easy to write. It's easy to read. There's definitely a lot of problems with it, but it's sort of the lingua franca of our little data world. So, yeah. We have all of our code as open source. So if you don't want to write your own CSV export, you can just go grab ours, which brings me to this. This whole project, it dealt with a bunch of our needs, and it was pretty useful, but it didn't take that much work because we were able to build on the work of some amazing open source developers. And hopefully, after this talk, you can build on our work and build your own data portals. I think that's it. I went pretty quick, so I'll just show you the resource slide so you can take a picture if you want, and then answer any questions that you might have.
Any question? There is one slide. Say, just incredible slide to go along with your talk. The illustrations are great and they're very informative. So, are you a cartoonist?
No, I just bought a Wacom tablet for $40.
So I have a question. So, like, the data you host, do you host for anybody's data? I mean, or you just host this only the energy data?
So this this tool only accesses our energy data. But you can run your own if you have your own data to show the world.
But you don't like provide a service for host data.
No, we pay other people to host the data, or I guess we don't because AWS gives it to us for free. But.
Okay. Another thing that like if is that possible, I can just like HTTP access your data.
Yes. So if we look back at the screenshot, there's a button there that says under the green button on the left where it's like preview and export. There's also just download the table as Parquet. That's just a straight HTTP link. There's no.
Oh, I can just copy that HTTP link and download.
Yes.
Okay.
So it's all hosted on S3, and you can just grab it. This is just like a layer on top of that for people who want to look at it before downloading.
Okay. Okay. Great. Good. Do you ever compress those data?
Yes. So the Parquet files are already compressed.
Okay. Okay. Great.
Yeah.
Thank you.
All right.
Our next talk gonna be Zach Kurra. He will like present it remotely. He will talk about building, maintaining, and tracking machine learning models in a production environment. Zach, you
Hello.
can start.
Hello. Yeah, my name is Zach Schira. It's great. I'm going right after my wonderful coworker, Dazhong. I am also an engineer at Catalyst Cooperative, and yeah, I'm going to talk about managing machine learning models. So I'll of course be getting into what that actually means, but the gist of what I'm trying to get across is how can we make our machine learning and AI development more streamlined, reproducible, reusable, and collaborate better with our teams during this process. So let's get into it. As a little background, just want to talk quickly about some of the modeling work we do and what inspired this. So traditionally, again, as Dazhong mentioned, we work with electricity and energy data primarily. And we have traditionally done small bits of machine learning, mostly focused on record linkage. So we have all these data sets that come from different government agencies, and we want to be able to know that we're referring to the same physical entities, like the same power plants across these different data sets. And unfortunately, the federal government is not doing a lot of coordination between these agencies, so we don't have unique identifiers. So we have to generate those ourselves. And this is a pretty complex problem in many cases, but a lot of that complexity is in the data cleaning and pre-processing, which is true of a lot of machine learning. But it means we're typically working with relatively small, unsupervised models that we don't need to do a lot to manage. We can kind of do it in an ad hoc way, just define the models in code, and they get run just like anything else. But we've been kind of dipping our toes, or maybe diving into the deep end with a new set of machine learning problems, which is trying to extract structured data from unstructured documents like PDFs. So one such problem that we recently took on was trying to look at the ownership of power utilities. So we wanted to be able to know, like, who are the big holding companies who own power utilities and what other companies do they own? And that data was only available in SEC documents. So these are documents that publicly traded companies have to submit to the SEC, and they contain, among lots of other financial information, a list of subsidiary companies that bigger company owns. And at the bottom of this slide, you can see an example of what this looks like. Unfortunately, like in this example, it looks, at least visually, somewhat structured like a table. That's not always the case. There's not nearly as much standardization as we would like. And sometimes there's different information contained in there. And so we ended up with a pretty complex computer vision model that looks at these PDFs, pulls out data, and puts it into a structured table that we can then use just like any other data and distribute to our users with the great tools that Dazhong just talked about. And so this ended up being a big model that required dedicated GPUs that we could only access in the cloud. And we'll talk about some of the challenges that we encountered in this development process. So there's a lot of logistical challenges. If we're training these big models, it takes a lot of time and dedicated resources to train the model. We need to make sure we're saving the weights and whatever other outputs we have in a place that is usable by the entire team, that's not going to get mixed up and confused. We don't want to be just naming them with version numbers like we do here, and we can't commit them into a Git repo because it's giant binary files. So this presents some challenge. And we want to make sure that as we're developing these models, we are developing different models, trying different parameterizations, and comparing results. And we want to be able to make sure that we're comparing the correct results with the correct version of the model. And then we also want to make sure that over time, as we get new data or we make updates to our models, that we can manage those updates in a relatively streamlined way, that we don't come back in a year and we're totally confused about where everything is saved, and that we have a system in place so we can compare new results to results that we might have had a year ago. And there's also some operational challenges, which is, again, we're running this on dedicated cloud infrastructure. We need to make sure that different developers can access that infrastructure, that we're using the correct development environment, we have the correct dependencies installed. And so all of this is just introducing a lot of chaos if you're trying to manage this all in an ad hoc way. And that's where kind of the field of ML ops or ML operations comes in. And there's a lot of tools that exist out there in the world that can help with this. One such tool that I'm going to talk about more and that we used is called MLflow. This is, from my understanding, kind of the biggest, most prominent open source tool in this area, but there's a million other tools. If you are alive and paying attention, you hear about AI and machine learning every day. And of course, Silicon Valley is doing a lot of development on these tools. And while us in the scientific computing world, I think, are actually using AI and machine learning to solve useful problems, which is not always the case in Silicon Valley, we are often, I think, behind the curve in terms of the tooling. And so let's just dive in. And I wanted to demonstrate how MLflow works. And this is going to be similar to other tools in the space to start reining in this chaos a little bit. So as a demonstration, I created this little toy problem. It's just a very simple classification problem. We have two things. We want to classify them. One is thing one, it's blue. Thing two is orange. So if we wanted to develop a model for this, super straightforward these days. I'm using scikit-learn, but you could use any number of popular machine learning libraries out there. It takes a few lines of code. We can train and fit a model, in this case, a k-neighbors classifier. And then I've plotted the predictions that this model spits out and did a pretty good job. You can see some points that were wrong here, and you could compute some metrics like accuracy, recall, whatever makes sense for your case, and save those somewhere. But now if we want to develop multiple models and compare those models and share any pre-trained weights across the team, we start to get into that chaos that I talked about earlier. So let's pull MLflow into this. So adding just a couple lines of code, I'm able to do that. And MLflow is integrated with pretty much any popular machine learning library or framework out there. But it's also highly customizable. So even if it isn't directly integrated with your library, that doesn't mean it's not still going to be useful. But when it is, we can just use like this auto log function, and MLflow knows about scikit-learn. And so when I call model.fit, it's going to automatically log a bunch of parameters and metrics that it's computing, and then you can also log anything else you want. So as an example, I'm logging that plot that I showed earlier with the predictions. Let's look at what this all looks like in practice. With the code that I just showed, this is going to save all of that, those metrics and parameters and everything to your local file system. And then you can run the MLflow UI locally, and it'll pick up those results, and you can browse them in your web browser, just at a little localhost endpoint. And so this is kind of the entry point. And if we dive into, you see this run right here, which is created by that code I just showed. If we dive in there, we can see some of what has been logged here. So there's a bunch of parameters here. These, if you look at like the scikit-learn API docs, you'll see what all of these parameters mean. But then it's also computed all of these metrics like accuracy and precision and recall. And I didn't have to do any of this. Scikit-learn automatically does this when it's training a model, and MLflow knows to pick that up and log it. And so then we can also go over to this other tab called artifacts. And here MLflow is logging things like the actual model itself. So you have a pickle file here. You could just load that model anywhere. Any developer who has access to this could load that model. You also have some descriptions of the code environment and the dependencies that were used. And then you can also see this plot that I showed earlier has been logged, and it's associated with that specific version of the model, as well as all of the metrics that we used while training this model. And so this becomes really useful when we start using more than one model. So here, previously I'd used a single k-neighbors model, but what if we added a neural network or a decision tree or a support vector model? Now all of those are logged here. We can see all of those different models, and then we can also compare them. So if we just hop over to this other tab, MLflow automatically created these plots. I didn't have to do anything. And we can see how all of the models compare across a variety of different metrics. So now it's going to be really easy as we're in our development process to pick the model that's working the best, pick the parameters that make that model perform the best. And we can keep track of that throughout the process. It's really straightforward. So these tools like MLflow, we can go a lot further with that. I think the example I just showed, running everything locally and just storing it on your local file system, is honestly an improvement over a lot of processes that I've seen in the world, and could be good enough. But there's a lot further you can go. You can, like, for example, we run a remote tracking server. So this is a server that we can interact with. We can all go to a web page that looks just like that UI that I showed. And it's storing all of our model weights and other artifacts in cloud storage that we already use. We hook it up to a cloud bucket. It integrates with our existing tooling super easily. And then there's also deployment tools. So we can package a model together with whatever code environment it needs to execute. We can avoid, if you're managing multiple models that require different machine learning frameworks, you can get into some dependency nightmares where you have conflicting dependencies and they're really hard to solve, but we can just package a model together with its dependencies. We can deploy that remotely, and we can interact with it through MLflow directly. And again, I want to encourage people, if you want to start learning about some of this ML operations and managing your machine learning processes better, find the right tool for you. I've demonstrated MLflow. It's a popular one, but it's far from the only one out there. And it's also, you might find that just an ad hoc process is sufficient for your team. And that's also fine if you have a fairly simple use case. But I think it's important to still think of some of these core questions that we're trying to solve here. So those are, how are we going to share a model with the rest of our team? How are we going to evaluate the model as we work and keep track of the results? How are we going to run our models in our production environment? And how are we going to handle updates going on in the future and make that process smooth and painless? So that's a little bit about our journey into this. It's a wide world, and there's a million different ways to go about it. I encourage people who do explore some of these tools, don't get overwhelmed. There are so many features. A lot of them you don't need probably, unless you're Google or OpenAI or something. So figure out what works for you. Use just what you need. Don't get overwhelmed. And just quick shout out to some of the great people who have sponsored and collaborated with Catalyst over the years. And I think I'm open to questions now.
Thank you, Zach. Any question?
Hi, thanks for the presentation. I enjoyed it. I was wondering, since you focused a lot on ML operations, do you still think these tools are worth exploring for like one developer working on a, kind of iterating on a model? Is it worth the kind of initial setup time for some of these tools, or is it not really worth putting in the effort to get it started unless you're working on a team or deploying it operationally?
So I think it absolutely can be. The example that I showed there would, I imagine, be super helpful for one developer. Just so during that process, you have everything organized. You don't have to, create that organization yourself. You don't end up in a situation where you're like, wait, how did that version of the model work? I overwrote the result somewhere. How can I recreate that? Even if it's just all on your local system, like it might not be backed up remotely and you might not be able to share it with other people, but I still think that could be super useful. And it's really easy to set up in a local environment like that. A lot of the complexity comes when you try to do some of the more, cloud-based remote deployment stuff.
Thanks.
There's a question on Slido. Were there any unexpected tricky parts of setting ML flow up?
Yeah, I think the process of, again, getting that remote deployment up and running was pretty tricky. Unfortunately, like, so many tools in the tech industry, while MLflow is an open source library, they do tailor it a lot towards some like hosted solutions, in which case I think it would probably be a lot easier. But setting up a fully open source kind of self-hosted situation proved to be a little bit complicated. And then I also found there was some complications in getting MLflow to play nicely with some of the other tools in our personal tech stack. And so I do think trying to keep that isolated sometimes from your other development environment can also be useful.
Yeah, okay, thank you. Yeah, give Zach another. Yeah, so another question.
Yeah, just real fast. For the kind of the ML flow visualizations and everything, and just the tracking of the model progression, is that something that you're pretty much just using internally, or do you expose that to your end users at all? And if so, what is that like?
So right now we are just using that internally. So we have this web UI that any of our internal developers can go to. I think it would be great to be able to expose some of that to external users or to external developers. Again, we are an open source project. We haven't really quite figured that out yet, because I think there's just a lot of potential. Like, we are using MLflow to host big models and pass a lot of data around, and we don't want to just put that out to the wide world and incur crazy costs or have weird permissions, things that we need to get figured out. But I would certainly be interested in trying to make that work someday.
Thanks.
Thank you, Zach.
Thanks.
Next speaker is Edward Hartnett. He's from Nova. He will talk about using AI in earth science programming.
Hello, everyone.
So great to see so many people interested in improving scientific software today. I was thinking, and I don't want to sound nostalgic, I was at the very first one of these, the SEA first meeting at the Hill at NCAR. Is anyone else here in this room was at that meeting? Anyone at all? I'm the sole survivor. I win software engineering at NCAR. I believe we have a prize for that. Is that not, we have a prize, Brian? Some kind of vacation? No, I'm being told we don't have a prize for that. All right, let's get down to it. I'm here to talk about using AI in your earth science programming. So we're not talking about predicting the weather with AI, but just being better programmers with AI. First question, who's used ChatGPT in this room? Lots of people, so you all know about it. So you know I can use it to write haikus of questionable artistic merit. However, when I put in this prompt about a Fortran NetCDF program, it gives me a correct NetCDF program, which is impressive. And if you imagine someone who has no experience of NetCDF, if we can even imagine such a thing, this would be very helpful as a starting point, right? A couple things I want to point out is that when you ask it to program, it usually will sum up what it's heard from you. And it's important to read that because that is how clear were your instructions. And then after it writes the program, and I've cut that out, at the bottom, it kind of sums up and suggests further steps. Okay, and these steps that it suggests, let me know if you want to add global attributes, write sample data, or define coordinate variables. These are good steps. If you're writing a NetCDF file, this is exactly what you want to be thinking. So very useful. Okay, who's used Notebook LM? Anyone? Less people. Notebook LM allows you to upload documents, okay, and it provides what's called a RAG, a retrieval augmented generation. So the LLM, the large language model, will answer your questions, but in doing so, it will look at the documents you've uploaded. Okay, so here I uploaded all my many presentations to NOAA about NCEP libs, and this Notebook LM can now answer all kinds of questions about NCEP libs. So very useful for training. It does a 15-minute podcast about the topic, which is surprisingly entertaining. I won't play it now. But what I will play, oh, I don't have permission to play this file. Will that not work? I'm sorry. We can't play my video. Okay. Video generation also works. And I have here about a 1.5-minute commercial of why you should use unit testing in your software. And it's probably more effective than all of the dozens or hundreds of presentations I have given to NOAA about that topic in the last 10 years. So it's a shame you can't see it. Maybe we'll play it in a little bit. We'll figure out. Okay. Machine learning has been around a long time, but what has come along recently are called large language models, and that has revolutionized the field. And they're not magic, but they seem very magical. These diagrams are from this excellent book, which I highly recommend to all programmers, Build a Large Language Model from Scratch. Takes you through it, building ChatGPT-2 from scratch in Python, and it's very, very informative. Two very important concepts, tokenization and vectorization. You should understand these even if you're just using LLMs. So when you give it text, it takes that text and it breaks it down into tokens, which are words or subwords or punctuation marks. And it assigns a number to each of them. So each token gets its number, okay? That's tokenization. Then the next phase is it goes into a database and it assigns to each of those tokens a very large vector of numbers, like 1,024 numbers for ChatGPT-3. The vectorization is determined by neural networks separately, but it contains information about the meaning of the token. And we can't visualize a space of 1,000 dimensions, but if we put it down into a 2-dimensional space, it's something like this, in that related concepts are grouped together in the vector space. Okay, such that by looking at the vectors of 2 tokens, the LLM can determine how closely related those concepts are. The key insight for LLMs came from language translation. And if you are familiar with any foreign language, as I am not, you will know that the wording of sentences is different between the languages. So here's an example from German to English. And you can see that if you translate the sentence word for word, you get an English sentence that is not correct. In order to translate it correctly, as shown in the bottom diagram, you have to know these words are important, right? The words at the end of the sentence are important in the middle of the sentence, and the words in the middle of the sentence are important at the end of the sentence. And you have to keep attention on important words until you finish the task. And that is done through the transformer block, which is shown on the right, and in particular, the masked multi-headed attention block in the middle. This is consisting of multiple large neural nets that pay attention to all the words and keep track for each word. How important is this word? Okay, so this keeps the attention on the words. And then when it determines what to do, it looks at, okay, what are the important words I should be looking at here? So I don't know if who's familiar with neural nets? Computer people will certainly be. This is a super small one. It has 4 inputs and 3 outputs. And the way it works is each of the inputs is like a floating point number. And then you have these hidden nodes. At each hidden node, it determines its value by taking each of the inputs, multiplying them by a weight, and then applying an activation function that either makes the neuron activate or not. And this propagates through the whole network. So you can see there's a tremendous number of calculations. Okay. What I'm showing you on this slide has 3 hidden layers, 4 inputs and 3 outputs. In ChatGPT-2, it was like 768 inputs and outputs and 12 hidden layers. So much, much more complicated neural net. Okay, how will all this help us code? Who's heard of vibe coding? And wow, guys, you guys need to get on social media more. Vibe coding is when you code without programming. You just talk it into the machine and the AI codes for you. And if you go on Google, YouTube, you can see a bunch of people showing the games and stuff that they wrote with vibe coding. There's several competing LLMs who specialize in the code space, and they seem to change ranks, month by month. So any of them are probably good. Most of them have a free plan, but usually pretty quickly you run out of free and you sign up for the $15 a month plan. And they can write working code based on text or voice input. I'll give you a little example later. They can fill in documentation and testing. They can manage your build system. They can do many, many things. It's very, very helpful. Here's an example. I use Codium, which is a windsurf. It's a clone of Visual Studio, which uses the Codium backend to do the AI, but it's similar to the other ones. So here I write a unit test. I instruct it to write a unit test for one of the grid functions in an OL library, and it does so. And it adds it to the build system, and it explains to me what the test is, and it will add documentation to the code. And this results in a working test. Very useful. One of my colleagues, Alex, used one of the LLMs to write tests for the W3 EMC GRIB1 library. And these were the prompts that he used. And the point is that it will give you something, and then you need to look at it and work with the AI to tune it to what you actually want. And that's what Alex did over these different prompts until finally he got the test that he wanted. He used it to create a bash script to do something. He wanted to create a bunch of oxygen documentation that he would have had to do by hand. It would have taken him a couple hours. Instead, he told the LLM to generate a script to do this. It did. He ran the script, and it worked well. Another thing Alex is exploring, which is great. We do everything at NOAA. We do it on GitHub, and so he wrote a GitHub Actions action, which will take the diff in a PR and we'll upload it to the LLM and ask it to look for bugs or whatever. And it will then upload back its evaluation of the PR. Very handy. And it gives this kind of result. Now, when I read this, I thought the primary beneficiary of these is going to be the programmer who put up the pull request, because you put up a pull request and this appears, code review summary, and you read it. And if it doesn't match what you thought it was supposed to match, then you just found a problem, right? Okay, this is my second to last slide. It used to be that I would give talks about legacy versus agile, but now there's a third column on my slide. If you are a programmer who does not write unit tests for your own code, then I regret to say you are a legacy programmer. You are 25 years and 2 revolutions in software engineering behind the times. So it's time to catch up. Legacy code is characterized by no unit testing. If you don't have unit testing, almost every advanced software engineering technique is closed to you. That's the ABCs, that's the basics. So if you do that, you can bring your productivity up to the middle level, agile. And in agile, things move about 5 times faster on most projects, in my experience. Things that take about a week in a legacy project will take about a day on an agile project. And agile will result in much higher quality code. It's much better tested, much better documented. Generally much stricter quality. It's difficult sometimes to get legacy programmers to code up to the agile level. In fact, that's a key difficulty in transitioning from legacy to agile, is developers who cannot perform at the higher level. Okay, so then when you add AI to the mix, it takes everything up another 5 times in productivity, in my estimation. Because the AI now handles simple tasks for the programmer. If you need to do something to the build system, add a new test, add a new file, something like that, you just tell the AI. The AI does it correctly for you. You don't have to look up CMake syntax again and check that again. It can build tests for you. It can document undocumented code. And it does it to about, in my experience, 80–90% accuracy. So very, very good first draft of undocumented code. Very good first draft of tests. Still need to be refined by the programmer. Using AI for debugging is significantly faster. Take your exceptions or your error reports and put them in the AI before you even read them. Let the AI read them, and maybe it knows the answer, and you don't even have to figure it out. In my experience, the AI is getting the correct answer there 80% of the time. So that's a significant savings in debugging. What becomes more important for the programmer is managing complexity. It's always been important. Now it's more important than ever. The AI can add tremendous amount of code to your code base, and it's up to you, the programmer, to manage that complexity and make sure it doesn't get out of hand. But what becomes most important is imagination, creativity, and knowledge and direction. Because the AI can do anything, but you have to tell it what that anything is. So you have to be the one who figures out what your software should be like, and then the AI can very quickly help you get it there. And I would say that in each of these, from legacy to agile, from agile to agile plus AI, the requirements on leadership have gone up. Okay, legacy software leadership consists in going to meetings and explaining why your software is late. When you take it to the agile level, now leadership is responsible for making sure that there are tests, that there is continuous integration, that every programmer gets a pristine code base to do their work on, so they have the best chance to succeed at it. And that's a management responsibility. When you then take it to the AI level, similarly, management is even more responsible for selecting the correct AI tools, making sure that programmers can use them effectively, and making sure that everyone is doing it correctly so that we get a good code base that can be maintained. Because AI can spin up a lot of code for you, but when you have to maintain that code, then that can be a problem. Legacy programming started in the 60s when modern languages were invented, Fortran and C, if you can call them modern. Agile programming started in the year 2000 with the Agile Manifesto. Agile was really programmers self-organizing management because they realized finally that business managers were never going to figure out software. And so Agile was very much developed by programmers for programmers. And AI just takes everything up to a whole nother level. And I would say that with a day of programming in AI, I can achieve what took me a week in Agile or a month in legacy programming. So again, if you're still on the legacy side of this slide, it's time to move on. Okay, final conclusions. Programming has changed again. So as programmers, we always have to keep up with the latest technology, and technology has just undergone a dramatic transformation. So keep up or get left behind. Those are your choices. They're talking about a 10 times productivity improvement. I don't think that is crazy talk. I think for many programmers who are already programming well, who are already programming with great agile discipline, and who already have figured out how to concentrate for long periods of time, AI will bring a 10 times productivity improvement. And it's very, very fun to program with AI. I love it. Okay? Agile practices are more necessary than ever. If you neglect them, your code will rapidly spin out of control. And finally, the AI always must be supervised. It's a very enthusiastic and ignorant assistant who will do things for you very quickly, but not often very correctly. You have to monitor it. You have to select small tasks, make sure they were done correctly, and then move on to the next task. But if you do that, it's a tremendous time saver. Thank you. Any questions?
Yeah.
Question is regarding the IPR issues. If you're using someone else's code given by the AI to you and you're using it, so do you intend to declare that this part is generated by AI and I'm using it, I'm not responsible for it? Or what is the UCAR policy for that?
I can't speak to UCAR policy. I work for NOAA, and I don't know if they've specifically addressed this in their policy. However, my policy is that every programmer is still fully responsible for their own code. So if the AI helps you generate the code, that's no different than if Emacs helped you generate the code, right? It's still your code. Thank you.
So there are several questions from Slido.
Oh, yes.
Do you have any recommendations on how to navigate using AI with the knowledge that is very helpful, but is also very detrimental to our environment and the plane?
That is certainly a very interesting and thoughtful question, and I certainly do not have the wisdom to answer it. I am using AI for science programming. I hope that is a sufficient justification. Whether it is or not, I suppose, is something we all have to individually decide.
Second question, just want to add to your slide about AI-based code review. GitHub now lets you request a review from Copilot. I tried once and it suggested too good, but small changes. One hidden behind low confidence.
Yeah, GitHub is using Copilot, which is one of the major programming LLMs, and you can get to it right from the GitHub page. You don't even have to use a special editor. Give it a try and see how you like it. You know, as with everything, it's giving you suggestions. It's not telling you what to do. It's giving you suggestions. If you find them helpful, then great. If you don't, then you just don't take them.
Can you speak to your experience or therefore with AI hallucinations?
Yeah, AI hallucinations are caused by the following. The LLM, the large language model, it is trying to say things that sound like the right answer to you. That's all it's trying to do. If it is coincidentally the right answer, that's great. But what you know is going to sound like the right answer. Okay? So hallucinations are when it gives you something that sounds very reasonable, but in fact is completely made up. That does happen. If you ask it to write too complex a piece of code, it will make up functions. It will make up libraries that look very real. In fact, it did that for some netcdf functions, and I was like, wow, we should put these in netcdf. They're good functions. But that's AI hallucinations. The way you control that is you give it small enough tasks so that that does not come into play, and you monitor carefully the output of each task.
The last question, that's what I want to ask too.
Yeah.
Has programming with AI been successful in legacy spaghetti, millions of lines of Fortran code base we have in weather forecasting, at least in improving the quality of the code, also the PIO?
PIO?
I'm just in, just Fortran can deal with all those legacy code.
Well, I was a co-author of PIO, and that is certainly not millions of lines of Fortran spaghetti code. In terms of the millions of lines of Fortran spaghetti code that weather forecasters have indeed created and endured these many decades, AI will be much less helpful because that code is much less organized. So AI will not organize your code for you. You should have done that already, and you should start doing it now. However, AI will help a lot in documenting undocumented code and writing unit tests for untested code. And what I would suggest is that everyone who is working on a legacy project rapidly transition to Agile while you can, because you're falling behind the whole rest of the world here.
Hi, I'm a research software engineer from Berkeley Lab, and I work with a lot of scientists that maybe still do develop in a legacy manner. Do you have, and my team and I, we try to encourage them and we try to introduce them to more agile techniques, but we often face issues, well, not issues, I'll just say that they often express a lot of discomfort with adapting the agile practices. Do you have any advice for how to help people that are uncomfortable adapting?
The only way that I have ever succeeded in imposing Agile on legacy programmers is by being their manager and telling them it was now their job and there is no alternative. Right. So you need to go to your leadership and you need to say, if this is important to you, then you need to direct your employees to do the job the way you want them to do it. And if they can't, then they need to find other employment. And if you're not willing to do that, then I guess, you're not going to get it. That's what I find. It might sound harsh, but, 10 years of NOAA have shown me that. Dom.
So you kind of mentioned this, but you can't use AI unsupervised. But the problem is, of course, if you put this everywhere in the workplace, people forget about coding themselves. So how do you make sure that programmers have the knowledge that they need in order to supervise AI in this world where you can just throw everything at ChatGPT and then it comes back and you stop thinking about it and you forget about how to do it right?
I think that what we've seen in our lifetime is the evolution of software engineering from something that could be easily done on an amateur level, even in a professional setting, because that's all we had. And it's become more and more professionalized and specialized and difficult over time. So that if you're talking about legacy programmers, in my experience, the biggest challenge with legacy programmers is a reluctance to learn new tools and new ways of doing things. They want to keep doing it the way they did it in grad school in 1990, and that won't work anymore. So the answer is that those who cannot perform at a professional level should not be employed at a professional level. And if you're going to try and be an amateur, then you should be an amateur, but not take precious science dollars and be a professional. So I would say anyone who's got a job and their job is software development, it is their responsibility to learn how to use the tools of the job. And if they can't do that, then they should find other work. That may sound harsh. I've been called stern for this attitude at NOAA, but that's how I feel. This is important software, and it's not a jobs program for scientists, right? It's supposed to be a important software that we develop together for the nation. So therefore, if you can't contribute to it, then you shouldn't be on it.
Thank you. And for the record, I agree with you.
Thank you. Controversial NOAA talk here, people.
Thank you, Ed. Yeah.
Any other questions? No? Thank you all.
Our next speaker is Daralynn Rhode. She will talk about IMAP data access API, functionality improvements and usage for better data management.
Okay, hi. Thank you for having me, and ISS for providing me the opportunity and the support. My name, again, is Daralynn Rhode, and this is my talk on the IMAP Data Access API, touching on its functionality, improvements to be made, and its usages for better data management. So just a quick overview of what I'll be talking about. I'll have a brief background to provide some information, and then what features have been added to the API, the impact this will have on data management, and the future work that is slated to be done. So just some quick background on me. I am a current junior at CU Boulder studying computer science and astronomy. I work as a student developer at the Laboratory for Atmospheric and Space Physics, or LASP for short. I've been working here since June 2024, so almost a full year. I've absolutely loved the work that I've been doing here. I function as a student intern on the Science Data Center, or SDC team, for the Interstellar Mapping Acceleration Probe, or IMAP for short. My work here has consisted of introducing pre-commit checks to an already existing code base and assuring that all the code complies, general debugging work, and my main work currently has focused on expanding the existing data access API to make it more user-friendly and improve its functionality. In this talk, I'll walk you through how the IMAP Data Access API improves data management for space research and how we're expanding its capabilities. So, some background on the mission. IMAP is a NASA mission launching in September 2025 to study the boundary of our heliosphere, the region where the solar wind meets interstellar space. There are 25 institutions involved, and the Science Data Center is in charge of managing all the data levels and its processing for all 10 instruments on board. As space missions collect increasingly complex data sets, scientists need better tools to access and work with the data efficiently. So this is just an image of the 10 instruments on board that will be going up that the SDC is in charge of managing the data and processing for. So this is where the IMAP Data Access API comes in. It enables researchers to interact with mission data stored in the cloud, making it easier to query, retrieve, and analyze it as soon as processing is completed for the desired files. Improvements are, of course, still being made to it, but it is currently being utilized by the science teams for the mission and by the SDC internally for the processing systems and access and upload files. So, and this is just a screenshot of the IMAP Data Access wrapper for the API, the GitHub repo that it's stored in. So now to talk about the current features and enhancements being made. APIs, or application programming interfaces, act as intermediaries that allow different software systems to communicate. The API is designed to provide fast, structured access to mission data that is stored in an, this is going to be long, in an Amazon Web Service Simple Storage Service bucket, or you can just say an AWS S3 bucket. Users are able to upload, with permission, download and query the data files in the S3 bucket. Querying files can be done by any combination of instrument, data range covered, data level, version number, ingestion date, descriptions, file type, etc. that pertain to that specific file. Currently, the API caters to science files, which are the L1 through L3 data products. But support for other file types, like ancillary, will be added soon, as well as some other files. There are 3 ways to access the API. It can be used through a command line interface after installing the package, or it can be imported directly into files through a Python package. And then calls can also be made directly to the REST API. This is the endpoints for the command line interface. Download, upload, and query being the main 3. Query, of course, has the most support and functionality to it. One key improvement is enhanced query functionality, making it easier for users to filter and access specific data sets. We are constantly taking input from science teams to find what fields are the most interest to them. A few of these new features include a versioning latest flag that returns the latest version of a file matching other specified fields. So whether the scientists know exactly what they're looking for, but they don't know what the most updated file is, they'll be able to flag it, and the query will return that exact updated file. In addition to searching by a range of start dates that the data covers, users are also able to search by a range of ingestion dates from when the data was processed. Another major enhancement is my current work of the moment, which is the introduction of ancillary file support. This means researchers will be able to upload, download, and query supplementary files alongside the primary data records. Now, why does this matter? Ancillary files contain mission metadata, calibration details, or background context essential for accurate analysis. By integrating these files within the API, we ensure a smoother workflow for scientists, reducing the time spent searching for relevant data. Here are the query parameter endpoints. Right now, ingestion date has not been added to this set, but that's currently in development. So you can do anything from instrument, data level, the descriptor of the file, start date, end date, which is just end to the start dates. It's not actually like the end date of a file. Repointing, version, file extension, and then if you know the exact file name of a file you're looking for, you can also search up by that. Here are a few example queries. See, this first one is using the command line interface, and it's just a generic search for the SWE instrument. I'm blanking on the name of it, but yeah, so you can search it up and it'll bring up all files relating to that instrument. Here's another one, which is a more refined search. So you know what instrument you're looking for, your data level, start date and end date. With these files, it's just the version number that is differing for all of them. And then this is with the Python package. And so this is something that can be installed and imported in, and it will return kind of this longer format for all your queries. Yeah. So now for the impact this will have on our data management. IMAP mission data is categorized into L1, L2, and L3 products, each level representing a different stage of processing. For context, L1 data is raw, unprocessed telemetry from instruments. L2 data is calibrated but still detailed, and L3 data is fully processed and ready for scientific analysis. In addition to data levels, each file also belongs to a specific instrument with the version number attached, as well as a description, start date, and plenty more metadata attached to it. The API is not only used for accessing data, but also for searching for it too. Not all parameters have to be provided to run a valid query against the database. So if a person wants to see all level 2 files for the CODICE instrument, the API will return to them a list of all those files. By improving the API functionalities, it is made easier for scientists to locate and retrieve the exact type of data they are searching for, or a broad range of data matching certain parameters. With cloud-based access via the API, researchers can now quickly locate the data they need using structured queries, retrieve datasets without downloading unnecessary files, and work more efficiently by automating data requests. The API wrapper is designed to be as lightweight as possible. It has minimal overhead on the client side. Most of the processing and heavy lifting is handled by in the AWS server, yeah, that's the word, which manages the backend operations efficiently. This reduces the burdens on users by optimizing the interaction with the API. As a result, developers can focus on their work without having to worry about complex infrastructure or resource-intensive tasks. So, future enhancements that are coming up. Some upcoming features that are either in development or are still slated for work are to add in support for querying ancillary files, like I said. This will mainly focus on switching between database tables and ensuring the query functionality is versatile to support the switch. Other work will be adding full support for SPICE files, SPICE standing for Spacecraft Planet Instrument C matrix events. An actual production instance will also need to be created or deployed in the future. And we are wanting to add more internal logging and tracking for events to more closely monitor activity. Right now it's a little bare bones, so we just want to amp that up. And of course, any requests that come from the science teams, we are happy to facilitate with them and take those into account. Just to touch on the bigger picture of the open source science that we're doing, one of the most exciting parts of this project and working with the IMAP Science Data Center is its contribution to open source and accessible science, and the possibility of contributing to continuing improvements in space mission data access. Open source projects, particularly in the field of space exploration, are essential for ensuring that scientific data and research are available to everyone. This is especially exciting for me as a college student who jointly studies astronomy and planetary sciences, because it means I'm not just learning from existing data, but also contributing to the creation of tools and platforms for future research. Then, just to recap and summarize, the IMAP Data Access API simplifies how scientists interact with mission data. New enhancements improve usability, querying, and file management. And future updates will make access even more efficient. Ultimately, the intent is to make science data more accessible and manageable so researchers can focus on discoveries rather than data logistics. And here are some relevant links. I did not get on the bandwagon with the QR codes, so sorry. But these are websites to the mission website, the Science Operations Center GitHub repo, and then the Science Data Center personal website as well. Thank you. All right.
Thank you, Daralynn. Any question? So I have a question. For new person never access those kind of data before, how can I start?
If you go to the GitHub repo, it'll have instructions as to how to interact with the API with those 3 different options that I mentioned, with the command line and then the Python package, and then the direct calls to the REST API. It's pretty simple once you install the package, and then the help menus kind of help you along as to how to make calls and queries to it as well.
Okay, so I even don't know like which instrument or what time should I like look at, but that guy can guide me through.
Not so much, because right now it's still in development, so there's a lot of mock data right now in the database, but really it's very versatile in how you can play around with it to find out the other parameters that you can search by. So the basic parameters for like instruments are provided to you. So with that background, you can just search by instrument and then find out how other parameters apply.
Okay. Another thing that can it be accessed from HTTP directly?
I don't. Yes, you can. The calls are done through HTTP responses and stuff, so you are able to.
Oh, so there is such a like a help me to like using HTTP with all the JavaScript commands.
Yeah, so we have some basic documentation detailing that. Of course, it's still in the work, so as changes are being made, the documentation is being updated and more fleshed out.
Okay, great. Thank you. Any more question? Okay, thank you, Daralynn. Before we go to lunch, Brian has something to announce.
Yeah, nothing super exciting, but just wanted to give a couple of reminders. So I posted this in the Slack. We'll have a networking session, actually 2 kind of parallel networking sessions at 3 p.m. today. There'll be an in-person one for folks who are here. That's going to be based on sort of the voted topics that are on the whiteboard, I believe, still out there. And that'll also have some like light refreshments like we've had for the breaks. So hope you're able to join for that. If you're virtual, we're also going to do a virtual networking session in Zoom. So it'll just be in the same Zoom room. I think we'll take like a 5-minute bio break after the tutorial ends at 3. So I'll lead that and we'll reconvene at around 3:05 for the virtual folks in that room. And then the only other thing is just a reminder that a few of us are going to get together at Rosetta Hall this evening for like an informal social event and dinner. That's like a kind of a food court thing. So if you're interested in that, just sign up. The link's on the Slack, and we can coordinate like rides over to Pearl Street where it is. So yeah, otherwise enjoy your lunch, and I'll see you at 1.
Yeah, thank you.
Yeah, if I'm like reading not doing this, I don't know, I can't do it.
Feel like I feel if there's people over there though. Otherwise, now I'm starting to think that maybe I would just stand. Yeah, the whole room. Like maybe I would just. Throw the button. I remember that. Yeah, watching like throwing. Yeah, I remember that from the last time you guys here. If you're in here, Yeah, I can still. Yeah, I can hear my voice in here, so as long as people. Oh, look at that. I was just gonna ask, like, you're a little taller. Can you cut my feet off? Or, yeah, it's just. Yeah, but. Oh, yeah, I'm gonna do that. Oh. I remember it. She moved on. Oh, okay. I remember Tasia. Yeah, yeah. Okay, so it's center second. If anybody. No, it's just me. It's gonna be pretty loose. I spent my time, but I didn't not have a lot of resources. I could do a live. There's just gonna be one spot in there where I'm. I do like what I'm talking about is basically everyday level. Yeah, hopefully, so. Just going through here and then I'm probably just gonna share. Yeah, it's just gonna be my desktop. I have slides I'll show a little bit there. Yeah, I'm mostly gonna go. Except this. Kind of walk through. That's my core thing that I want to get across is that, and then I have a million things that I can branch out to. So that's kind of why I'm like, I don't want to go off this stuff. Check, one, two, check.
And I guess, for the people, if somebody does want to weigh in.
Check.
Maybe just. I don't think we have.
Check.
Yeah. Use some mics.
Yeah, check. All right. But yeah, I got like one. I don't want to. Are we waiting until 1? Okay, rather than like dry run. Okay, you can go ahead and share. Yeah, because I can show you the. I don't know if you're. So this is the user. Yeah, okay. He told Andrew. But I can submit a ticket too.
Yeah, I was gonna, I mentioned to him, but now I can mention to you. I think I put together for him.
Yeah.
Be happy to submit an APAR if that's.
Oh, sure, yeah. Did you just do it, or did you look at how we do it and
Yeah, I
do it
kinda
based on that? Yeah.
Cross-reference what and sites we're doing and this.
Okay.
And what made sense to me under HR. But, I don't know that it's necessarily optimal. I'm sure that's one.
Yeah.
At least it seems to.
Yeah, okay, yeah. You know,
Good baseline.
okay. Yeah, I can. Thanks. I'll show up.
I mean, I figured. Good angle.
Yeah. Honestly. Stop.
Excited for that, but
I'm worried about how much it changes. But I'll talk a little bit about that. Yep. But it's automatically. Oh yeah. Yeah, you can automate.
yeah, I'll go outside and try to wrangle.
Sure, okay.
For you.
Yeah. Okay. Okay, cool. Okay, thanks.
think that's. I think in some ways it's maybe easier. Yeah, Sarah's. Actually, I know, and that's. Yeah, and the only one ever used to say people want it and they just. No, I know, and it's like 120 words. So I mean, it's easy. Right, like right around. Questions to go nice.
All right, I think we might be gathering a few more people. If people online are waiting. I think we're, what is it, 1:04? We're gonna start in maybe a minute or so here. I think there's an effort to get some people in from the hallway or outside. since we're just coming back from lunch. All right, I think I might start talking though, if people can fill in while I go through some introductions and whatnot. Is it fine if I start, I guess, or are we in the back? Is it fine if we start? Good, okay. Great, okay. So my name is John Rhode. I work at the National Renewable Energy Laboratory in Golden, Colorado under the Department of Energy. So I came up to give you a tutorial on a bunch of stuff that I wind up working on most of my days at NREL. So mostly I am like kind of a performance engineer. I mostly work on CFD, like computational fluid dynamics applications. Mostly for the past 7 years, I've been doing combustion energy and wind energy. So mostly we had to develop a lot of stuff for our project called ExoWind, where we were doing wind energy simulations. So we have a lot of complicated software there. So I'm going to go through kind of how we've tackled development on that project. So I guess, yeah, I was mostly doing performance engineering for like GPUs and things like that. I'll show a little bit of videos, I guess, because I always like an excuse to show some of the stuff that I was working on. And we have a really good visualization department at NREL. So here's a combustor. I don't know if this is probably doesn't show up very well for people online. I guess it's smooth on my computer, but not on anything that anybody else is looking. This is 60 frames per second, but but it's only like five frames per second online. Oh, it's lagging. Anyway, so this is a CFD application for SCO2 combustor, so supercritical carbon dioxide combustor. And then I have one where we did so mostly for the last 7 years, I was working on the exascale computing project underneath the Department of Energy. So this was our grand challenge problem that we did there. So we were simulating a combustion engine, injecting fuel into this low temperature combustion engine. So that's the type of work that I typically do. So rather than the videos showing up, maybe I can show some images. Oh, I want to go here. So we do a lot of wind farm simulations. So these are some images of 2 of the projects that I work on. I showed you some of these videos, but try to get the wind ones up. So we do like fully blade resolved wind turbines, and we try to do a lot of them. So we need a lot of large supercomputing resources. So anyway, I just thought I would go through some of those. I'm trying to get to the good. There's a good ExoWind one. So I'm going to focus on I'm going to be talking about SPAC. I'm going to be talking about how we use SPAC mostly for development, but a lot of other things. So we really needed it for this project that I'm showing here, this project called ExoWind. So ExoWind is an extremely complicated project, and I'll show you some slides in a second, how much software we're actually dealing with there and why we needed to develop it. But I want to preface my whole tutorial and say that we could not finish this 7-year project that was this complicated without using SPAC for development, in my opinion. In the last year of the project, I think we cracked how to iterate and develop with all our developers with how complicated the build process was, to the point where everybody could go off on their own and build stuff. And I'll go through some slides to show you kind of how complicated that build process is. So I'm going to preface all this stuff just for a minute here. So this is a slide that shows what we were actually dealing with in our project and why we wound up using SPAC for development. So this is the like DAG. I'm going to be talking about directed acyclic graphs in the idea of SPAC. So we I call it a DAG, D-A-G. So this is the DAG for the dependency graph of our XWin application. And there's a lot of stuff pruned out of here. So the things that are circled in red here are the applications that we were developing all at one time. So we were developing this application called OpenFast. We were developing Hyper, which is a linear solver library. We were developing Trilinos, which is from Sandia Labs that has a bunch of solvers and a bunch of things for doing meshes and stuff. We have our own application called AMR Wind. We have this Tioga application that works between these applications, AMR Wind and Nalu Wind in our application. So, and then we have this driver on top of all of it. So we had this stack where developers were developing these 7 packages all at the same time in this hugely complicated software environment. So with all that like motivation out of the way for what we were doing, is there anybody in here who isn't familiar with SPAC? Okay, we have a couple people that aren't familiar with SPAC. Okay, so I'll go through a little bit of like what SPAC is at the start here before I actually go into like my tutorial. So let me look at my outline here. So I gave an overview of myself, overview of XWin. So I'm going to give you a little bit of an overview of SPAC. So if you want to know about SPAC, the best thing to do is to go to spac.io and you'll see this web page. So SPAC is really a package manager. So it's the supercomputing package manager. It's kind of more than just supercomputers at this point. SPAC is a very large project. Maybe we'll go to the GitHub site and I'll show you how large the project actually is. It's a very international project at this point. I would mention for cool points that I've been using SPAC since it started in 2013 and 2014 is when I started to use SPAC. So I've been using it for a very long time. So if we go look at their project on GitHub, there's 40,000 commits on this. There's 4,600 stars on it. It's international, all over the world, people are using SPAC. So it's a very popular project. It's also under the HPSF, the High Performance Computing Software Foundation. So it's under the Linux Foundation now. So it's branched out. It came from Lawrence Livermore National Lab, but now it's a much larger project and it really has a community backing it. So it's very highly developed. The development happens very fast in SPAC. So SPAC is really for managing packages. You know, you show up on a computer. One of the big things that SPAC does for you that if you're familiar with something like Homebrew or Mac ports, if you show up on your Mac, you can use those to get software, you know, like I need a wget on my laptop or something. I can use Homebrew to just install that package. So SPAC does that, but it kind of goes one step further. And when you're on a supercomputer, you really want to be able to build with a bunch of different compilers on a supercomputer. You want to build with a bunch of different configurations. You're ultimately looking to get the highest performance. So SPAC is really focused on helping you build typically from source, you know, very highly performant software and to be able to automate the whole dependency tree for you. So SPAC kind of started out more as like a systems administrator type utility to be able to deploy software and, you know, create software environments on supercomputers. But as SPAC development went along, a lot of extra features came along in SPAC. So my core thing that I want to get across to you while I'm doing this tutorial is how you can really use SPAC to develop your software. They have this feature called SPAC Develop. that was really crucial to our project's success. So I'm going to go through the tutorial and explain that process. But since we have people who've never seen SPAC before, I'll try to give you a little bit of background on SPAC. Just a couple things that might be useful to know before I dive in, and like, because I kind of focus this talk a little bit on not really wanting people to necessarily have to know everything about SPAC before I show you how cool it is to iterate on a software project, developing it. So, so before I talk to you about all my other projects that I have this documentation for, I have some slides here that show. I think I heard somebody talking on, maybe just because my audio is up. If anybody, oh, by the way, if anybody has any questions, feel free, just talk to me. I want to make this more like interactive and stuff. I'm not going to be super formal about this tutorial. The other thing I should preface is, you know, tutorials you usually follow along. I don't have a lot of resources to get cloud resources so people could follow along. One thing I wanted to mention, which I completely forgot, is I'm going to be doing this on my Mac, my M1 Mac laptop. So I can tell you fairly easily how to set up a Mac to use SPAC. But another thing that you can do is if you have Docker, we have a Docker container that we can use. So there's on Docker Hub, this has pretty much all the stuff that I would use in the tutorial if you have Docker, access to Docker. But you don't necessarily need to follow along. I feel like I'm going to show you what I'm doing step by step. If I had more resources, I would have set this up better, so we all could have followed along if you wanted to. But it's this ECP E4S/ExoWin snapshot. That's a container that's built every night that has our software and all the stuff that I would be using. So I'm going to jump around a little bit here, but. Okay, so for people who don't know SPAC, I'm not going to like go into too much more detail. I'm going to try to hit on some core topics of SPAC before I move on into my tutorial. So the key thing to learn about SPAC initially is the spec. The idea of a spec in SPAC is how you're describing packages and their dependencies. So if you just install SPAC and then you know, you want to install zlib here or something, you kind of need to know how you want to install zlib. So the idea of a spec means that you're basically describing a package and you're describing things about it, such as I want to build this package with a certain compiler, or I want to build this package with certain options on it, or I want to build this package for a certain architecture. I could build for multiple architectures in SPAC. I want to build this thing, this spec or this package that has a dependency, but I want to do a specific thing to a dependency that exists in that tree. So the spec is pretty crucial to describing what you want to get across with SPAC. So something that you can do here, and I can start to be interactive about this. So I have SPAC loaded here already. So things that I can do once I have, I'll show you how we load SPAC later, but let's go through how the specs actually work. So if I'm gonna, so a spec is basically just what you're looking to install, like a zlib in this case, something I want to install, but SPAC actually has to go through and make a specific way that it's going to install this for you. So you have a general thing that you want to install, but SPAC has a process where it solves exactly how it's going to install something. And that's the second key thing that I want to talk about in SPAC is they call it concretization. So SPAC has a solver in it where it has a bunch of rules and it figures out how it's going to exactly install what you want to do. So the way that you can see how it's going to do that is I have this spec and I can do this zlib package. So if I type spec zlib, it's going to go through the concretization and it's going to tell me exactly how it's going to install this package for me. So you can see that zlib has a version on it. Zlib has these blue options for it. These are called, we call them variants. So you can turn optimization on, you can turn position independent code on, which is what pick is, shared. It has a build system that it uses. This is a makefile build system. It has an architecture. I'm on a Mac. So Darwin Venture, it's an M1. And then this percent is the compiler that I'm going to use. So Apple Clang 15. And then you can see there's a dependency that since this is the build system, it's a makefile. It depends on gmake, so it needs gmake. So one thing that's great about SPAC is you can show up on a machine that doesn't have any packages on it for the most part. You just have a compiler. And SPAC can really stand on its own and install packages for you. And it doesn't need things that already exist on a system. It doesn't need gmake. It will build it for itself. So I'm not intending this tutorial to like give you the whole background on SPAC. That's something that you can branch off and do on your own for the most part, but I do want to get across the idea of a spec because that's like pretty core to what we're doing. So you can get a lot more complicated in this. Yeah, I can. So if I go to a different project, such as a project that I work on called AMR Wind, and I do spec AMR Wind. So we can see this thing and see how many dependencies and exactly how it would install AMR Wind. And I'll show you some other options that I can do to change. And I know there's a lot of stuff that I'm not going to be able to, I'm going to miss so many things as we go through this. But here you can see that it concretized AMR Wind, exactly how it's going to do it. So AMR Wind is built, it uses CMake, so it will build CMake for us. It's an MPI application, so on this machine, by default, it will install OpenMPI for me. It'll install all these little things that it needs, like Perl and whatnot. So let's say that I'm on a supercomputer or something, and I have my machine configured, and I'll talk more about configurations later, but I have some compilers that are available for me on my machine. So since I have Homebrew installed on this machine, I have GCC and I have Apple Clang available. So you can see when just by default, SPAC has defaults in how it will install everything. So by default, it's using Apple Clang based on some preferences it has. But if I want to install AMR Wind here with GCC, I can give it a directive to say, install AMR Wind for me with GCC. And we'll see how the DAG changes. Sometimes it takes a little while to solve when there's a larger thing to solve. So now you'll see that all these green identifiers, everything in this whole DAG is going to be built with GCC based on me describing GCC for AMR Wind. So other things I can do is like, if I want to do something different for a dependency, I can say, I can add on, like I want to do CMake with So at this point, I can use the caret and use a dependency for CMake, and I can change, I want to build CMake with Apple Clang. So I can do a lot of stuff like this. I can do options for CMake. So yeah, I'm not going to go too much more into depth about the specs, but so we'll see what this actually does. So here you can see that I have GCC for AMR Wind, but once it gets to CMake, now it's anything underneath CMake as a dependency is built with Apple Clang. So now I can have a mix of things. So that's the idea of a spec in spec, which is very important. So spec.io has all this information. So, you know, once you figure out what you want to install, it's typically pretty easy commands. You know, you can do spec install, spec uninstall. And it will download the source code for you. It will build it automatically. But I'm going to go mostly into how we're using spec to develop projects. So, I talked a little bit about specs and spec commands. So, so spec does have develop options inside of it. So we can do development in spec directly based on their documentation. So if I go to the spec docs, and the docs for spec are really good. So I think they should have development. They have a tutorial for doing spec development. So here's the developer's workflow tutorial. So you can do development directly in spec. But one thing that you don't necessarily get when you do spec is when you do spec develop just by itself is when you show up on a machine with spec, you typically have to set a configuration for the machine and how you want it to do certain things. For example, if I show up on a supercomputer, I don't typically want to install my own MPI unless I'm a very experienced user. So if I show up on a Cray machine, I probably want to use Cray MPitch or whatever MPI they have. So I typically would have to go through and make a configuration for SPAC and do a lot of things that involve some overhead to really, you know, wind up with performance software and to really, yeah, not do things naively. So if you're just going to go do SPAC development and use SPAC develop by yourself, there's a little bit of overhead in it. So one thing that we did, that we started to develop for our project, which other projects can use too. So let me start back at. Okay, so now I'm going to start like moving into the tutorial. So I can tell you like where I'm actually going. So we have this ExoWin project. It's just the ExoWin organization. So github.com/ExoWin. So that's where I'm at. And then we have, I'm going to talk about ExoWin Manager later, but this is the documentation that I'm going to use for the tutorial. So we have this thing, before I talk about ExoWin Manager, we have this thing called SPAC Manager. So this was developed by a guy named Phil Sakovich at Sandia National Labs. So what SPAC Manager really does is it's a lightweight layer on top of SPAC that really does two main things for you. It automates deciding which machine you're on. It automates finding configurations that you would have an expert hopefully develop or create. And it also can focus specifically on a project that you want to develop. So Spec Manager really kind of automates finding the configuration on whichever machine you're on, automates injecting that into your SPAC configuration. And it also focuses on a project that you are developing. So that's the two main things that SPAC Manager really does for you. So I have documentation on that based on ExoWin Manager. So SPAC Manager is just a little bit, just a layer. So it kind of does like, and I'll go through how it does the machine fingerprinting and things for you. But on top of that, we have a project focused iteration of SPAC Manager called ExoWin Manager. So regardless of whatever project you're in, I'm using this for a very specific project, ExoWin, that I kind of described before. Everything that I'm doing here doesn't necessarily have to be specific to our project. You could just rename anything from ExoWin to whatever your project is and be able to use all of this framework on top of it. So I'm going to dive more into the tutorial here. And just throw out any questions if you have them or anything. I know I'm a little bit scattered on all this stuff, but I'm really just trying to get this tutorial. I'm trying to get a key thing through to you and how cool this this feature is. So that's really like the main thing I'm trying to get across. So yeah, Xwood Manager is a project specific specialization of SPAC Manager. So I'm going to do this tutorial on my laptop. I just have an Apple M1 laptop. I have, if anybody would want to do this on an M1 laptop, basically all you have to do is install Xcode, install Homebrew, and then you can install GCC because you need a G4tran. You don't have that on a Mac unless you get Homebrew and get G4tran on your Mac. And I'm going to use a feature of SPAC that I'll talk about later that you would need Make for. And then you can just put GNU Make in your path because the GNU Make on the Apple Macs are too old to use dep files that I'll talk about later. And you might need to install Python 3.12 instead of 3.13. So the first thing to know when using SPAC develop is, I talked about the machine configurations, and those can be kind of difficult. So if you have an expert that kind of can do the machine configurations for you, the key thing that Xwood Manager and SPAC Manager do for you is automate finding itself on the machine and then using those configuration files. So I'm going to go through and I'm going to do all this stuff live. So I have this directory called live, and hopefully everybody can see the text big enough on this. Let me know if you can't. So I'm going to clone this Xwood Manager. I'm going to show you what this, show a little bit about what this all looks like. So we have some submodules, if you're familiar with Git submodules. So inside Xwood Manager, we submodule SPAC Manager itself. So it has a couple, SPAC Manager is like it's built as an extension of SPAC. So you can use, you do SPAC Manager commands, and then it's just a full extension of SPAC. So it's pretty much like using SPAC. And then we also submodule SPAC, so it doesn't change over time unless we want it to. And then we have, maybe I don't. So we have some custom package files, maybe specifically for our application. So I have a couple optimizations that happen specifically for my project that don't make sense to upstream to SPAC. I'm hoping to go over those while I build stuff later. So there's a custom package repo. So SPAC has a bunch of recipes for packages. We have a custom repo that has some customizations for certain packages that we do. Documentation, and then here's the machine configuration. So these are like the supported machines in our project. So for example, we have a Cray machine at NREL, where I can have my compilers that I want to use listed. So we have some Intel compilers and GCC compilers listed here in our configuration. We have a way to use the MPI implementation that's on the machine. So the configurations aren't too crazy. They're pretty short. This is a complicated Cray machine, and this is kind of the whole configuration. So I can do certain things, like I always want to use boost with 1.8 on this machine. I always want to use, for MPI, I always want to use Cray mpitch that's defined up here. Things like that. So that's kind of what the repo looks like. So I'm going to cd into here. URL here. Okay, so the first thing I'm going to do is I'm going to load Xwood Manager. So I have this little shortcut thing, shortcut script. You can see all it does. we set an environment variable, XON manager, we source the start.sh, and then we have this little SPAC start thing. So this really gives us shell support for SPAC. If you look on SPAC's documentation, they have a way to load SPAC with shell support. So we kind of do all that stuff automatically here. So I'm going to source that. So I have my compilers. So based on whatever machine I'm on, I can do this command. Spec manager find machine. So you can see that this is the project that XON manager is my specific project, and it says I'm on Darwin. So I'll show you how that stuff works, but we can look at the Darwin config. So I really just have, I don't even have the compiler specified here. I just have a packages.yaml. So for my Mac, I just have these couple things set. Like I always want to use Apple Clang. For CMake, I can always do build type release for CMake. For all the BLOS and LAPACK, I want to use OpenBLOS on my machine. I get back to my tutorial. So I'm going to show how we actually do the fingerprinting. I feel like that is. So the other thing to note in the XON manager directory is that this is the find machine Python file that does the inspection for the machine. So you can basically see we're focused on environment variables. So if I'm on a certain machine, say I'm at NERSC uses this NERSC host. So if you're on Perlmutter, we basically just probe the NERSC host environment variable. If we're on that, then we know that we're on Perlmutter. So it basically goes through this whole list of lambdas. And these are all the machines that we support. So these correlate to the configurations that we support. So it's a pretty straightforward file. If you want to add a new machine to this, it's pretty easy, especially if you just have an environment variable. You can just probe that. Otherwise, there's a bunch of, you can do that any way that you want in Python. So that shows what machine I'm on. So in SPAC, we're going to use just these things called SPAC environments. It's just kind of like a Python environment. And SPAC has this these YAML files, spac.yaml, that you can define certain things in certain packages in your environment that you want to install. They're not too complicated, so I'm not describing it too well, but the first thing that I can do once I have XOM manager like set up and sourced and I know what machine I'm on, I can really go through, since I'm on a project specific repo here, I can go to so what I have in the configuration on certain machines is there's a template.yaml file, and this is basically just a spac.yaml file that describes the packages that you want to install in a SPAC environment. So here I just have XOINT. So it's a pretty simple package file, but I'm just showing you that because the template files we can use by default, we can just deploy our project now based on defining a simple template file here. So I can show you that we have this deploy script that now if I want to build XOINT, oops, I can just use this deploy script. So this is the simplest way. So I can run this deploy script and it will look at what's in the template file for that machine. And it will go through, it'll create a SPAC environment for me. It will concretize that whole template.yaml file. And then it will install it for me. So one thing to note about building stuff in SPAC is you want to build this, build your stuff as fast as you can. So if you're familiar with doing make and parallel and trying to make stuff as fast as you can, so you can do make-j whatever in GNU make, and you can have parallelization to build a bunch of object files all at one time. So SPAC does that automatically inside, a CMake project or a CMake package or a make package. SPAC will look on the node or whatever machine it's on, and it will know how many cores it can use, and it will automatically build each package for you with that amount of parallelism. But if you look at a graph of your dependencies, there's a lot of things that don't depend exactly on one another. So there's even further opportunity for parallelization inside the DAG, where if I have packages in the graph, I can build them concurrently. So I can build in SPAC using DAG parallelism as well as using makefile parallelism. So once you get to that point, you're really building things pretty much as fast as you can go. So SPAC really does the parallelization through file locks. So you can go on any machine, you can go on multiple nodes on a supercomputer, and you can go to your scheduler and you can run 1,200 processes, and SPAC will figure out how to do the parallelism inside the DAG and parallelism inside each package as well. So that's what our script does automatically for us here using dep files, which I'll go through a little bit later. But you can see that this is, hopefully it's, you can kind of tell that it's building multiple packages at the same time as it goes through here. So I'm not going to go through this whole build, but this is just a very simple way to deploy your project immediately using this framework. So I have this built already. So once I have that built, you need to know how to load your project. So here I show that I went through and built ExoWind until it built, and it will take about 45 minutes to build on my laptop. And before we had these dep files and all this parallelization, and we used to have 2-core Intel laptops, it would take us 8 hours on our laptop to build ExoWind each day. If we were going to build it from scratch, it took the entire day to build it. Now it takes like 45 minutes. So if I want to go back to my project that was built using that script, so I just started up a fresh terminal, so I shouldn't even have SPAC in here. So I'm going to show you how I load this thing. So this created a SPAC environment for me. So it's called ExoWind environment. So I can load that environment. Oh, I'm in the room. What do you know? I may have messed this up. Yeah, it's not gonna let me. Okay. Anyway, so I'm gonna breeze through this one a little bit. So you would have saw me type in activate the environment, and then you can just load each package and it will put it in your path. It will load, do like LD library paths type stuff for you. So typically when you're on a machine like a supercomputer, you might use modules or whatever, but SPAC load can do all that stuff for you. Okay. So let's go through and show you the coolest part about all this stuff, which is how to develop code within a project. Okay, so I'm gonna load this thing, source, shortcut. So when you first source this, it's going to do a couple things on my laptop. It's going to find the compilers automatically for me, and it will add those to a configuration. It will also register my custom package repo. So we have some shortcuts inside XWin Manager and SPAC Manager to get a development environment set up. So the thing I can do there is once it's sourced, I can use this quick create dev. So this is just a shortcut to do SPAC develop. And I'm going to give it a name for my environment, which is this -n. And then I'm going to give it a spec, which I talked about before. So I'm going to say, hey, I want to build AMR Wind without MPI. So this tilde means that it negates MPI. So I'm going to turn off the MPI variant. So this is just going to be a serial version. And then I'm going to specify the branch for my package, which is AMR Wind. So all this stuff is encoded in SPAC, so it knows the branch and it knows the Git repo. So it's going to clone AMR Wind for me. It's going to set up this whole environment, and then it's going to load the environment for me. It'll take a little bit to clone AMR Wind. Okay, so now it's trying to color the prompt. So this is all a mess here, but it can't color the prompt on my Mac. So now, if I look in this environments directory, I have this AMR Wind env. So what SPAC Manager did for me is it cloned AMR Wind automatically. So I have AMR Wind in here as a Git repo. It created the environment for me. So there's this spec.yaml. So this describes what I want to build in this environment. So I have this spec, which was the AMR Wind without MPI. There's some other options I'm not going to talk about, but I also have this include, and there's an include.yaml, and that's all my machine configuration stuff. And then it lists AMR Wind as a develop spec for me. So the key to having this thing listed as a develop spec is when you do the SPAC install process, it will always rebuild your software in that repo. So I will show how that process works. But if I look at this include.yaml, so this include.yaml is all of the machine configuration stuff. I have some default configuration things where I store like the downloaded source code. I store it in my home directory here. I can put the temporary build stage where SPAC like builds everything and then it discards it later. So this include.yaml, this is what SPAC Manager puts together for me for this machine. So it did it automatically. So based on the configurations I already had, it's set up for me automatically. So that's basically the spec.yaml file. So once I have an environment, now I need to concretize this environment so that SPAC solves exactly how it's going to install. So I should see that It should solve AMR wind, and it should just have CMake as a dependency in this case. So before it has to solve, it's going to install. Klingo is the name of the thing that it uses to concretize. So it has this solver inside of it, and it downloads this typically from in a binary form on one of SPAC's sites. So here you can see how it's going to install AMR wind. So what I could do is I could just type SPAC install, and then it will install AMR wind in this environment for me. But I want to be faster about this, and I want to use full parallelism inside the DAG. So what I can do is I could run SPAC install multiple times, just like here. You can see that I can do SPAC install with the ampersand, SPAC install ampersand. So that's going to do SPAC install twice in my bash terminal, and I just wait for it, and then it will do, and SPAC's file locks will handle figuring out that it can build this package at the same time as it can build another package. So I can do that with more parallelism based on creating a makefile, which we call dep files. So once I concretize my environment, I can say SPAC env dep file, and then I say, oh, and I want it to just be makefile. So what that does is it creates a makefile, and it gives it all the SPAC commands that it needs to build my my environment. So now all I have to do is do make with parallelism in it. So I can do that even listed on here. So here I do nice make J8, but I'll do nice. And we'll see this light up my machine. So I am going to build this live, and I'm going to, as this builds though too, I'm going to try to give you an idea on how much stuff we use SPAC for, because I think that that's, we use SPAC for pretty much everything that we do, based on it being able to automate everything for us. So you can see that it's building multiple packages at the same time here, and it's going to use, it's going to light up all my cores. So we'll let that build. I think that usually takes like 15 minutes or something like that. And I know people don't like SPAC that it will, I already have CMake on my machine. I don't want it to build CMake. But at some point you just give up and you let SPAC build whatever it's going to build. Because I recreate stuff constantly all day, and it's way more efficient than trying to figure out how to not do it. So once this builds, the next, I'm going to show you how I run the tests in my application. And then I'm going to show you how I just edit the code, and I'll show you how I rebuild the code, edit the code, then rebuild it and rerun the tests and just iterate on the code. And while I do that, keep in mind, the key thing to note about this is when you think back to my slides where we were developing 7 applications at the same time, and Hyper, our linear solver, like AMR win could depend on Hyper, and we have an expert in Hyper developing this specifically for our project. You can put multiple software projects or multiple packages as developed specs into that spec.yaml file, and you can reinstall all of them with all your code changes in one command. You can type SPAC install. It knows exactly how to rebuild it. It does it iteratively, so it doesn't rebuild your whole project. It doesn't rebuild all the dependencies. It keeps all the object files around, and it will rebuild the code, in seconds. And you can iterate on that. And I can develop Hyper at the same time. And I could develop a feature in Hyper, type SPAC install, test it in AMR Wind, and I can do that all the way down to like zlib, whatever I want to do. I can type SPAC install, and I'm developing this thing in zlib, and then I have this dependency tree that I'm testing it so far away. And that's the power of and we would not have been able to finish our ExoWin project in the 7 years it took us to if we didn't have this feature. There's no way we would have had the capacity to set up all the build systems on all the different machines, and we were building ExoWind on heterogeneous machines. So, you know, GPU machines and, you know, 3 different supercomputers we were developing on. People develop on their laptops. And the other key thing to think about when you're doing development in this is imagine that you want to develop 4 CPUs and GPUs at the same time, which is what I do during the day. Inside that spec.yaml file, you can set up multiple specs for your project. So for AMR Wind, in that spec.yaml file, which maybe I show here. So inside this, I have this one spec. I can add as many specs as I want. This is a CMake project. You can do out of source builds. So I can say, I want to do AMR Wind plus CUDA to build this thing and run it on the GPU. I want to do AMR Wind minus CUDA. I want to do AMR Wind with the address sanitizer turned on. That's what we do a lot. I can put all of those in here. I can edit the same single source code in AMR Wind, and I can type spec install and have it build the CUDA version for me. I can have it build the CPU version for me. I can have it build the ASAN version for me. I can have it build all these things for me automatically, and I can have it run the tests in all of those. Just like the snap of a finger. And you can, you know, you can get a compound command to basically do all that stuff for you. But I'm hopefully conveying the power of that if you're actually developing software at any level. I feel like just getting yourself into the SPAC developed system, and not necessarily like you necessarily have to use SPAC Manager or ExoWind Manager. The key there is it gives you a lot of automation for the machine configurations and stuff, which is super helpful. But just SPAC develop itself is something worthwhile, just based on developing anything. Because once you get yourself into the system and know how to use SPAC, it translates to, it's so portable, and it translates to your laptop, it translates to, you know, supercomputers, it translates to the cloud. They use a lot of it, SPAC in the cloud. So as this continues to build, it should start to get to CMake pretty soon here. I'm going to talk a little bit more about what we use SPAC for in my project. Sure. Yep. Mm-hmm. Yeah, so the question was, does SPAC typically support NVHPC, which used to be PGI, right? And then the NVIDIA bought PGI. So now they have this NVHPC. So are you asking whether or not you need that installed on the machine, or can you, because SPAC can install that for you. It can install all the compilers for you too. So you can choose to have, like, if you're on the machine, you can choose to, we call it making it an external. So you can describe that in a YAML file for SPAC and say, it's already installed here, you can use this. Or if you don't list it as an external, it will typically build everything that it needs. So if you want to specify that it needs NVHPC on the command line, it can typically go through and install that for you. Sometimes it doesn't necessarily work very well on the machines, but for example, if you're on like an AMD machine, like AMD GPUs, it will install all the ROCm libraries for you if you want. You don't necessarily need to have them installed on the machine. We typically don't do that. There's a machine at Oak Ridge called Frontier that is a AMD GPU machine, and that already has ROCm installed. So we have ways that we list that so we don't have to go through and build it every time. But you don't need to. It's typically up to you. So while we wait for this thing, I'm going to go through some other topics that I just have at the bottom of this. So the other a main key way that we use SPAC is for automated nightly testing for our projects. So we have this script that just kind of automates the deploy script that I showed you earlier. So the deploy script just takes those template YAML files and it just installs automatically whatever inside of them. So the way that we do nightly testing is I talked about having, well, actually, I'll go through some custom repos here. So we have these custom repos for our packages. So one thing you don't have to do if you have your own custom repo that I don't know if there's any SPAC experts, but you have these package files that are built into SPAC, and then on top of that, you can have your own custom version. So you don't have to duplicate all that code that's in that package file. You can just inherit the class and you can add on certain things. So what we did for a lot of our packages is we add an address sanitizer variant. So we call it ASAN. And then based on some code in there, we basically do, if we have this option ASAN turned on, then we just add in fsanitize address to our C++ flags. So we just have this little extra thing on top of whatever SPAC is already doing built in. So you can see that we import the built-in AMR win package. And then you can just inherit it as a different, we just always call it B, whatever package. And then we can just add on our little delta of changes to the packages. So you can see that we also have this thing described as, so inside the package files, they're either, they have a certain make system. Sometimes they're just defined as a CMake package or, a GNU make package or something. So on top of the CMake package class inside SPAC, we created a CTest package. So any of our custom packages in our repo, if we list them as CTest package, that allows us to be able to test these and submit C- results. So you can see I have this ExoWin C-. So we have ExoWin that's tested on a machine with GPUs. So we test ExoWin every night. We test it with the Clang compiler, the GCC compiler. We test it with the build type release in CMake, which does all the optimizations and stuff. We also test it with debug, so it turns optimization off. It does -0, and that does a couple different checks for us. So we do that for our top level ExoWin package. Underneath that ExoWin driver is an application called µWMS. That really does the wind turbine itself. So that's like an unstructured mesh thing. And then that gets coupled to AMR Win, which does the space in between the turbines. So that's a square structured mesh solver. So we test all these, we test ExoWind, we test Nalu with GCC, and we test it with Clang. But we also test it with, you can see that plus CUDA is on for some of these. So we test these all, these are all GPU capable. So we test them on the GPU as well. So we really do that through using that specific CTest package here. So if I go back, we have the CTest package that does all the CTest type things for us. So it will say the name of the machine you're on, and it will do all the CTest arguments automatically for you to submit the results to C-, which is our dashboard for testing. So that's just built into here, and we get that in every package as long as you just describe it as long as it's a CMake package, and then you list it as a CTest package as well. So once we have that set up, the way that we test this thing is there's just that simple script that really just runs that deploy script that I showed that deploys the template.yaml files. But if I look at the testing machine, so our testing machine is called Ellis. So I have a list of compilers in here that it can use. So I just have Clang and GCC. I just have my regular machine configuration, but in this template.yaml, this is the key to how we do testing. It's very similar to how we do development or just deploying the software. it just flips a little switch and then it will actually test these and submit them to CDash. So you can see here's the specs that I have in that template.yaml for the test machine. So here I can either run AMR Wind or Nalu on the GPU or not on the GPU. And I have a couple other like options that I'm doing here, and I'm testing these all on the master branch. So I'm specifying the branches for these. So I could list a whole bunch, if I had other branches that I wanted to test, I could just make another spec and I can change, I want to do Nalu on a develop branch or something. So here I'm listing the dependencies with all, so what I'm doing here is I'm just turning basically all the options on. So I'm kind of testing all the options and making sure that all of the things that I want to test are on the develop branches. So since, and you'll notice that ExoWind is just one spec. I don't have this broken out to a list of, there's 4 build lines on the dashboard for every application here. So I don't list those explicitly because AMR Wind and Nalu are already in the DAG. They're in the dependency graph. So as long as they're C-test packages, they just get tested automatically. So I just have four specs in this thing, and it submits all of these results every night based on those 4 specs, just because they're dependency of one another. So hopefully you see the power of just being able to, I can add whatever I want to this dashboard just by editing that template.yaml file now. So that's an overview of kind of how we do nightly testing. I talked about the C-test package. I talked about custom package files and how we can just do the delta. You don't have to like overwrite the package files. Another thing we do if you have an application that we have CFD applications, so we test we call them gold files. So we have physical quantities that the simulations outputs, like temperature and whatever. We have these as plot files. So we want to see if we make changes to the code and that the output of the code in plot file form was changed at all. So we have tools that are built into like AMR Wind has tools that will check differences between plot files. We call it fcompare. So we have this type of thing in Nalu too. It does mesh files, it does Exodus meshes. So we have exodiff there. So built inside like the testing, like the CMake C-test stuff that's built inside each one of our applications, we need to be able to manage gold files too based on doing our nightly testing. So we can do that kind of automatically in SPAC as well. So rather than, so if you have these physical quantities and you have optimization turned on for your code or you have it turned off, your physical quantities can be different based on the optimization. So you can have, orders of magnitude differences in your quantities for temperature or anything. So we typically organize our gold files based on exactly what machine we're on, exactly what like options we have for the code. So we can organize that in SPAC because we have these specs. So I'm just showing the script that I have that we kind of have everything automated based on inside our CMake, we have the ability to store the quantities from the results of the tests in a certain directory. So we basically just store those in a certain directory. And then we can reference them through SPAC. SPAC is basically a database of options in our packages. So based on this package with this options, our gold files are stored in this location. So we can organize that and we can update all of the gold files just based on the options. So that's kind of organized for us automatically. So I have this update gold script that I can run as soon as somebody changes something in the code and it changes some quantity and we're fine with it. I need to update the gold files. And this basically goes through our list of build options, which you see here, which is just what you saw on the dashboard, which is, Clang, like Clang with ASAN turned on, Clang with ASAN turned off. Then we have no CUDA GCC, and then we have with CUDA GCC. So those are the 4 main build lines. So I can organize those all automatically too, just based on using the specs in SPAC. So that's how we manage gold files inside of there. Okay, AMR1 built, by the way. Okay, so now that AMR1 built, and it built CMake and everything for us, I'm going to go back to, let's iterate on the code now. So this is key thing I want to convey is how easy it is to iterate on the code. So the first thing I want to be able to do is run my tests. So inside AMR-Wind, I have the CMake project. I have CTest does all our tests for us in there. So that's how we tell our project, how to test the code. So what I can do now is I can say spac cd. So I want a cd to the build directory for AMR-Wind. So now I'm in the build directory, which has this crazy hash on it, but it's in the stage directory. So the next thing I can do is I want to run the unit tests for AMR-Wind. So I'm going to use this command. I'm going to use this command called spac build env. So this loads the build environment that AMR-Wind was built in. And so I'm giving it spac build env, and I'm giving it the spec. So I'm giving it the spec of AMR-Wind. I want it to be in the AMR-Wind spec build environment. And then I'm going to run ctest inside that build environment, and I'm going to run everything labeled unit. So there I run the unit tests. And I can see that they passed. So I built my project. I have the source code that it built from. Now what I want to do is edit the code. First thing I can do is I can run ctest with more verbose output. We can see the actual unit tests we have for our code. And I'm going to show you this one section where it starts because I'm going to edit the code. So I think it's around here where it's running 250 unit tests, 254 unit tests. So I'm going to edit the code and see how easy it is to rebuild. So I'm just going to go back to my environment. I'm going to go to the AMR-Wind source code. Let's see if I made this easy for myself to find the unit tests. So this is the unit test. And I'm just going to add output here. Okay, so I edited the code in AMR-Wind. So there I just have a couple edits. I still have my, I should still have my spec environment loaded. So now all I have to do, I didn't edit my spec.yaml file. If I would have changed something in the spec, or so maybe I wanted to do a CUDA version of this, I would edit the spec.yaml file. I would have to reconcretize my environment to do the solve in the way that, so it knows how to install it. But I don't need to do that. I just edited the code. So all I have to do is reinstall my project. So I don't need to do dep files for that anymore because I don't need to build this so fast. It already has all the dependencies built. AMR-Wind is built. It's just going to find the files that changed, and it's going to rebuild this iteratively. So all I got to do is type spac install. It's going to run CMake. It's going to run the build process. And it already built it. We also add this little analysis step. It just runs the unit tests every time. We added that inside our CTest package. But you can see this is only 17 seconds, where before you know, I sat and babbled about some other stuff for like 10 minutes while it built. So now I want to run my tests again. I can cd to the build directory. And all right, I'll clear the screen and then run the unit tests. And hopefully we see my changes. So I changed the code. I didn't have to go through some other fancy build process. All I do is edit the code and I type spec install. And I just want to reiterate, if you're developing something underneath this, like if I'm developing Hyper underneath this and I want to change something in Hyper and I change the code, and all I have to do is type spec install. It will rebuild Hyper, relink it, and all it has to do is relink AMR wind on top of it. So it's super fast to iterate on a project underneath it. So hopefully I conveyed like how powerful that is for any project really. Even if you don't have dependencies, you still you're just typing spec install and it's already installed because nothing changed. So I ran the unit tests again. That's really the key. I knew I was going to go short on this tutorial anyway. But that was really the key thing that I want to get across in developing with SPAC is how powerful I think that is. So if I was going to do, more things, I might have to, I could add so maybe I want to add a debug build to that. So all I do is add a separate line, reconcretize this. So concretize two specs. Can I even find them? See what happens if I spec it. So anyway, with one single source, I can do a lot of different things. I can just edit that one single source. I don't have to try this in a bunch of different ways. SPAC can do all the permutations for me. So a couple other things I'm going to mention, and I'll probably only go to like 2:30 here, but some other things in SPAC. If anybody wants to know about anything else, there's a couple extra commands that I didn't go through all the commands that we have. We have a bunch of shortcut commands in like XOM Manager for doing certain things or shortcutting certain ways. Another main thing I'm going to talk about is, so yeah, we use SPAC for everything. I'm going to show you how we use SPAC for our CI, like our continuous integration. So we have this huge, huge graph of dependencies. I told you that, when we started out on our laptops, it took 8 hours to build ExoWind on your laptop with a 2-core machine. Now we're down to like 45 minutes. But if you want to test this thing on GitHub, GitHub has GitHub Actions that you can use their virtual environments on the internet for free, basically. And you want to test the code, how can you do that with the SPAC? You can't just build on their runners for hours at a time on hundreds of cores. You really want to really pinpoint all, like the only thing that you're trying to test. So for example, we have this top level package in XON called XON driver. This is really how the top level where everything's coupled together. And we want to test that. So if I go to the YAML file for the GitHub actions like YAML file and how we test XON driver, we use all this XON manager stuff and it's pretty simple once we do it. So every night we have a machine out there that builds the container that I showed you initially. The E4S is from the University of Oregon. They build this container for us every night. So we get to use that and, you know, you can download that on your any Docker, just off a Docker hub, and you can run it on, you know, any computer that you want. I think you could even run it on supercomputers with the right MPI implementation. But we use that on the GitHub actions to test our application and only the changes in like a pull request. So the way that we do that is just with these couple lines. So we basically download that image and we go through and we basically set up the pull request to or we set up an environment in SPAC to, so we actually have two environments in here. So we have an environment that built everything for us inside this container. We set up a second environment and we have this SPAC manager external command. So one thing that SPAC does, like I tell you before, it likes to build everything for you. It builds CMake and stuff for you. So this external command says, take everything that's in this environment and put it in a packages.yaml file as an external. And it sets this keyword buildable false. So that means that all of these packages listed in this package file SPAC won't build. And you don't, like, you can use SPAC upstreams and stuff if you look in the documentation and try to get SPAC to resolve the solving so that it doesn't rebuild everything for you. Because once it matches the hash, it will reuse things that it's built. But it's kind of hard to do that. But if you use the SPAC manager external command, you basically force it to say, I already have this stuff built. I know exactly how it's built. Don't ever rebuild it. So we can guarantee to not rebuild all of the dependencies for this XOWin driver application. So we basically say, use everything, list everything as an external inside a YAML file, but exclude XOWin package itself, the XOWin driver application. That's the one that we want to build. So once we do that, then we concretize this and we do SPAC install, and I can show you that this doesn't rebuild anything. So when it runs the tests here, you can see that it doesn't even, when it solves it, it doesn't even create a full DAG, because a lot of these things have dependencies, and when it's listed as an external, it doesn't need anything underneath. So you can see that when I do the, when I concretize this, when it actually runs this for a PR, it says this stuff already exists, and you can see that it's a E listed, so it's listed as an external. And then it goes through and it only builds XOWins. And you can see XOWin only takes 15 seconds, but then it runs our test for us. And that with that same image, that E4S like XOWin snapshot image, we test this XOWin driver, we test this Nalu application with the exact same thing. So what we do there, we just exclude Nalu. We do all the other. And then all it does is build Nalu here. You only run the unit test, but this still takes 20 minutes to build just Nalu. But we couldn't do this otherwise. We just wouldn't have we don't have the resources on here. And plus it's more efficient if we just build the dependencies every night and then we just distribute this container. That's how we do CI. So I think that's pretty powerful. else did I want to talk about? There's just a bunch of other like very useful things in SPAC. You can have source mirrors for like air gapped machines. If your machine can't download from the internet, you can have SPAC. You can say SPAC fetch this whole environment and it will download all the source code it needs. And you can just move that whole group of source files over and tell SPAC that use this, and it doesn't need to use the internet. Another thing you can do is like build caches where you've already built binary files. SPAC can actually relocate binary files even if they have RPath in them. So SPAC has its own build cache that you can hook up. So sometimes you can kind of shortcut building something like CMake so many times. You can just say download the binaries from the internet. So that's a way to make building faster. I think I would talk a little bit about deploying large software environments. You can orchestrate SPAC based on make files, like I talked about dep files before. So I have this project that I do at NREL to basically show you what it looks like. So I've completely automated building modules on our test machine using SPAC. So SPAC can output module files for you if you've ever been on a supercomputing machine. They typically use module files. So here's a big software environment that I built with SPAC, and this is completely automated. I really just type make, and it builds all of this for me. And the way that you do that is really just with one large make file. So that machine that I have there, you show up and you have GCC 4.8.5, and that's what you have. So you want to go through and create a full software environment. So you can make a makefile to do a bootstrap phase on that, have SPAC automatically build like a GCC 12 for you so you can actually build some other stuff. So you bootstrap the machine with a phase through this makefile. And this is the makefile is just lists all these dependencies, and you can automate all the configuration of SPAC here. So I can do the bootstrap phase with this makefile. Once that creates a file that says the bootstrap phase is done, now it can go through and it can build all the compilers that I want in the next phase. So it waits until I need to build, okay, now I have this GCC. Now I can use the GCC in the bootstrap. I can build all these compilers, and then I can pick one compiler. And I want to build a bunch of software that you saw on there, like MPI and Python and SQLite and Hyper and all HDF5 and all that stuff. And I just have that listed in a spec.yaml file. And I just I go to this machine and I type make, and it builds all that entire thing, and it creates the module files automatically for me. And it ends up with this. And then people use this machine every day for development. And I'm a scientist. I'm not an administrator. I'm not a systems administrator. I just create this stuff and people can use it. So hopefully I'm getting across like the power of like why we use SPAC for everything. It's so automatable. You on my list here. Oops. Yeah, I mentioned that. So SPAC mostly uses RPath, so you don't have to deal with LD library path. It's kind of builds in all of the dependencies, so you don't have to deal with LD library path in your environment so much. I think maybe the last two things I'll mention. I mentioned the module files that can do that automatically. Is SPAC views. So imagine you're on your machine, your typical Linux machine, and you have this user directory or USR directory that has, all the libraries, all these like libraries in lib64. So there's a million things in here, right? So the way that SPAC typically deals with packages is it puts a hash on them once it does the solve, and then they're all listed in their own separate directories. So you have all these packages and they're all installed in their own separate directory structure. What a view can do is it will automate making a bunch of symlinks to recreate something that looks like / user. So if you have a SPAC environment, you can say, generate the view for that environment for me. And then all I have to do is, if I'm developing something, any random project, I could just export the LD library path to that view directory. I could export my path to that bin directory in that view. And I basically have that entire environment in my environment. I have that entire SPAC environment in my environment at that point. So views can really let you recreate like what / user looks like. And that's really powerful in just like making a single module that you can load to load a bunch of stuff. So there's a lot of things that you can do on top of this. Last thing I would just mention is that if you're using SPAC, it keeps track of everything it installed. So here's like where everything ends up getting installed for that AMR win, or where am I? So for example, I can look at how, all right, this is the directory structure, right, that has all the packages in a separate directory structure. There's these hidden .spac folders that's useful to know about, that if you install something, here's basically all of the information on how it built this package. So this shows the whole build process that SPAC did. This is just for Pigsy. So that was the last thing I was going to mention. Sorry, my tutorial is like a little scattered. I didn't have too much time, and there's a lot of stuff going on and whatnot. So hopefully I just conveyed to you like the power of SPAC and why we kind of use it for everything. If anybody has any questions or anything about it or how it might apply to your project, I feel like no matter what project you're on, it applies somehow. So I'm a huge proponent of it. I've been using it since 2014 or 2013, so I'm a huge advocate for it. If anybody ever wants any information about how to do anything or anything that you think it doesn't do that it could do, I would love to hear about it. But thanks for listening to me babble up here for an hour and a half or so. Yeah, I'm not going to go till 3 o'clock with this. I don't have any more stuff. I just wanted to show mostly the development process there. But thanks for listening, everybody. Yeah, I know I didn't cut, like, I definitely, there's a bunch of holes and stuff that I didn't cover, but really just want to convey like all the things you can do. All right. I think, is that even the end for today? I don't think is there? Oh, yeah, go right. I don't want to speak.
Yeah, I guess two things. So John, if you want to take questions, we certainly can, and
yeah,
we could.
And if anybody has any.
I don't know if we can take Slido questions online or not, but okay, nothing online, but if anything filters in, but yeah, in terms of what's next, so once we do wrap up here, basically sort of a break until 3 o'clock. There's a networking session. I will amend something I said earlier. So I think at the start of that, right at 3, we are going to sort of have a little short hybrid thing. So for people who are online and people who are in the room, we're going to do like some Slido polls, which could be fun. I don't know. And then after that, we'll sort of split apart, and virtual people will stay on the Zoom, and then the people in the room will just be in the room. So, but yeah, if there are any, I guess, in-room questions for John, maybe I'll ask one just
Sure.
To get your perspective. I could certainly offer my opinion on like the HPC software stack side, but I'm curious for like the developer use of SPAC. Like just your opinion, what complexity of project and dependency graph do you think that it makes sense to layer tooling on top of spec versus just sort of use it out of the box?
Oh, sure. I feel like, I mean, so maybe I'll mention that. So all the spec manager stuff by a guy named Phil Sakovich that kind of developed all this stuff. He's now like a core spec developer. So you can imagine that a lot of this stuff will be upstreamed. I think one of the key things that doesn't exist in spec is really like machine fingerprinting is a very great thing to have. That's like now, you know, as soon as you have that, every developer on our project that if you go to a machine that's supported, they already have the configuration injected automatically. So just based on that, to me is like a reason to do something like this. You know, not like you have to use spec manager or whatever, but it already does it for you. So just having those machine configurations automatically injected every time that you're creating an environment or anything, I feel like that's all I need to be able to switch to, you know, building something on top of spec because they don't have that yet. Maybe the other thing I would mention is just based on like using spec for development rather than like, imagine you have just a regular CMake project. Like AMR Wind is like that. It stands on its own. You can just use CMake to build it. A lot of people do that. But the second you add HDF5 into it, you move to something like this. Because the second you have to go deal with finding that module on a machine and now I moved to this machine, we already have that built in. You can just move to another machine. You can do it on your laptop. You know, oh, my machine's down. I can just develop this stuff on my laptop and I don't have to think about it. So yeah.
Agreed. Thanks.
Yep.
So thanks for all of this. I'll add on to this. So we have Spec Stack, which is basically Spec Manager developed at the same time by a different bunch of people.
Yeah. I know there's a couple projects like that.
Site-specific configs and environment templates. So it's exactly the same thing.
Yep.
So I hope we can have more of a conversation in the future because I think we're duplicating efforts here.
Yep.
I'll be in Chicago next month at HPSF here as well, so we can spend some time there. Otherwise,
Yeah. So the SPAC project is aware of that. It's not just SPAC Manager. It's not just SPAC Stack, or it's not just there's a bunch of projects that have done all this stuff. So there has been an effort, and I'm glad you brought it up because there has been an effort to kind of consolidate those. But it is pretty obvious when everybody's doing all that stuff that it would be nice to have some kind of extension or something on a SPAC that's like how to fingerprint a machine or something like that. And yeah, the environment files and all that stuff kind of automated.
So, but to your question there, sorry if
no,
I answered this. It's really only that part that's missing. So being able to have the machine config set up properly, especially on a Cray where you have complicated environments and externals and whatever else. On Monday there was this presentation by Jacob Kali, the keynote, right, where he spoke about this idea to break up complex projects like the UFS with its 12 or 13 submodules into individual pieces that then can be unit tested and installed separately. One of the concerns that developers are bringing up is, well, but then I cannot put my debug print statement in that submodule and then compile the thing and run it. What you presented today about spec develop with being able to have all the dependencies built, maybe like an external packet, like an external environment, and then give the developer tools to have these packages all built in with one spec installed, that will alleviate the concerns there and will help us break up these complex, massive projects into smaller things that can be loaded individually.
Yeah. Yep. Yeah, I agree. Okay. Well, I think that's it for me. I probably have a break until the networking session then. Okay. Well, thank you, everybody.
Like everything. Don't go looking. You don't want to know. you done the whole trail?
It's on my list. My mom was trying to get me to do it. But my mom and dad did it when they like got there. Yeah. Try to get up there.
Kind of, I'm at IMAP.
Oh, sweet.
Yeah.
I'm very thoughtful. You got to stop that Schrader base. Like very. I'm done to the.
Right, yeah, so you don't actually Other
Yeah, guys, I've got some time in grad school, so it's nice. Yeah. Mountains we call them.
she's like, Going home.
Right?
I would very much like to never.
That's the brain is. Yeah, and then I'm all, like, I get home and it's like. Tired. I'm tired, but I didn't do anything. Yeah. Some conferences you can like HU, you're like running. Hey. Well, yeah. It's like I'm busy. Yeah. Right. Right, yeah. Yeah. You know,
Other. Get more time last night. Okay. Like the parrot you're giving, like. Is that connected to the gut problems at all? To go under a mixture like engineering, public health. It's really, and it's really unique there too. I really sort of mix it up. Yeah, so they talk about the history. Like, so it's like the public health side of the engineering. Oh, came out in the Olympics. For a good reason. Those some of the same. Yeah. Actually, a really good use of that'll actually benefit the implementation from that, but not as much. Still some of the air. But yeah. I like that experience. Okay, yeah. I started liking around I mean, my favorite part might have been finding one I like went up to the security parts, but I literally so the museum probably think up to the security guy, I'm like so of course he's like what? Yeah. Gasoline comes to mind. Yeah, so that was the most memorable part. The museum, it's just really cool. I love it. Interesting museum in like there similarly there could be like New York State. Yeah. I've never heard of them. LA, they have like online you can Google like secret. Back when LA was filled with cars, regular cars, they had a lot of stairs built in like Beverly Hills, the surrounding areas. A lot of these stairs are still there. People have made like little urban figures. You can see like these stairs in the 20s, and it's actually really neat. Free thing to do in LA, where you're like, of course you're like, really expensive small houses. Yeah. But there were other people around. Yeah. That was it. There's a
I don't know if your girls will like it.
well, I think they will actually.
They might,
They
but
both like that. It's really like
yeah.
Okay. So I hope everyone was able to get some snacks and rejuvenate as I needed between the end of the tutorial and our networking session planned. So thanks everyone for sticking around. Today we're going to just be doing as you've already seen, at least for those in person, we've had some planning ahead of time of like topics of interest, and we'll get to those in a little bit. But just to warm up between everyone here, as well as including those online, we're going to just go through some, polls just to like live up the conversations and think about, what are important to us as, software engineers working with and among domain scientists and researchers, and how we can best support each other. So one of our colleagues on the committee already submitted some warm-up questions for us to go through, and if you can, please get ready with the Slido here, either scanning the QR code or entering the code number 9610202 if you're online. We'll go ahead and get started. So one of these, this first question here, we've had some sessions already talking about machine learning and AI, but want to get a sentiment in the room amongst people here about on a scale of 1 to 5, how do you feel about the AI ML hype in scientific software? I'll give folks time to respond there, and then I'll open up the results so you can see it. And if you want to like be contentious with people at your table that you're nearby with, feel free to like, add your own thoughts. This is supposed to be interactive in a sense of seeing what your colleagues think about, the hypeness in this case around AI ML. So as your votes go in, it should show up. Maybe there's, well, I guess one person was able to enter at least. So maybe there's some, I see the people participating at the top, but I'm not sure if you're hitting enter at the end. Oh, okay. Is it making you do all the questions at once? Okay. Sounds like a design UX problem. Yes, so in this case, it looks like it's a somewhat even distribution. In terms of people just kind of like meh about it. That's like not necessarily too excited by it, but maybe as like an interesting side question to this one, like, so I imagine us as software engineers have an awareness of the hype and usage of scientific software. How do you feel like scientists or domain scientists are responding to this? Do you feel like that's similar or different? Yeah, these are just not hard and fast kind of like, questions here. And they're just obviously just a small sample size in terms of us in the room and online. But, maybe this is informing you in terms of like, what might be important to you and your peers, and how you might be responding to like requests to help support and build out AI frameworks and workflows. But let's move on to the next question. Oh, I results. Okay. So in thinking about our day-to-day tasks, RSCs wear many hats, but which hats take the most time? Rank these from the tasks you spend the most time on to the least. And so here are some options of your tasks to choose from. I'm glad so far it's actually doing new science as opposed to focusing on old science, but how does that make people, I guess like that the refactoring one is second still. How does it make it feel about like the, at least the ordering here? Does that lead towards a, furthering or advancement of technical debt, or are we starting to, would that be drawing that down, you think? Yeah. I would like to see at least some emphasis on writing and updating documentation. I think recently, at least for my group, I've been encouraging my colleagues to have like a monthly meetup about at least our documentation to at least focus on that. But it's still not necessarily as much of a priority maybe as I think it should be sometimes. At least for us that are user facing sometimes in my group where maybe if we had better documentation, people could fix their own problems sometimes. So I think thinking about the ordering of this can maybe help what is most important, what can maybe resolve problems from one issue to a different issue. But yeah. All right, appreciate the participation so far. Hopefully just like encouraging you to like, think about just, what your peers might be thinking about and maybe help inform future discussions when we break out in a little bit. So our next question here, imagine you have a magic wand to eliminate one headache from your work life. Which pain point disappears immediately? So if you never had to deal with Fortran 77 again, would that be awesome? Or would you rather have, reduction of endless planning meetings about a project? Or maybe you didn't have to write updates to documentation every time you released a new version. Which one would you like to eliminate? Okay, so it's at this point, the vast majority are saying the legacy code. Maybe that's like, maybe when you encounter that, you want to like be able to tell someone, it's like, hey, like this is from 30 years ago. Let's move on to something else. Do you feel empowered enough to tell a colleague when they ask you to work on some old legacy code to actually try something new or move on from there? Or is that a difficult conversation? How difficult are those conversations? Any other thoughts or responses? And hopefully folks online can somewhat hear that. And if we need to, we can get a mic to pass around. But we'll soon like break out into groups because managing hybrid networking is probably hard. So nonetheless, I hope folks participating online, and if people see their hand raised in the Zoom, please let me know. But just a few more questions just to get the mind going. So let's think about best practices. There are many in software development, but what do we actually have time to do? Please rank these practices by how consistently you follow them in your own projects from most to least consistent. So which which skills and practices are you actually doing consistently? Like the things you should be doing and then actually doing them, So, how about you adding comments and documentation? Writing descriptive and meaningful commit messages, unit testing, reproducible environments. It could be even through SPAC now. Hopefully you know a little bit more about that. And that could be a way in which to offer a reproducible environment. Refactoring code, readability. So let's see, is this showing? Okay. So it looks like at least people say they're consistently adding comments and documentation. Maybe we should have separated those. Like hopefully, I would hope that you're doing comments all the time because that's pretty easy, at least while you're writing code. Maybe the documentation part is harder. Is there opinion there? Does doing one help the other? Okay, I thought this to you.
What is that?
Oh, okay. Okay. Yeah. So I was saying, depends on the language you're writing in. Some languages like JavaScript and PHP, you can write the comments in your code and then use a tool like for JavaScript, maybe JSDoc or TSDoc. And for PHP, you could use PHP Documenter, or if you have a framework like Laravel, you can use LaRecipe and extract that comment into a document. Yeah.
Yeah, I know I've always liked Doxygen. The thing is, I don't know too many scientists that consistently use or even aware of Doxygen.
Yeah, we use Oxygen a lot. I just find we've kind of given up on comments in our applications, honestly, because they have done more harm than good to us, with just based on how they go out of date. And at this point, we kind of mostly rely on the code to speak for itself, and have stood on that, honestly.
I think part of that is then making sure you're writing readable code.
Yeah.
Sometimes like, oh, you're super fancy making a
that's
one-line
been-
statement, and then it's like, I don't know what it's doing anymore.
Kind of been our focus.
Anyone else like to chime in? I think we have two more questions, if I'm keeping track of myself correctly. What keeps a scientific software ecosystem spinning? What's one tool technology you can't live without in your current workflow? Like Python, Git, NetCDF, Docker, VS Code, anything that helps you survive? As you saw a little hint of, it'll create a word map after this. So feel free to add what inspires you. Maybe you might align with some of your colleagues. I think you can enter multiple entries in the, hopefully in the Slido. I'm just, see the one, I'll get this one additional person to finish responding, then I'll show results. Oh, no, there's three. Don't want to bias everyone too much. Kind of see what shows up. 3, 2, 1. Yeah, okay. So yeah, and if you want to continue adding some ideas, you're welcome to. Obviously, I think the biggest one we see here is Git, and a lot of people using Python. I think that's obviously a big desirable today. It's kind of interesting though, at least this past week with the multiple Julia talks. I see Julia as a direct competitor to Python in terms of how they even frame themselves as being superior and more performant. So maybe at some point that might change, but I admit a lot of our scientists still heavily rely on Python, so there's not a argument quite yet, for my case, at least, to say we can't live without it. Do you like that someone added climbing, especially if you're in the blunt range area? Gotta get yourself out of that desk chair more often than maybe you otherwise would. Hopefully find other ways to keep yourself active. Yeah, and I'm a tea person though, and I'm not responding, so got a coffee option. But yeah, tons of tools hopefully you also learned about this week, and might even consider making these indispensable if they're not currently, in terms of the way in which you currently operate, and maybe even just highlighting, just thinking about what is most important to you, as then what you might be also then recommending to your colleagues you're working with, maybe the less computer savvy programming like domain scientists working with, to maybe adopt some of these as like must-haves. I've had many conversations with scientists who don't feel comfortable using Git, and I'm always try to strong on them. It's like, you need to be comfortable using Git. Like this is this required kind of tool in terms of what you are doing and with modern science and software nowadays. Anyone feel differently or agree with that?
I didn't even think about Git because it's so fundamental.
Oh,
I will, well, sorry. I will, I will say that for the scientists I work with, what's really helped with selling Git is how much you can undo anything you've done in Git, because basically within like, reasonable limits. So I've definitely found selling things like Git revert and Git reset and all of that has helped a lot in getting them a little on board. Oh, don't worry, that's also happened. Yeah.
anyone online want to chime in anything? Or I think we have like one more question and then we'll split off into our groups. Okay. Well, the last question is a similar kind of, oh, go ahead, Brian.
Yeah, can you all hear me in there?
Yeah.
Don't have a thought, but just a suggestion. When people chime in the room, maybe go ahead and introduce yourselves, since we're in a networking session.
Well, we'll be sure to do that. And even though one question left, but looking towards the future, we're all trying to stay ahead of the curve. Let's find out what's on everyone's tech radar. What's one technology or tool you hope to learn in the next year? And after everyone inputs their ideas, we can chat about it a little bit, and people online can do the same. And again, remember to introduce yourself if you haven't. I think the people that have talked already so far were also presenters earlier. So if you haven't presented, just here, you're welcome to also chime in. So for this question, AI/ML is there front and center. I kind of think we might need a game plan of how to do that, because it's admittedly a broader space than maybe we give it credit for. So any thoughts of how one might tackle learning AI/ML for what they're thinking of doing? Like, sure, there are like Coursera courses or YouTube videos you could watch, or workshops you could, sign up to attend to. Or I guess as a specific use case of AI/ML, like AI coding assistance. I think we've actually started providing licenses at NCAR for folks to use those through GitHub Copilot. Do any other organizations provide, like, IT department-wide or software engineering team group-wide coding assistant licenses? You think you should be? You want to tell your supervisor, your department heads to pay for that? Well, obviously there's a lot of things we could be learning, and hopefully you're keeping that in mind in terms of like where maybe you want to be focusing on over this coming year. Lots of interesting opportunities that you can learn from each other in terms of what are important here being added into this list. But in any case, I think after this point, our plan is to shift into our breakout groups. I might have you throw the mic back. Okay, so for those in person, we did have this easel to like vote on different topics, and I printed out basically little tents for each of these tables. There's 6 in this main room, and there's 2 more out in the lobby area. And so I did include anyone that has above a 3 vote, if you want to keep that in mind in terms of like maybe mutual interest in the group. But the highest interest was support for science software teams, Julia for modern science, and integrating AI/ML for science. Oh, and reproducibility with CI/CD. So as a way to keep each other, just introducing yourselves and maybe like taking notes on the conversation, if for each of these groups, if you can go to this.
Hey, y'all. So for everybody who's still online, feel free to, so I just had them disconnect the room since they're going to start more of an interactive activity. But I do see that we have a few people online who are joining for the virtual networking session. So I think it would make sense first, and I'm going to see if we can just have the full screen here. Let's see. But yeah, cool. I would say turn on your cameras if you're comfortable. Maybe the first thing we can do is just a little roundtable introduction. I know a couple of folks here have presented, but I still think that's a good idea. So I'll start. Yeah, so I'm Brian Vanderwind. I guess I'm conference chair. But my day job is more HPC user support. And do a lot of software installations on our HPC machine, Duracho. As I presented in the talk, I also maintain a lot of scripts that are written in Python recently, but I do also have a weird affinity for Bash. So some of the scripts end up being Bash scripts, which get a little unwieldy, and then I convert them over to Python sometimes. So yeah, anyway, that's me. I think David, you're first on my screen, so do you want to go ahead?
Sure. My name is David Swenson. I am the ecosystem infrastructure technical lead for the Open Molecular Software Foundation. So we are in a very different sort of domain than I think a lot of you are, but dealing with a lot of the same problems and the same kind of questions about developing software. Geographically, I'm in Chicago, and I see that's about it. My background is, not surprisingly, in molecular simulation. Did that for many, many years before I moved on to be more software focused.
Awesome. Yeah, I imagine a very different software stack, but a lot of the same challenges. All right, Hilario, why don't you go ahead?
Hey, I'm Hilario, also known as Lalo. A lot of people around NCAR may know me as that. But yeah, I'm a software engineer in NCAR, the ASAP group. So that's an application scalability group. So mostly looking at scientific codes and doing like performance optimizations, that kind of thing. And then whoever wants to go next, feel free to take it. I think our host here is busy.
Yeah, sorry, somebody walked up to me and was asking questions, so I had to take that real fast. Michael, why don't you go ahead?
Yeah, so hi, my name is Michael. I'm a joint hire actually between Sizzle and CGD, and I primarily work on the system for integrated modeling of the atmosphere project as a software engineer. But my background is very much applied math and computer science for undergrad, and trying to get back onto the grad school bandwagon here shortly. So, yeah, that's pretty much me in a nutshell.
All right, thanks, Michael. I guess I'll ask a quick follow-up question. We don't really have a format here. What are you thinking to go back to grad school to focus on?
So I'm leaning towards more of the applied math track. Johns Hopkins has a really good online applied math program. I thought about the computer science side of things, but a lot of the computer sciencey stuff I kind of pick up on my own outside of class anyway, and just in general, working within industry and whatnot, versus some of the more technical math, solvers and that kind of thing. Much more difficult for me to pick up outside of the classroom. I'm sure with enough time I could also get there as well, but it just takes a lot more out of me to get there. And I want to be more involved on the math side of things, because I already have a pretty heavy hand in some of the code side of things. So it's like, let me just go a little bit farther.
Makes a lot of sense. Thanks for sharing.
No problem.
All right, Ed, please go ahead.
Hey everyone, I'm Ed. I'm a graduate student at Drexel University studying environmental engineering. My main focus was to apply a numerical method in complex chemical transport models. I gave a presentation yesterday on this, and I was previously a Sizzle SciParks intern with the Darius group. Yeah, it's nice to meet everyone here.
Yeah, thanks, Ed. It's good to see you back, talking to folks from NCAR and interacting with our community. So appreciate that. And Spencer, please.
Hello. I don't know if I'm unique, but as far as I've seen so far, I'm the only Canadian participating in your group. So I don't know. Makes me feel special. Makes me feel important. Reinforce friendly relationships between our countries. I'm sure nobody wants to have any political conversations. I'll leave it at that. Yeah, so I'm an academic. I'm at McMaster University. It's in Hamilton, which is close to Toronto, which is the biggest city in Ontario, actually in Canada. My research interest is in applying software engineering methodologies, tools, techniques to improve the quality of scientific and research software. So that's why I'm interested. I like to learn more. I have experience with computational mechanics 20 plus years ago, but I've really focused on the software engineering side. So it's good to hear about real projects, what people are really doing and what their pain points are and what solutions they're looking toward, and if there'd be a way to sell my solutions to people someday in the future where they're relevant and welcomed. And yeah, there's a lot of challenges with change, but there's also a lot of challenges with productively developing high quality scientific software. So the challenges haven't been solved, so people need to keep thinking about ways to make it better.
Awesome. Thanks, Spencer. And yeah, I hope we can solve our nation's relations in this meeting, but it seems unlikely, but we're happy to have you here.
Well, there's no tariffs for this, right? So we're good.
No. Tariff-free zone. Anyway.
I shouldn't have mentioned it.
No, it's hard to avoid. So yeah, we don't really have like a defined format for this. We do have, I guess, a couple of prepared sort of discussion prompt questions that I could bring up if people want, but I'm also happy to just open the floor if there's a particular topic of conversation that people want to bring up. The interruption that I got was also a reminder that I think we have like a note stock that we don't have to fill, but if people wanted to, just so that you can kind of not have to try to remember everything that you hear in this meeting. So I'll share that in a second once I stop talking, so because I can't multitask. But yeah, if anybody wants to jump in and sort of suggest a discussion topic, feel free. And if not, I'll put somebody on the spot.
I guess so. Spencer, you mentioned something about you have some different tools or techniques or something than what you've seen here today. Is there a little could we get a little version of that in a nutshell? I guess what were you referring to?
Yeah, I always have to be careful. Right now, you don't know me, and I want you to either like me or feel neutral. And I certainly don't want to take over with these highfalutin academic ideas. But I'm going to continue because I'm an academic and I can't stop myself. I would say what I'm most excited about, sort of the big idea that I would like to see gain traction, is we call it the Drazil project. Drazil comes from Yggdrasil from Norse mythology. Yggdrasil had been taken. It's a long word, so we just shortened it to Drazil. But it's a framework tool approach where we generate everything. So you need to capture and codify scientific knowledge and documentation knowledge and technology knowledge and mathematical knowledge and computer science. That's a big, tall order. But if you can put all that information into code, if you can represent it, then you can generate everything. And I mean everything. Like the code is obvious. Code generation has existed for a long time. But this would be generating the requirements document, the design document, the build scripts, the continuous integration, however you've set that up. Just you capture the technology information and generate that YAML file based on what the domain expert wants. That's and nothing to do with machine learning. As I give my little blurb about that project, and it usually sounds like I mean feed it a bunch of scientific papers and it'll generate another scientific paper. But it's actually saying, well, we already understand the science. A lot of what we do is involving things that have been understood since Newton. I mean, some of it is deeper than that, but a lot of it is the basics are still the same. So we can just find a way to represent that knowledge, then we can reuse it in every project where it's relevant, and only have to capture it once. And it's not easy to capture, but because it's so highly reusable and relevant to so many things, and because people don't like to write documentation, and I guess the final thing that we're really excited about is each piece of knowledge or information is captured once, and then you generate all the views of it. So if you capture an equation once and that equation shows up in your requirements document and in your code, and maybe there's some test cases based on it, if you made a mistake in that equation, you will notice, because everywhere you generated it, it's wrong. Not one place where you made a silly error and everywhere else it's right. It's wrong everywhere. So you'll notice, and then where do you fix it? In one spot. You go back to your original knowledge. Oh, yeah, supposed to divide by 10, not 100, and hit generate, and then everything is corrected. So that's the bold vision. And yeah, we've started with tools in that direction. But we generate right now like projectile motion. And the most complex example is slope stability. So you have a mass of soil and you want to predict the failure plane. That's almost working. But the sophisticated high performance computing things that many of you are doing, that's for down the road. So hopefully that wasn't too long an answer. That's my big fear. I'll talk too much.
Do you have a, I missed at the very beginning, do you have a link that you could share for that project, or?
Sure. It's on GitHub, like most things. It says chat disabled.
Oh.
I don't know where I put it.
I guess I'm putting messages in the chat that are going to nobody.
Oh, well, I got your messages. I just can't have my own.
Yeah, I think chat might be disabled for us. I'm not sure if you have a meeting organizer or something.
Oh, there we go.
There it is. Yeah, now it's enabled.
Yeah, so that's the Brazil project. My colleague Jacques and I work on it with our students. But I definitely don't want to dominate the meeting, so we can talk about other things and circle back to this if we're bored. I did notice that the documentation, when I said how much time people spend on things in the poll we just did, documentation was pretty low. But I didn't know if that meant it's because people ignore documentation or because it's easy and just fly through it and it's done. It's kind of unclear from the poll results.
I think I used to feel that documentation was a good fraction of the time. I would tell people when we were teaching them best practices that, it's not surprising if your testing and documentation take more time than writing your code does. These days, though, I am using Copilot, and if I've written the function already, it just fills in my docs. It makes it a lot faster. I hit tab and it's right usually.
Yeah. How do you feel? Like, is that the right? Obviously, that's a very useful level of documentation. Very important. It says what the code does. but often there's like a higher level of abstraction. Like, what assumptions did you make to come up with that equation? That's never going to be generated from the code because it's modeling, not coding.
Yeah, if the function actually needs more explanation, then I'll probably have to fill in more. But the really tedious part of how to, just writing out what the parameters are and all of that sort of stuff, so it can be picked up by the automatic, code or the documentation generators. That part gets saved right away. If I have to write a paragraph to explain the ideas, that's easy once the rest of that is done.
Yeah, take the drudgery out, the mundane stuff. And then the thinking, that's still your job. I like that. Brazil
So are you
promises
basically are you basically using machine learning to generate like doc strings and things like that then? Is that the level that you're talking about, or is it?
Yeah, and also, I mean, I do also use it when I'm just writing, plain English. I find that the predictions are often wrong, but it gets me going. And it's like, no, that's not what I wanted to say. What I wanted to say is this. And so it's almost like it's a prompt that helps me a lot more than the blank screen does.
Yeah, the like first sentence problem of writing.
Exactly.
I guess Michael and Ed, what are your thoughts on just documentation overall? Feel free to gripe if you want.
No, I'm all for any tool that helps that part of the job. One of the things that is difficult for me as a technical person is that a lot of the documentation that I end up writing is it is technical, but it's from a it's to help a person who's not in the trenches every day. So we have a document for some of our technical processes right now. And I know how our code base works. I know how our framework works. I know where the ins and outs are. But someone who is not familiar with our code base, they're just going in blind. They don't know what the edge cases are. And so I find that anything that can automate generating or helping me write documentation for those use cases is extremely useful. Because that's where I spend so much of my time, is acknowledging the corners that I know intimately, but someone else clearly doesn't. And like, it's very difficult for me at times to convey in words how to effectively do something, because I know what the code is doing. So it's like, just let me do it myself. I can be done with it. So anything that can help with that process would be tremendously helpful.
Yeah, I totally agree with what Michael and David have said. And as like I didn't come from a computer science background at all. I had like chemistry, physics degrees, but like working with scientific softwares, I found good documentations to be super useful for people who come from more like a scientific background instead of a software engineering background. I've been writing documentations with generative, like some of the AI tools like Copilot, and I found that to be definitely revolutionizing. I previously found those like steps to be a little bit hard for me, especially from I've been always thinking in the scientific perspective instead of the software engineering side of things. Yeah, my work at NCAR with a research software engineer, and she definitely taught me a lot about like the software engineering side of things. And like I began to appreciate the importance of writing good documentation.
So I guess maybe I'll ask a roundtable question that makes sense to me in a networking session. What is the next thing that you plan to work on or you need to work on? Maybe I'll just go around. Start with you, Lalo.
I mean, I guess it seems like there's a lot of. I'm on the train of, I think AI ML is overhyped for sure, especially in the scientific domain. I think it's good. It's really awesome for like text generation and image generation, all that stuff. We don't have like a governing equation for that per se. But where you do have a governing equation or something, a lot of times people are using it in ways that I think don't make sense. and they're just getting the same answer slower and using more power and so on. But I don't mean to totally ignore the field. So to learn a little bit more about how it works under the hood and how it could be used. So I think like the idea that I've had that I haven't really pitched in terms of turning into a formal project is like sort of putting uncertainty like bounds on performance models using some generative AI stuff in the middle, sort of like as a fast way to evaluate like surrogate models, if you will. And again, this is something that's not super accurate and not governed by an exact, equation where there's an exact right answer. Maybe a machine works a little different than another machine, and the network's a little slower or something like that. So it's not, extremely, there's not one right answer. And a lot of times in that sort of fuzzy gray area, I think this could work. But in order to get that done, I need to learn a little bit more about how to actually implement some of this stuff and what are some of the tools I can use and, which one should we pick, that kind of stuff. So, yeah.
Thanks. Yeah, I sympathize. I feel like I would self-label as a bit of an AI skeptic, and I think it's just because I'm allergic to marketing. but it's also putting a nagging voice in my head that's saying like you're probably stubbornly missing things that would be useful. So I'm kind of wanting to sit down and spend more time with the tools. Like I like Notebook LM, but pretty much everything else that I've seen I like less. So, but yeah, I appreciate the challenge.
I think the Copilot thing's great. I actually use it quite a bit now, especially for the boilerplate code stuff like testing and documentation. It's like I don't want to, you're basically copy pasting most of that anyways and changing the content. So for that kind of stuff, I mean that's great. But for solving the heat equation or something, it's like we don't really need it for that. But yeah, anyways.
Yeah, the actual machine learning part. I'll just go around the circles. Well, actually, Spencer, you're unmuted, so why don't you go ahead?
Because I'm unmuted? That's good. Good criteria. I just forgot to mute. Yeah. Well, I won't repeat myself. Obviously, the Trazil project's ongoing. But I'm always looking, and maybe someone here will help me find it. I'm always looking for projects where there can be like sort of an information exchange on the software engineering of scientific computing theme. There's certain workflow that I've sort of, especially in terms of documentation, that I think this documentation would be great. I think people would love it. And I think some of the ideas people would love, and other ones they'll tell me, oh, that's not a good idea. That's very naive. I mean, especially because a lot of what I base on is smaller projects. Like my PhD was a big piece of finite element code, but not the size and scope. It was still one person that wrote it, so it's very different. So I find the more I learn about real projects, but not so big that it's hard to grasp and know where to start. But the more I learn, the more it helps. So I'm always looking, maybe a master's student that can partner with someone who's trying to write software, and my student can be the software engineer and they can be the domain expert, and have some conversations and see if something useful comes out of it, or if not, why didn't something useful come out of it? So I'm always looking for something that I can explore more and learn more about. So if anything occurs to any of you at any point, don't hesitate to let me know. I'm always starting students, and especially if it's a small enough project, even undergrad students, in capstone course and other things can get involved. Just a chance to learn and a chance to talk, kind of drive things forward sometimes.
Yeah, I guess I'd encourage you if you signed up for our conference Slack. I know it's like Slack fatigue, so no pressure. But if you want to put that sort of little blurb in our ISS 2025
that's a
channel.
good idea. Yeah, I signed up. Yeah, that's a great idea. Thank you.
David, why don't you go ahead?
Sure. So a lot of what my team does is less really deep in the science and more in like the DevX side of things. But one of the things that we're looking at doing now is trying to help our projects get their stuff cloud ready. And so I've been playing a lot with that, and we'll be doing a lot more of that in the near future. That's kind of something that we think that a lot of scientific software projects, especially our projects, are of relevance to industry. We are largely funded by, I'm not, I'm on a federal grant, but most of our hosted projects are things that make a lot of money for the pharmaceutical industry, or more accurately, we're their open source competitor to things that they spend a lot of money on in the pharmaceutical industry. So they donate to us to keep our projects going. But that's something where, we're not necessarily, a lot of them are looking more and more towards the cloud. They're moving away from on-prem hardware and clusters. And so that's something we're really trying to make sure we are ready for.
Ed, why don't you go ahead?
I guess in the near term, I'm trying to graduate from graduate school, and just to be continuing working on scientific programming stuff, which has become my interest. So like before I started my PhD, I don't know what I'm getting into, but like at this point, I know like I want to become a scientific software engineer, like working on exciting scientific softwares, basically. Yeah.
Sorry, I had a momentary freeze there. I think Zoom's been a little acting up just in general in this conference, unfortunately, but I guess I am curious. Sorry if you said this at the very end, but what are you, what thoughts do you have in mind for after you graduate?
At this point, I think I'm open to anything that can hire me. Like I think the job market is not like, especially within the field of, like my main field is more like in like air quality modeling and stuff, but I'm open to any opportunities like within my expertise, definitely. But I've worked on like different projects. I've worked on like modeling with chemical transfer models in my master's. I worked with models that are based on first order principles that are more like that are simpler, that doesn't require supercomputers. Just yeah, pretty much anything postdoc, scientific software engineer, something like that. Yeah.
Michael, I think you're up.
Yeah. So I guess one of the things that's on my to-do list is to play around more with Julia programming. I wrote a solver based off of a white paper last year, and I want to say even it's not completely done yet, unfortunately, but even just the small or the majority of it that I got done, it's like a quarter of the size of what the equivalent C++ or possibly even the Python code would look like. And so that it's very nice to have a language that has a bunch of built-in features for me where I don't have to worry about, okay, what BLAS package do I want to pull down, or what external third-party library do I want to depend on. It's all baked in. Performance might not be that great initially, but can you get the math codified, and then you can start worrying about performance and portability and whatnot from there. I found it extremely nice for edge cases like that. I'm not sure how I feel about it for production use cases yet, although we have a lot of talks about using Julia in production. So I'm very intrigued to see where that goes going forward. But at least for proof of concept solutions, it's been amazing so far, and I'm hoping to keep that going.
Does anybody else in here use Julia at all? Yeah, I feel like it's a small but very passionate population, so I expect it to grow.
Hoping we'll see what happens.
We are adding Julia as one of the target languages in the code generator for the Brazil project I mentioned. So we generate C++ and Python and the languages you would expect. And Julia's been a challenge because it's a different paradigm. So we generate some code, but we don't really get the performance benefits yet because we do it naively. So maybe you're a resource we can talk to when we get stuck.
Yeah, absolutely. It definitely is one of those you have to figure out what you want to do first, and then you worry about the performance later, because otherwise you'll be constantly going back and reiterating. And in one of the talks, I think it was yesterday, there was one of the talks about the differences between performant and underperformant Julia, and it was a missing, dot, a missing period. And so that can if that single character can tank your performance, I'm not writing Julia code for performance initially.
Yeah.
All right, I guess I'll mention, since I asked a question, I should answer it as well. The kind of the thing I want to do next is on our software stack on our HPC. I just want to add some more regression testing, because I feel like, we have more testing than we used to have, but it's still very much a users find the problems more often, I feel like, than we catch them. And I don't think we have too many problems these days, but it's still frustrating every time that happens. So it's such a big scope deployment that it's kind of tricky for me to figure out how we should best regression test it. But within the confines of what other people are doing, I'm plan to take some ideas and re-implement and add some NCAR customizations, I suppose. But that's my next to do.
I have a question about that, because I've written that advice in like a state of the practice for Lattice Boltzmann solvers paper. I talked about more testing, but the challenge is, unit testing or the test cases take too long. I mean, at the bottom line, you want to do like a real test. You can't do that every time someone does a pull request. So how do you balance out the performance and also getting that sort of continual reassurance that what's been added hasn't broken something?
I guess I'll just answer generally my thoughts that are probably more specific to like a functionality testing than performance testing. But other people should weigh in because they're probably more software focused. In terms of like testing out the software stack, I think the thing that would make the most sense would be either nightly or even weekly testing, because the pace of change there is pretty slow. We do have a test system that we try to match with our production HPC system, and I feel like if there's a requested change, it's tricky. But if there's a scheduled change, like we know a new compiler is going to come out and we want to build software with that, we could test that with a regression test on the test system before we deploy in the production. The tricky thing there is just having a large application suite. But absolutely, you're right. I feel like the turnaround on the time to solution makes it so that if I want to make a small change to our software stack, it's totally impractical to run a full regression suite, because just building out everything that I would need as a dependency there is out of scope for a lot of stuff. So I'd be curious to hear other people's thoughts as well. But I agree with you, Spencer. That's tricky.
Michael's got his hand up.
Sorry. I was wondering, Brian, have you guys looked at regression test repos yet, like Reframe? It's made by the folks at, I think that's CSCS in Switzerland. I could be wrong. But I've been actually wondering about this exact same problem for our regression test harness right now for some of our projects, because they're all in-house developed. And I would love to move to something that's off the shelf and as plug and play as you can get. So I'm curious what you guys end up coming up with as your solution.
Yeah, I will say with Reframe, I looked at it maybe a year ago and then had to be like, oh, well, there's other things to do. So I immediately lost track of the bookmark. But yeah, I think to your point, surveying the landscape again would be a good first step for me for moving forward on this.
You can say a little bit about what one of the teams that I work with now, but that I worked on previously does. That's Open Free Energy. And so they have some tests where they do really want to make sure that they are not regressing against large scale calculations. And it is you run the whole test suite before you have a separate test suite you run before you release. You have a proper test plan where you say, we do this kind of testing at every push. Then we have a larger set of tests that we run every night. And then when you're about to do a release, we send it over to Mike, who pushes the button to run it on the cluster. And we make sure visually that we have not had any kind of failure with a decent sized set of compounds that we compare with. I think that's kind of has to be at some point. You just have to have that whole end to end, and yeah.
So David, do you find it hard to get the resources to do that? I was talking to some people at SC in November, and they're like, nobody wanted to give them the resources to do testing, so they were.
Yeah, we don't have too much of a problem with that. Some of that was through collaboration with Memorial Sloan Kettering Cancer Centers, the research group there, and so we actually had someone had access to their cluster, and that's why we gave it to Mike, because he was officially employed there. But he, yeah, so that was part of it. We also, again, we do have money that comes in from, from pharma, and we can dedicate some of that with the approval of the board to hardware. We have a deal with UC Irvine where that's actually hosted there, and we were buying a number of GPU nodes that were hosted there that we would, it's some deal where it's like we get to, technically we don't just have them exclusively, we're buying them for the school, but we have access to the school's resources for a certain amount as a result of that.
Right.
So that was not too much of a problem, really.
There's not a tension between, because it's a lot of resources, the energy and the compute time, and I feel like there would be pressure on people like, let's use it to do new calculations instead of checking that we get answers that we kind of already know we're supposed to get. Like, I mean, I'm all for testing, but I could see the tension existing when it comes to precious resources.
As an organization, we are a software development organization. We are not a scientific organization. Now, we do have some projects that are creating new science, that are creating new representations of how molecules interact with each other. But certainly on the open free energy side, there is no scientific development going on there. Our job is to create software.
Right.
So it's completely an engineering process, not a scientific thing.
So if you say, we need these resources to be confident in our software, nobody's going to push back.
Yeah, we go to our board, we say we want to dedicate X dollars out of the budget to do this. We have it's an adult nonprofit, so we've got a board that includes people from the funders, and they usually say yes. They sometimes have some questions, but they largely do trust us, which was also very good to work with that. So
Yep.
Yeah.
Thanks.
Maybe that raises a follow-up question then. Do you have a sense of strategies that were employed to build that trust? Is it really just delivering, or are there other aspects?
I give a lot of credit to John Cadera, who is a professor at Memorial Sloan Kettering Cancer Center, and David Mobley, who is a professor at UC Irvine. They had former students who are now in a position to help make the case internally in the pharma companies to fund this. And it was the trust in them that got us started in the first place, I think. And then since then, we've been able to deliver. I mean, that project started in 2022, beginning of 2022. So it's not very old yet, but it's grown. It's only grown since then. Yeah.
So we're at 4. We still have like a whole other hour we could use, but I want to be respectful of people's time. So if anybody does need to jump out at any time, just feel free. But I guess with that said, does anybody else have like sort of a software engineering topic that they've just wanted to pick people's minds on?
I do. Design. I'd like to know people's approach to design. Speaking as a software engineer and what we teach at my school, for instance, UML, design patterns, it's unclear to me how much of that is actually used in scientific computing software. I actually, it's also unclear to me how useful it is. But I don't want to tell you what I think. I'd really like to know what approaches people take to not coding itself, but sort of that system architecture before, what goes into what class or module or unit or file, whatever, however you divide things up. I don't know if you've got things to share in that area.
We got a few. We really tried hard to use UML when we were starting out, because again, Open Free Energy 2022 Greenfield project. So, we really tried to use UML, and it just didn't. It didn't clarify anything. It didn't help. I do find that at least
And you didn't,
knowing
sorry, David, but you didn't have a very OO design, would be my guess.
we do, though, but I think that that wasn't the way for us to communicate it. I mean, it's a completely object-oriented thing. The point is that you have a pipeline that things go through, and a lot of things kind of have to be modular components within that pipeline. And so I felt like it's less of a web of things that are talking to each other and more of a linear structure of this goes to that, to that, to that. We did find a lot of sort of more informal drawing of pictures to explain the connections between things helped, but converting that to proper UML did not. It sometimes made it more confusing, actually. And yeah, we also I do the same regarding design patterns. I think that at least knowing the terminology around these things is really useful. Because it prevents you from reinventing wheels. I mean, often, I learned all those things later when I'd already invented a few of them myself, and I'm like, oh, that's what it's called. But yeah.
So, what are your favorite patterns? What are the ones that are most relevant, I guess?
Well, we made a slightly strange decision to do a flyweight thing that was kind of our entire basis of all of our simulation objects is that it's to ensure that there's a unique, it's how to say this right, it has to do with ensuring that they don't get duplicated or when they come out of serialization. That was the main reason we were doing it, but yeah. It's not one that we would use often, but it's one that in that project we use quite heavily. I mean, factory pattern shows up all the time. If you don't know what that is, it's going to be, it's just so nice to be able to say, this is the factory and move on. We do a lot of something that's very similar to template method, but isn't exactly, because you can plug things in. It doesn't have to be a subclass. Let's put it that way. I always feel like the template method thing was technically it's a subclass, but you could also just have variables that take, callables in there, and that's what we usually do. So those are a few that come to mind that we use a lot of. I don't know what other people think, but yeah.
Maybe this is so I'm relatively new to the in-car, but for the last couple of years I was a postdoc at NASA Ames, and before that I was doing my PhD with a couple different, working with some people in the DOE and various universities. So I feel like generally what I've seen so far it's just a Wild West, and everybody does what they know how to do or what they're used to. I know one person likes design patterns and I see them in their code, and I know somebody else that doesn't, and they're in the same repository, in the same project, and they look different and they do things differently and they abuse the API that's in different ways and that kind of stuff. And you can kind of tell who wrote what after you've looked at a couple different files. I mean, you got to look at the commit history. So, the Wild West, this person likes writing documentation, that person doesn't do tests, and that's just kind of where, things fall where they fall. And but largely that was, I think, the case especially in academia, but also at NASA, I feel like, especially working in the research computing groups where people were more interested in the results of the code and not the code itself.
Right.
To sort of Yeah, to follow on with that, yeah, it's similar to everyone else's. You have to conscientiously choose and like know beforehand that you need this, or you come across it and you take the time to refactor it. In my experience, language also dictates how easy or possible even it is. In Fortran, which is a lot of code that we deal with, it's almost impossible to do proper design patterns in Fortran. It does have object oriented, kind of. It does have some other things, kind of. But if you want to do, pure design pattern implementation, it's almost impossible. C++ is better, but not by much, depending on what you're doing, in my opinion. Language also does dictate a lot of what you can and cannot do easily. You can do them to a degree. Is it going to be worth it at that point to maintain this thing that you've written in a language that's not really meant for that thing? Is it going to be worth it to maintain that going forward versus using a different language where it's more native? There's going to be pros and cons there.
Mm-hmm.
Yeah, I do agree with the comment about just it being the Wild West. I feel like probably in scientific software in general. And it's not, I don't think it's for lack of care. I think it's more so just for lack of even knowing about this as a concept. A lot of the people who are writing the software would never know to even think about it.
Mm-hmm. So typically people would have a domain knowledge first and then learn coding and software development. That's the normal career path, I guess.
If you're learning like good software development practices, it's whenever you encounter people who are actually doing it. Like I was halfway through my postdoc before that happened. And then all of a sudden I started working on a big project that took me a long time to continue with. But that we started that thing, and the guy who started it shortly before I joined knew all of the best practices stuff. And I'm like, oh, writing unit tests. If only I had known about this during my PhD, I bet I would have gotten a couple more papers out.
Yeah.
Yeah, my work involved like editing like Fortran source codes, which are like CMAC is like this community multi-scale air quality model. It has multiple modules like aerosol processes, gas-phase chemistry, all these transport. And when you read those source code, you kind of realize they're all written by different people. And like it also has mixed Fortran 77 versus Fortran 90 all compiled together. But as long as it works, like as long as the result seems reasonable, like I guess there are no dedicated software engineer that are working to make it, to like refactor it, to make everything consistent with each other. But yeah, I think that's a common theme in the scientific software domain, I guess. Yeah.
Mm-hmm. So Michael mentioned programming language. I assume there's no functional programming languages that are popular, like Haskell or F# or
I mean, I've dabbled in F# professionally at my very first job, and we used it a little bit. But yeah, in terms of a purely functional first language, at least in my experience, I don't know of anything that comes to mind as a pure functional language and library that's used, at scale, within the enterprise, at least within scientific computing. It may exist. There may be someone working on it. I don't know. Everything's pretty much Fortran and C++ or some other weird older languages, I'll say.
Yeah, I've read papers promoting functional programming, especially because of the lack of side effects, which is, if you want to improve properties, is pretty nice. And but they were academic. I don't think it was used.
I think there's a critical mass problem. Like I had a colleague, I guess I have a colleague, I should say, who's super jazzed about Haskell. It's like his favorite language. And when he writes little scripts and utilities, like that's what he wants to write it in first. But then his enthusiasm gets tempered because it's like, well, you're working on a team and none of the rest of us are going to be able to read this code without spending a day to get up to speed on kind of a whole different way of thinking. It's not like going from Python to Julia or something. So
Right.
At that point, it's like, okay, well, I'll go and write it in Julia, and you'll deal with that, even though we're all Python programmers.
Right.
So I think there would be more if there were just collections of people who were, you had a community that was sort of insular enough that everybody in that community was willing to just use that to, design codes. But I haven't seen it.
Yeah, that makes sense. That's what I expected, but it's good to ask, and who knows what the future holds.
What's your perspective on it, Spencer? Is that do you want to see more of it?
Maybe. I mean, the Brazil project is written in Haskell, and it's ideal for that. But we generate. We generated a lot of languages. We do not generate a functional programming language yet because the paradigm is so different. The academic papers are exciting about the idea of, if the compilers could be smart enough, they would be told these things cannot interact, so you don't need to worry about it, and somehow some magic happens and actually performance could actually be not hurt, but maybe even improved. But someone more clever than me needs to know how to do that. But I feel like it could happen. But it is, like you said, Brian, it's a very different way of thinking. People don't like recursion. Like, just my son actually is in second year software engineering and he's complaining about recursion. It's a different way of thinking. And if you're writing in Haskell, there are no loops. You need to use recursion. So I think after a while, we actually teach it to some high school outreach. And if people learn functional programming before they learn another programming language, it doesn't seem that hard. It's almost unlearning all the other stuff that makes it more difficult. Especially, like you said, if you could do it in Julia or Python quick, why are you going to, write the code quickly? Why learn something else? So I'm curious to see what might happen in the future. I think it'll have a place. I don't know exactly what it'll be, but I think it'll have a place in high performance computing of some sort.
Yeah, I'd be interested to see the adoption of like what was presented yesterday in the tutorial, or maybe it was mentioned this morning, some of like the pure and simple functions in Fortran and, the stuff that's latest in the standard there that's a bit more functional in design. But it sounds like it's not really getting adopted by codes. So.
Right.
Well, and I think in that aspect, it's a sort of a double-edged sword because having the new stuff would be great, but there's already so much Fortran out there being used in production. There, in some cases, at least one project I'm aware of, they're never going to get off of iFort. Like that, they will always have to use that until the end of that lifetime of that program. And so I would love to use some of the latest stuff, but if it has to work with that program, it might as well not exist to me because it doesn't.
I don't know if this is software that's used on the HPC systems, but I don't plan to support iFort forever. So.
No, this is for some operation stuff that we have to collaborate with. So it's not on our systems, but unfortunately, the code that we are currently writing to some degree has to play nicely with that system. So we have to deal with it.
Well, I guess maybe the one other prompt question I'll mention, and then I'll stop. I did think, I don't know how many of you saw Ed Hartnett's talk today, sort of about, use AI or else. but I was curious what your all thoughts were on, I guess, the place of the programmer or the software engineer in like this job in 10 years. Is it, is it really just, is it gone? I guess that's the worst. Or is it like hand holding an AI that does most of the coding, or is it, what do you think?
I think in less than 10 years, it's going to be mostly hand holding the AI. I mean, that's a lot of what I'm doing already. The thing I'm worried about is I can do that because I've been writing software for 30 years. And so I understand what looks good and what doesn't. How do you get to have that experience that I have if you're doing vibe coding?
Yeah, I'm not surprised about the whole vibe coding concept, but it kind of freaked me out.
I mean, I don't know much TypeScript, so I wrote a good chunk of something in TypeScript in an evening just doing that. And it's, I knew enough that I could follow it, but it felt like that. It felt like I was just like typing things in and magic was coming out, which is kind of the vibe coding thing.
I think it is going to be a lot of hand holding, but at least the current problem is the complexity that a lot of these things generate, though. They just do things in really weird ways, especially if you're working in something that's not super well supported. Like for GitHub Copilot, I found that. So I don't like doing things in Bash that much. Usually I do it in Python, but I've been sort of using a lot more Bash since I got the Copilot license, just because I can tell it, just write a Bash script that does X, Y, Z, and it'll do it. And I can read Bash pretty well, but I just don't like writing it because I don't remember all the exceptions and the edge cases and stuff. So, but for that, it works fine. But if I ask it to do something in like some library that we're using, that's just like some C++ library or something that not that many people use, even if I point it at the documentation and say, here's how you use it, I get really bad code. It's long, it's complicated, it hallucinates. So for stuff that's super well trained, then yeah, it's probably okay. But I still get some really complicated stuff out of Bash that I'm like, you could do this in like, one line with a pipe, and you're piping like 6 commands together, and it doesn't make any sense. But I guess it gets the right answer, for this case. So then I got to replace that, right? So
I had a really great coworker years ago who blatantly told all of us, like, we are all training the machine that will take our jobs. Like, and he knew this a decade ago. He called it. So, I'm kind of on the same page. I don't know that we're going to be out of a job, but I think it's going to just be a lot of hand holding going forward. And as a proof of concept, I was just poking around with Gemini today. And I said, write me a Fortran program that does X. And he gave me a couple of options for which way do I want to do it. It understood that there's different ways to approach the problem. And I was like, okay, that's scary. And then I said, okay, now write me unit tests. And I only gave it the word PF unit. I didn't even point it to a web page or anything. And it generated valid PF unit tests. And then I said, okay, write me an fpm.toml file that can build this via FPM. And it built it. And I tried it out and it worked. And I was like, okay, this is getting real spooky. And then I said, okay, now let me get a little crazier. Build me a spec package.py file. And I spun up I got a quick and dirty spec environment up and running. And it did a spec install and it worked. And I was like, okay, now this is really terrifying, because that loop from writing code to the boilerplate to the infrastructure to, getting an installable product would take me forever. And the fact that it did it, and granted it's a bit of an edge case because it was a simple demonstration, program, but the fact that it understood the loop there of how to get from A to B, that was terrifying. I'm happy because it takes away a lot of that annoying boilerplate that I have to do. But it is getting there to a terrifying degree.
I don't know. I mean, what you described, Michael, sounds very impressive. It is very impressive. I haven't done the same thing, but I've been impressed with, wow, it did that. but I'm not as optimistic. I missed the talk from today, so I don't know what exactly was said, but there are two things that make me think that it's not the end of programmers. I think for one, it might morph what people do. So they move to more high level things, more design, interacting with the clients and what are the requirements. And so, yeah, they're not doing as low level things, but, you know, anytime technologies come along and people say it's gonna ruin everybody's jobs, it may have taken away those jobs, but things got better and there were more jobs just at a higher level. So I think that will repeat. And I anticipate that there will be a dramatic failure that will be blamed on AI generated code. And it was Hilario or somebody else said that it's really weird what they did, but I guess it works. Somebody who's not knowledgeable is going to just take that code and say, there, I did my assignment, and then something horrible is going to happen, and then it's going to overcorrect. And there is explainable AI. They're trying to address that, but I'm not that very optimistic about explainable AI. I don't think that's going to. I think eventually they're always going to say, just trust us, it works. And if it works 99% of the time, that's still not good enough in some cases.
Although
we'll stop.
one cool thing to fight that is, because I've used this to play around a little bit to generate some things in scripts. And when it does give me a really long, complicated line, I usually end up never using it. But then I also ask it, why does this work? And it can explain, well, this command does this, and then with this argument outputs to that, and then we pipe it to this, and like with this obscure argument that no one uses, but it's technically in the man page, does this, and that's why it works. I'm like, oh, okay. So like, it's a nice way to kind of learn a little bit about, you know, maybe some more, I don't say like how to abuse the, you know, some of these tools, some of the weirder corner cases that aren't used that often if you were to search like Stack Overflow or something, you know. So but then usually I'm like, okay, we could do this, you know, in one line instead of 5 or something, but it kind of learns something and then I move on.
Mm-hmm.
I think the one thing that I'd really like to see in that sort of exchange, or maybe not like to see, I don't know, depends on one's perspective on whether this is all good or not, but like in the example you're describing of asking it to explain its work, like let's say you were to reply and say, well, wouldn't this like single pipe version of this be better? I feel like most of the time it's going to be like, oh yeah, you're right, it's very differential.
It says that every time. It's like, you're right, and then it changes it. Yes.
Like I'd love to see scenarios where it actually is like, it's like, no, I like, this is what I'm recommending to you, and I insist on it, and here's why. And of course that needs to be right. It's not good if it's like a confident, you know, liar, I guess. But I think, you know, once there's that sort of memory and permanence, that's when it's going to be really like a full-on assistant, or maybe colleague if you want to go that far.
I think a lot of that might also be how you prompt it. If you say, wouldn't it be easier to do this, it will always agree with you. If you say, what are the use cases where this would not work? Then it will either come up with something or it won't, right? Like I've done that a few times where I'm like, that's how I prompted it, and it would sometimes give me an answer of no, that doesn't work, and sometimes it would say, yes, that would be better.
Yeah, that's a great point, David. I don't think too much about the prompt engineering, but obviously, like, it's a whole field now, so I should.
I've also been wrong too. I'll say I got to give it credit where it's right and say like, it'll do something and I look at it and I say, there's no way this works. This can't be. And then I just curiosity run it. And I'm like, it does. And then that's also get to learn something and then be like, well, this is some, you know, for performance reason, this is going to be faster most of the time or something. And I'll be like, huh, I didn't think about it like that, but I guess it will be. And then that line stays or something. Yeah.
Cool. Well, I guess any final thoughts? Maybe we'll wrap up here at 4:30 Mountain Time. So yeah, anything anybody else wants to bring up?
I'll just say I enjoyed meeting you all. I thought this was a nice idea. I didn't think, I wasn't that optimistic that it would work, the virtual breakout. And I think it worked pretty well. You did a great job, Brian, sort of coordinating and leading the conversation along. It's been fun. Thank you.
Thank you. Likewise. Actually, the person who was supposed to lead this, like, he's like, "Oh, I actually have to teach a class. I have a conflict." So I'm like, "Okay, I'll fill in." So I'm glad it flowed.
Yeah, thanks. Also great to meet everyone.
Good to meet all of you.
All right. Take care, all, and hopefully see some of you or most of you at the final day of the conference tomorrow.
Yep. Bye.